distinguished international delegates, respected speakers, industry leaders, railway professionals, ladies and gentlemen. A very warm welcome to each one of you today to the second Internationl Heavy Haul Seminar 2026, jointly organized by Dedicated Freight Corridor Corporation of India Limited and the Center for Heavy Haul Rail Research and Development. It is indeed a privilege to host this prestigious global gathering that brings together some of the finest minds in heavy haul railways from across the world. As we have already heard, coming together is the beginning, staying together is progress, and working together is success. Today we celebrate exactly that spirit of collaboration, innovation, and shared learning. The theme of this year's seminar, Engineering Reliability at Scale, the next phase of heavy haul railways, integrating engineering, maintenance and intelligence across high-capacity freight systems. It reflects the evolving priorities of the global railway industry, where reliability, resilience, digital transformation, and intelligent asset management are becoming central to sustainable freight operations. Over the next 2 days, experts from across the globe will share valuable insights on reliability engineering, predictive maintenance, digital twins, AI-enabled monitoring systems, signaling technologies, infrastructure management, and the future of heavy haul transportation. Ladies and gentlemen, India today stands at the forefront of railway transformation. The dedicated freight corridor has emerged as a landmark achievement in modern rail infrastructure and logistics efficiency. As we begin the proceedings for the day, may I please request Managing Director, DFCCIL, Shri Praveenji, to kindly please welcome our esteemed dignitaries who have joined us here. We welcome Shri R. Mohan Raja, Secretary, Railway Board. We request you to kindly please accord a green welcome to our dignitaries. Ladies and gentlemen, please join hands as we welcome Shri R. Mohan Raja. A very warm welcome to you. We also welcome Shri Sachendra Mohan Sharma ji, Executive Director, Railway Board. We welcome you, sir. EDCC, Railway Board, a very warm welcome to you. We welcome Ms. Carrie Gonzalez, CEO of MXV Rail and President IIHA. A very warm welcome to you, Ms. Carrie. We welcome our esteemed dignitaries. Please join hands, ladies and gentlemen. To formally welcome all participants and set the tone for this important international gathering, may now please request Shri Praveen Kumar ji, Managing Director, DFCCIL, to kindly please present the welcome address. Sir.
Thank you. Good morning to all of you. Distinguished guests, experts, colleagues from Indian Railways, partners from industry and academia, ladies and gentlemen, a very warm welcome to the Internationl Heavy Haul Seminar 2026. It is a privilege to host you at Bharat Mandapam for second edition of this seminar. Last year, in the month of June itself, we have conducted the first seminar. We are especially honored by the presence of our Secretary Railway Board, Mr. Mohan Raja, our Executive Director, Corporate Communication from Railway Board, Carrie Gonzalez. She is the chairperson of the Internationl Heavy Haul Association. The strong international cooperation reflects the growing importance of India and DFCCIL within the global heavy haul community. Last year, we spoke about moving from building our corridors to operating them. This year, our theme is engineering reliability at scale, because as our trains run heavier, longer, and more often, reliability can no longer be the achievement of any single asset. It has to be engineered into the whole corridor, whole gamut of infrastructure, that is track, rolling stock, overhead equipment, signaling, and operations working as one system. Over the next 2 days, we will explore reliability engineering under sustained loading, condition monitoring, digital twins, predictive maintenance, signaling and train control systems, including our own journey with Kavach. We will also examine institutional learning and the heavy haul experience. I particularly encourage you to engage in the panel discussion featuring some of the most experienced leaders in the global heavy haul operations whose insights span decades and continents. Let me highlight 4 themes which I consider very, very important and deeply concerning to us. The first and foremost theme is safety. Safety, safety, safety. As custodians of the freight that powers a growing nation like India, we have a responsibility to move it safely for our people, our customers, and the communities our corridors serve. That is why we continue investing in continuous train protection, condition monitoring, predictive maintenance, and automated and autonomous inspection. Safety is not a constraint on performance, it is a foundation of our entire infrastructure. Second, the responsibility to lead. DFCCIL today operates one of the most advanced electrified heavy haul railway systems in the world, carrying some of India's longest and heaviest freight trains and enabling large-scale double-stack container operations through its high-rise OHE infrastructure. Yet leadership is not defined by what we have built, but what we choose to do next. As a young organization, unconstrained by decades of legacy systems and practices, DFCCIL has a unique opportunity and responsibility not only to adopt global best practices, but also to shape the next generation of railway engineering in India. We must evaluate emerging technologies, challenge conventional approaches, and take informed decisions ahead of the industry when required. If future freight corridors are to be safer, more reliable, and more efficient, someone must be willing to take the first step. DFCCIL intends to be that organization. Third, the long-term partnership in maintenance. Reliability is sustained over decades and cannot be achieved through relationships that end at procurement. For this reason, DFCCIL has become the first entity in India to issue 12 years comprehensive operation and maintenance contract for tamping machine with Plaza and rail grinding machine with Vandana International. This is a contract for 12 years. We also signed several MOUs with international universities, domestic universities, and this is our endeavor to develop our human resources. These contracts transform the relationship between buyer and supplier for long-term partners with a shared stake in asset performance, reliability, and uptime. This life cycle-based approach is the maintenance model we are building and the standards we hope the industry will increasingly embrace. My final theme is one that goes beyond infrastructure and is about nation building, that is Make in India. World-class technologies must increasingly be built on Indian soil. To every company in this room, our message is clear: bring your technology, but make it in India for DFCCIL and for Indian Railways. Partner with Indian industry, transfer the know-how, build the skills here. This is how we create lasting value, sustainability, resilience, supply chains, and genuine self-reliance, and it will be a clear and continuing focus in how we connect, contract, and how we partner. Now, why do these themes matter so much today? Because the work ahead of us is enormous. The eastern and western dedicated freight corridors were only the beginning. The Government of India has announced the proposed east-west dedicated freight corridor spanning approximately 2,100 route kilometers from Dankuni to Surat. This is the next major chapter in India's freight rail transformation. And it will not be delivered by DFCCIL alone. It will require the collective effort of technology providers, OEMs, researchers, and operators represented in this hall. There is significant work ahead, and we want to undertake it with you, designed for reliability, built in India, and delivered safely from inception. I therefore invite all our partners to engage actively over these 2 days and remain engaged long after the seminar concludes. The opportunity begins before us is real, substantial, and only just beginning. Let me thank you, our co-host, that is Center for Heavy Haul Rail Research and Development, that is a sibling of Dedicated Freight Corridor. This is not-for-profit society, and this is taking a lead in heavy haul operation seminars. Our speakers and panelists from around the world, and every delegate present here today. Your participation makes this is a truly global forum. I wish you 2 days for rich, candid, and productive deliberations. One thing I always tell during my address, as these 2 corridors have been delivered and functioning very well, एक मुंशी प्रेमचंद की एक वो है कोटेशन है कि DFC has making lot of impact on the Indian logistics. I am forced to tell about this quotation, which is very, very apt. That is what is known as प्रत्यक्ष प्रमाण के सामने संदेह को स्थान का. Thank you and Jai Hind.
As you rightly mentioned, sir, leadership is not only what we have already built, but also what we choose to do next. Thank you, Praveenji, for sharing your views with us this morning and setting the tone for the seminar which is beginning. Thank you very much. Ladies and gentlemen, before we proceed further, let us take a brief visual journey through the achievements, vision and future aspirations of DFCCIL and the global heavy haul railway community. May we please invite your attention towards the screen and also request our team to please play the video.
In the 21st century, economic growth is driven by the strength of logistics infrastructure. Conceived in 2005 as a transformational national mission, the Dedicated Freight Corridor Corporation of India Limited, DFCCIL, is redefining freight transportation for one of the world's fastest growing economies. Today, India's dedicated freight corridors are not merely railway lines. They are high-capacity freight arteries powering industrial growth, strengthening supply chains and accelerating economic integration across the nation. On 31st March 2026, India achieved a defining milestone with the commissioning of the final section between Jawaharlal Nehru Port and Vaitarna, completing the entire 1,506 km western dedicated freight corridor. Together with the Eastern Corridor, DFCCIL now operates 2,843 route kilometers of dedicated freight infrastructure, among the largest heavy haul rail networks in the world. Purpose-built exclusively for freight movement, the corridor supports trains up to 1.5 kilometers in length, axle loads of 25 tons, and train loads approaching 13,000 tons. Freight trains now operate at speeds of up to 100 kilometers per hour, dramatically improving efficiency, reliability and turnaround time. Transit between Jawaharlal Nehru Port and the National Capital Region has reduced from over 72 hours to less than 24 hours. In January 2026, DFCCIL established a national benchmark by interchanging a record 907 freight trains with the Indian Railways network in a single day, reflecting exceptional operational capability and coordination. The Dedicated Freight Corridor stands as a landmark example of India's growing engineering and construction capability. Executed across challenging terrain and complex conditions, the project includes iconic infrastructure such as the Kalamboli flyover, hundreds of bridges, and multiple grade separators built with remarkable precision and scale. A defining innovation of the Western Dedicated Freight Corridor is its specially designed 7.54-meter high overhead electrification system, enabling seamless double-stack container operations, among the most advanced heavy haul freight systems globally. Advanced signaling systems, centralized train monitoring, AI-enabled inspection technologies, dedicated freight information system, and modern operations control centers at Prayagraj and Ahmedabad ensure precision-driven and technology-led operations across the network. Though constituting only around 4% of India's rail network, the dedicated freight corridors already carry nearly 13% of the nation's rail freight traffic. The corridors are reducing congestion on conventional rail routes, lowering logistics costs, improving supply chain efficiency, and enabling faster movement of coal, steel, automobiles, food grains, fertilizers, containers and e-commerce cargo. Integrated with the PM Gati Shakti National Master Plan, the corridors now form the backbone of a multimodal logistics ecosystem connecting ports, industrial corridors, logistics parks, freight terminals, highways and manufacturing centers across India. Gati Shakti multimodal cargo terminals being developed across the network are further strengthening last mile connectivity and seamless integration between rail and road transportation. Building on this landmark achievement, India is preparing for the next phase of freight mobility. The proposed 2,150 km east-west dedicated freight corridor connecting Dankuni to Surat will further strengthen connectivity between key manufacturing hubs and major ports. Additional future corridors will continue expanding India's integrated freight network and support the country's long-term economic growth. Behind this transformation stands a modern and future-ready institution. The new corporate headquarters of DFCCIL in Noida reflects the organization's evolution into a technology-driven enterprise focused on innovation, operational excellence and sustainable growth. From ports to production centers, from industrial corridors to agricultural markets, a new logistics ecosystem is emerging across India, integrated, efficient, sustainable and future-ready. Today, DFCCIL stands among the defining heavy haul freight achievements of the modern era. DFCCIL is proud to have hosted the Global Heavy Haul Seminar last year in New Delhi. DFCCIL is not only moving freight efficiently, but making a pivotal contribution in ushering India into Viksit Bharat.
Integrated, efficient, sustainable and future ready. Thank you very much for that wonderful video. Ladies and gentlemen, as we proceed, may I please take the opportunity of requesting Secretary Railway Board, Shri R. Mohan Raja, to please address the gathering. Sir.
Thank you. Good morning to all. Dear guests, international delegates, railway experts, business leaders, officers from Indian Railways and DFCCIL. Dedicated freight corridor today stands as one of the most significant infrastructure initiatives of Indian Railways. Within a short span of operation of DFCCIL has demonstrated remarkable growth in freight throughput, operational efficiency and service innovation. Today, nearly 400 freight trains are operating daily on the DFC network, with throughput touching around 558 million GTKM per day. What is particularly noteworthy is that while the DFC network constitutes only a small percentage of the overall railway network, it is already carrying nearly 13% of Indian Railways freight traffic, clearly reflecting the efficiency and capacity of dedicated freight operations. The operational model of DFCCIL has also opened new possibilities in freight logistics. Initiatives such as high-speed, small cargo services and innovative trucks-on-train operations are redefining multimodal freight movement by improving first and last-mile connectivity, reducing transit time and providing more economical and sustainable transport solutions. As freight operations become faster, heavier and more intensive, the focus must now shift towards ensuring reliability, availability, and intelligent maintenance of railway infrastructure. Traditional maintenance approaches alone are no longer sufficient for modern heavy haul systems. There is a growing need for integrated and predictive maintenance practices driven by real-time data, automated inspections, and intelligent monitoring systems. In this direction, DFCCIL has already adopted advanced technologies and data-driven maintenance systems aimed at improving asset reliability and operational continuity. The use of automated inspection systems, sensor-based monitoring, machine vision inspection systems, and predictive maintenance frameworks is enabling early identification of defects and reducing the possibility of operational disruptions. The integration of artificial intelligence, remote monitoring, predictive maintenance systems, and advanced inspection technologies is steadily transforming railway maintenance from a reactive approach to a more proactive, predictive, and technology-driven model. Aligning closely with the vision of this year's seminar on engineering reliability at scale and ensuring greater reliability, operational safety, efficiency, and sustainability across modern heavy haul freight networks. I am confident that deliberations during this seminar will lead to a valuable exchange of knowledge, stronger collaboration, and meaningful insights into the future of heavy haul railways. I once again congratulate DFCCIL and all associated partners for organizing this important seminar and bringing together such an eminent gathering of experts from across the globe. I wish this seminar great success and look forward to productive discussions and meaningful outcomes. Thank you.
Thank you very much, sir, for addressing us. Your perspectives on the evolving challenges and opportunities in heavy haul operations, coupled with your emphasis on innovation, reliability, and technological advancements, have provided valuable direction to all of us today. As we move further, may I please now request Shri Sachendra Mohan Sharma ji, EDCC Railway Board, to please address the gathering. Sir.
Thank you. Namaskar. Good morning to all. Ms. Carrie Gonzalez, Chairperson IHHA, MD DFC, distinguished delegates, global rail and academic experts, industry leaders, officers from Indian Railways and DFC, media personnel, ladies and gentlemen. On this World Environment Day, and having been part of DFC, it is a privilege to address this distinguished gathering at the International Heavy Haul Conference 2026. DFC has been part of the larger vision of our Honorable Prime Minister, Shri Narendra Modi ji, and our Honorable Railway Minister, Shri Ashwini Vaishnav ji, the vision of Make in India and reducing the logistics costs in India. Today, DFC carries 13% of our freight. The seminar comes at a defining moment with the commissioning of the last stretch of the dedicated freight corridor, marking the completion of one of the most ambitious infrastructure projects anywhere in the world. This also marks a new beginning of more complex and important phase of sustaining reliability, efficiency, and operational excellence at scale. Indian Railways today is moving forward through a period of accelerated transformation. Over the past decade, the focus has expanded from capacity creation to system optimization. Integrated infrastructure, technology, creation of systems, operations and maintenance into a unified and intelligent railway ecosystem. The emphasis is now on building railway systems that are not only larger, but smarter, safer, more resilient, and future-ready. In this context, the DFC represents a fundamental shift in the philosophy of freight transportation in India. It has demonstrated how modern railway infrastructure can improve average speeds, enhance network efficiency, reduce logistics costs, lower carbon emissions, and create new economic opportunities across the regions. Heavy haul operations involve continuous stress on track, rolling stock, signaling systems, traction assets, and operational interfaces. Hence, reliability can no longer be viewed merely as a maintenance function. It must become an integrated engineering philosophy embedded into every aspect of railway operations. And as we move towards an AI-enabled predictive maintenance regime, DFC has already deployed the machine vision inspection systems, the RFID-enabled monitoring, automated track inspections, hotbox detectors, remote monitoring systems, just to name a few. This technology, of course, is trickling down into Indian Railways. This is precisely why the theme of this year's seminar, Engineering Reliability at Scale, is both timely and more significantly important. Equally important is the need for having this institutional knowledge and technical capability initiatives, and such initiatives taken by the Heavy Haul Institute and DFC will help in continuous collaboration with international experts and international partners, and will also play an important role in developing specialized expertise and promoting global best practices for the next generation. Seminars such as this are extremely valuable as they bring together experience, innovation, and strategic thinking on a common platform. I extend my sincere compliments to the DFCCIL and all the associated partners in organizing this important international forum and convey my best wishes for the success. To all the international participants, I warmly invite you to experience India's renowned hospitality and culture, and I hope you find time to explore some remarkable places our country has to offer. Thank you very much. Jai Hind.
We sincerely thank you for your enlightening address, sir, and thanks again for the valuable contributions and sharing your thoughts with us today. Ladies and gentlemen, as we proceed, we will be launching compendium of this seminar now, which contains all technical papers of the seminar. May I please request the distinguished guests and MD DFC to please unveil this compendium. Please join hands, ladies and gentlemen. Zordar taliyan. A huge round of applause. The compendium containing all technical papers of the seminar. Thank you very much, ladies and gentlemen, for being here with us in this inaugural session. We will now be moving forward for the inauguration of the exhibition in the adjacent hall, which will be followed by high tea outside the summit hall. So we invite you for the inauguration of the exhibition now, which will be followed by high tea outside. May we request all dignitaries to kindly proceed for the inauguration. and we request the attention of everyone. So to ensure that, may I please request everyone to put your phones on the silent mode, please. Ladies and gentlemen, welcome back after the refreshing break that all of us enjoyed. We will now resume the program with what is undoubtedly one of the highlights of this seminar. It is a privilege to welcome Ms. Carrie Gonzalez, Chairperson of the Internationl Heavy Haul Association and Chief Executive Officer of MXV Rail. MXV Rail is widely recognized as one of the world's leading railway research, testing, and technology organizations, supporting railways across North America and beyond in advancing safety, reliability, and innovation. As chairperson of the Internationl Heavy Haul Association, Ms. Gonzalez also plays a central role in guiding the global heavy haul community and fostering collaboration between railway operators, researchers, and industry leaders across the world. With more than 2 decades of experience in the railway sector, she brings a unique perspective that spans engineering, operations, technology, and institutional leadership. Few individuals are better placed to speak about the future direction of heavy haul railways and the challenges that lie ahead as our industry seeks to move freight with greater reliability, safety, and efficiency. Ladies and gentlemen, please join me in welcoming Ms. Carrie Gonzalez for the keynote presentation.
Let's see if this is working. I'm waiting for my slide deck to come up, so, oh, there we go. Let's go back.
Move it from there.
Okay,
Or it can be moved from here also.
yeah, I have it. It's perfect. I think we have it all up and ready. So, good morning, and thank you to DFCCIL and the seminar organizers for inviting me to be here again this year. It really is a privilege to join you and open up what I believe is going to be a very important conversation. The theme of this seminar is engineering reliability at scale, the next phase of heavy haul railways. And I think that theme is perfect for the current state of India's railways. Because this isn't just a conversation about technology, and it's not just a conversation about individual engineering issues. It's really a conversation about how we build reliability, performance, and long-term operational success across an entire system. My goal this morning is to help set the tone for the sessions that are going to follow with one simple idea. The next phase of freight rail is not just about expansion, it's about building reliable, resilient, and maintainable systems that can perform at scale over time. So I wanted to get started with talking about India and entering into the next phase of freight rail development at a time when the global rail industry has already built some very meaningful experiences in safety, reliability, efficiency, lifecycle management, and systems integration. Over the next 2 days, we're going to get to talk about reliability-centered maintenance strategies, predictive diagnostics, lifecycle optimization, and data-driven decision-making. We're also going to be looking at the strategic importance of the East-West dedicated freight corridor. All of these points to both the scale and the scale of the ambition and the importance of getting this next phase right. And it really creates a real opportunity because decisions made during a period of major corridor development don't just shape the next phase of a project, they shape the performance for decades. Infrastructure at this scale has a very long life, and it's a very big investment. So the maintenance philosophy, the technology choices, the validation standards, and the operating assumptions put in place early are either going to strengthen long-term reliability or make the system harder and more expensive to sustain later. That's why this important moment matters so much. It's not just a moment of expansion. It is a moment of design discipline, life cycle thinking, and strategic choices. And the good news is that India doesn't have to start from zero. There are a lot of lessons that are already available from mature heavy haul systems around the world, and the opportunity is to take those lessons and adapt them to India's operating conditions, priorities, and institutional strengths. So to me, that's one of the biggest advantages in front of the room today, the ability to pair forward-looking investments with global learning. There we go. So reliability is, if there's one idea that I could anchor in the beginning of this conference, it really is that reliability is not a component outcome. It's a system outcome. And that matters because reliability does not come from one strong asset, one monitoring tool, or one software platform. It's built across infrastructure, rolling stock, electrification, signaling, operations, maintenance practices, and decision systems. When all of those pieces are aligned, the system performs more predictably. When they're not, even strong individual assets can underperform. So as we move through these technical sessions today and tomorrow, I would encourage you to not only think about each topic on its own, but how each one contributes to corridor-wide reliability, because that's really the right framing for the discussion. One reason I'm very optimistic about this phase is the mature freight systems have already shown us a great deal about what works. If you look across global heavy haul railways, there have been real progress in safety, infrastructure performance, rolling stock monitoring, predictive maintenance, and operational decision support. And that matters because progress doesn't have to stay theoretical. We already have lessons on how to validate engineering assumptions under sustained loading, how to use operational feedback to refine maintenance strategies, how to detect defects earlier, and how to use data to make better intervention decisions. So the opportunity here today is not to replicate other systems exactly. The opportunity is to move faster by drawing on what's already been tested, validated, and proved over time. And that's one of the real values of technical programs like this. It creates the starting point for turning global institutional knowledge into practical progress for India's freight rail network. And this, to me, is where my keynote directly connects to the technical agenda. The sessions that we're going to explore in the next few minutes are really not separate conversations. They're a part of the same reliability architecture. And for me, I feel like there's 5 major topics that we're going to explore, and together they're going to describe how corridor reliability is built. First, with reliability engineering, which is validating design assumptions under sustained heavy haul operations. And it matters because small design assumptions, if left untested, can become large operational constraints once a corridor is carrying traffic at scale. Second, wayside and rolling stock monitoring, detecting those defects early on and protecting your infrastructure. The value here is not only earlier detection, but it's also the ability to intervene before localized issues become broader service disruptions or higher cost failures. Next is the digital twins and predictive maintenance, converting data into corridor-level decision support. That's where information is becoming operationally useful, helping railways make better decisions about timing, prioritization, and resource allocation across the network. Then we have OHE and signal reliability, sustaining safe, high-capacity freight operations at scale. Because even when core assets are strong, inconsistency in electrification and signaling can cause performance issues and quickly erode corridor reliability and network confidence. And last, institutional learning. So translating that operational experience into standards, training, and repeatable practice. This is where workforce development becomes extremely important as you're translating knowledge from one generation of railroader to the next. It's what helps prevent organizations from relearning the same lessons repeatedly over time, and it helps turn individual experience into lasting system capability. So each of these topics that we're exploring today is going to matter on its own, but their full value comes when they're treated as a comprehensive system connecting parts to the same system. The one piece of advice that I have just from the experience that we've seen globally is that we have to choose technology for the network, not for the novelty. And this is where practical decision modeling becomes very important. Technology should be chosen based on the performance and the problem that it solves in every specific corridor. The problem might be safety reduction, safety risk reduction. It might be higher capacity, lower life cycle costs, better throughput, faster fault detection, improved intervention, or stronger protection of capital assets. But the starting point must always be the operational challenge, because from there, the next set of questions are going to follow. Is the technology a strong fit for the system? Is the organization ready to support it? Can it be validated under realistic conditions? Can it be integrated into maintenance and operations? And most importantly, does it create long-term value rather than just short-term interest? So the goal shouldn't be deploying more technology. The goal is to deploy the right technology. And this is where I bring MXV Rail into the conversation, because MXV Rail brings a long history of railway research, testing, performance validation. And that experience positions us well to support progress in system reliability, infrastructure performance, and data-driven decision-making. I shouldn't put so many Ds together. Our value is not only in developing or testing new technologies, it's really helping railways understand what's right for the specific operating environment, corridor by corridor, and how technology performs under those conditions and whether it really supports long-term network outcomes. So in other words, innovation on its own is not enough. The real value is when innovation is paired with validation and when validation is paired with disciplined decision-making. And that's how railways avoid investing in complexity that doesn't solve the real problems, that doesn't come up with the answers to those questions we asked earlier. And that's how we build confidence before deploying solutions at scale. The next few slides are going to give you an example or several examples of how MXV Rail has taken our overall experience and turned that into meaningful results across the globe. So I'll start with our example for the Facility for Accelerated Service Testing. I'm happy to report that this year we are celebrating our 50th anniversary of our Facility for Accelerated Service Testing, or FAST. And it's a place that's provided innovation, validation, and long-term performance come together in a real operating environment. At FAST, we're not just studying systems in theory. We're operating them under sustained high-tonnage conditions, and we're measuring how they actually perform over time. And globally, you get to benefit from all of the work that we do as a part of our industry research program that's subsidized by the North American industry through a lot of the publications that we put out and the conferences that we attend. I would highly encourage you to take a look at our website under the Knowledge Interchange. We have over 1,000 different articles that are available on all the various topics that will be covered today to talk about the underlying principles that they're supporting FAST. Programs like FAST that have helped support the widespread adoption of heavier axle loads, including 130 metric tons in North America, we've been providing evidence needed to move from concepts to implementation with confidence over time. We've also seen a lot of measurable improvements in asset performance based on this particular program. Over time, we've seen anywhere from 25 to 100% increases in rail life and a 5-fold increase in insulated joint life. And those are meaningful when you're managing large capital programs and one of your largest investments are in your track infrastructure. But to me, what matters even more is what makes things possible beyond any one technology. FAST is a place where we're continuously improving our specifications and standards. It creates an environment where systems can be tested, data can be validated, and operational learning can be translated into practical guidance for railroads across the globe. Last year, we were able to run more than 50 experiments on this small track that we have. We carried about 130 million tons of traffic and reached about 3.8 million tons in a single 24-hour period. So you can see that the pace at which we're collecting data is high. That information is getting back to suppliers and vendors so that they understand performance under extreme conditions and are able to translate that into meaningful changes and results for the industry. So the FAST example highlights some of the importance of testing and validation for technology under real operating conditions. But I think that there's another critical point that I wanted to point out in terms of the overall and longstanding success of any heavy haul railroad, and that's the role of standards and specifications. This is just one piece of what we do on behalf of the AAR is managing the specifications, but one thing with technology, it's always evolving. One of those cases is within the wheel impact load detectors, or WILDs. Over time, the technology behind WILD systems has continued to evolve. That we've used alternative detection approaches that have entered the market, and bringing those new capabilities and new technologies into the industry was proving somewhat difficult because of the standards and specifications that had been set 20 years ago. And so we were able to identify that there was a standards gap, work with these new technology vendors to update these specific standards so that implementation of new technology was more streamlined than it was before. And so as these gaps exist and how systems are calibrated and validated and deployed across industry networks, we're continually updating the standards and specifications that drive those. But these standards were also informed, I think it's important, by the critical research that happens at MXV Rail, looking at developing new technology or new methodologies to validate these new detectors is also important. So as you're exploring new technology and the implementation, making sure that you have standards to deploy these across your network in a consistent manner is extremely important as you're considering the operational impact of any single detector. Because standards and specifications are really what allow railways to deploy technology across networks with confidence. They help us ensure that systems are not only innovative, but they're also interoperable, comparable, and reliable in real-world applications. And the final step in that cycle that we did here was the validation testing in conjunction with our vendors and suppliers to help confirm that these new systems were actually performing in relation to and or better than the previous systems that were in place. So from full cycle innovation, research, standards, and validation, it's really what allows technology to mature in an efficient way and improve the operating environment overall. So I'm going to close by bringing all of these ideas together with a single slide that reflects the full system of what we've been talking about this morning and what we're going to see in the presentations that follow. On the left, you're going to see the foundation: disciplined engineering, thoughtful technology selection, integrative maintenance strategies, and collaboration. Those are not separate decisions. They're connected choices that shape how a network performs over time. And they're really what's going to determine life cycle outcomes. Because reliability is not something that you add later. It's something that you build from and in the beginning, and the decisions that you're making at every stage. In the middle is the global heavy haul rail learning, and that represents decades of experience in engineering reliability at scale. testing and validation, performance feedback, predictive diagnostics, and corridor-level decision support. That body of knowledge exists today, and that is why progress doesn't have to be slow. It can really be accelerated by leveraging the expertise that's known and that's been used and proven successful in other industries and other locations. But the key step is on the right, and that's the Indian application. The goal is not to copy what's been done somewhere else. The goal is really to take that technology or that idea and adapt it to the operating conditions that exist in India. Whether it be climate and maintenance realities, local priorities, network characteristics, and the strength of India's own engineering and innovation. That's really where long-term advantage is created. And if it's done well, the result is not just a larger freight network, it's a more dependable one. Easier to maintain, more predictable to operate, more efficient in its use of capital, and better positioned to deliver consistent performance over time. And to me, that's the real opportunity in front of this room today. Not simply to discuss the next generation of tools or technologies, but to help shape and share the shared approach to lifecycle reliability across engineering, maintenance, operations, and standards. Because the strongest systems are not built when each discipline is working in isolation. They're built when those disciplines are aligned early, informed by evidence, and committed to continuous learning as the network evolves. And that's where collaboration becomes essential. No single organization builds a high-performing system on its own. It requires experience, data, and expertise from organizations that have worked across different networks, operating environments, and technologies. MXV Rail is proud to be one of those partners, bringing research, testing, and performance validation to support informed decisions for India's railways. But just as important is the broader community of operators, suppliers, researchers, and technical experts represented in this room that are going to provide you with their specific applications following my discussion. Together, all of that collective expertise can help accelerate learning, reduce risk, and support long-term growth and resilience of India's freight rail network. And that's why gatherings like this matter, and why it's particularly important for me to be able to attend these events on an annual basis, because they create space to align ideas, challenge some of the assumptions we have, and connect technical expertise with long-standing system outcomes. If this seminar helps move that alignment forward, it will have done something very important. So for me, the opportunity ahead is very clear. We're here to leverage global outcomes, to apply them thoughtfully, to collaborate across expertise, and to build reliability in the system from day one. Because the next phase of freight rail is not just about expanding capacity. It's about building systems that perform consistently, efficiency, and reliably over decades. Thank you for your time this morning.
Thank you, Ms. Carey, for your insightful perspectives. And as you rightly mentioned, reliability is not something that we can add later. It is something that is built from the beginning. Thank you for sharing your perspectives, rich experience, and forward-looking vision that has set the tone, especially when we begin our technical sessions now. Ladies and gentlemen, as we begin with the first session, it is my privilege to introduce the moderator for this technical session on reliability engineering for high-intensity heavy haul operations. And this will be moderated by Shri Naresh Lalwani. He's an accomplished railway professional with nearly 4 decades of experience, an IRSC officer of the 1985 batch. He holds a bachelor's degree in civil engineering and then an executive MBA from IIM Indore. Before retiring as General Manager, Central Railway, he served in several key leadership roles, including Senior Deputy General Manager and Chief Vigilance Officer, Principal Chief Safety Officer and Divisional Railway Manager at Palakkad Division. Shri Lalwani has also made notable contributions to railway engineering and knowledge development. He convened the committee that revised the Indian Railway Track Machine Manual in 2018, authored a widely used book on track recording for Edison, and published technical papers on railway infrastructure. His experience spans major projects across diverse and challenging railway environments. May I please request Shri Naresh Lalwani to kindly please take over the proceedings and guide us through this session. Please join hands, ladies and gentlemen, as we welcome the moderator.
Thank you, Juhi. Good morning, distinguished guests, ladies and gentlemen. I welcome you to the technical session of this Internationl Heavy Haul Seminar 2026. And with me, Delhi weather also changed yesterday. So Delhi also welcomes you with the changed weather. So in all, in this seminar, because I am starting the session, so there are in all 5 technical sessions spread over 2 days, along with a panel discussion. So the 2 good things have happened to DFC in the recent past. One is that entire DFC Western corridor has been commissioned, Eastern was commissioned prior to that, and a new DFC corridor has been announced, East-West corridor. So these are the 2 good things which happened to DFC. So the overarching theme of this year's seminar is engineering reliability at scale, the next phase of heavy haul railways. It is a recognition that modern heavy haul railways can no longer rely solely on robust engineering design, but must increasingly integrate the maintenance strategy, operational learning, and data-driven decision-making into unified reality framework. So this first session, the technical session number 1, focuses on reliability engineering for high-intensity heavy haul operations. Across the world, the heavy haul railways are being required to carry ever-increasing tonnage while maintaining high levels of safety, availability, and asset performance. The challenge before all of us is to ensure that design assumptions, maintenance strategies, and life cycle expectations remain valid under a sustained high-intensity operations. We Indians are sticklers for value for money, so we look forward to the technologies which provide us value for money. The speakers in this session, 3 speakers are there. They will bring perspective from some of the world's most mature heavy haul environments and will help us explore how reliability can be engineered, validated, and continuously improved throughout the life of the corridor. So it is 11:42, our session is up to 13 hours, so around 78 minutes. So each speaker has 20 minutes, and there'll be, to maintain the discipline of the session, there will be a bell at 17 minutes, single bell, and 2 bells at 20 minutes at the end of the time. That is for the conduct of session. The delegates are encouraged to ask questions, so slips will be passed on. People will be circulating the slips, so whatever questions are there, you can write down your name and the questions and the speaker to which your questions are addressed, and just pass on, they will come to me. I'll request the speakers to answer the questions as much as possible. So we start the first paper today. The technical presentation is about the fundamental reliability components in heavy haul track, the rail fastening system. So as we have observed recently, the climate change, we have got hotter summers and colder winters, and which is increasing year by year. So buckling is one of the issues, which is a serious issue in this scenario. And in buckling, the track stability and the stability of the ballast, these are the 2 things which play a role. So this paper is about the track stability, and Ms. Nicole Witoff, she will be throwing our light. So I'll invite Nicole Witoff to start the paper. Thank you.
So thanks for the introduction and good morning. As we heard already and as emphasized from Mr. Kumar, safety for track is a key word, and also Carrie build up on that with the words, okay, you cannot look only in one component or in one parameter, you have always to see the track and the infrastructure as a whole. And that fits good in the prospect which we want to introduce for you today, because our speech is about how track stability can be increased with a particular focus on fastening system and evaluation methods of track buckling. So, my name is Nicole Wiethoff. I'm from Vossloh Fastening System. Just let me introduce briefly about fastening system, which is part of the Vossloh Group. We are based in Werdohl, in a small village in Germany, and this is since more than 130 years there. We are selling fastening systems from metro lines until heavy haul lines worldwide. But our aim is not only to focus on the selling of fastening system, it's more about understanding the track. So beside of fastening components, supplementary components, and actually also polymer sleepers and under-sleeper pads, we have also a bigger service as in-house simulation and having a big testing department. We are doing also on-track measurements and trainings, and that is, as I said, to really understand the track and the characteristic of track and how it behaves. So, track stability, why does it matter? As Mr. Lavani already mentioned, we're talking about global warming, we're talking about to bring more weight and more operation on the track, and especially considering the size of India, you have different environmental conditions from the north to the south, and somehow you have to tackle that. So also for the dedicated freight corridors, it's essential to have a stable and predictable infrastructure under consideration of the high axle loads which you applying to the track, the accumulating loads under different demanding operation conditions. You have steeps, you have sharp curves, you have high operation. And the track is not only just a plain track, maybe that would make the things much more simple. If you just consider the track, you have to calculate one line, but you have also, let's say, disturbing factors as turnouts, bridges, transition areas, which we have to consider in specific as well. Yeah, the buzzword global warming we had already. At the beginning, it was a little bit, does it impact us also as railway engineers? But seeing now what's happening in the track, the rail heat is increasing more and more. So yes, we have to consider also that. So for the design of railway lines, you need a risk-based approach and identifying also specific locations where you have to do maybe additional measures and cannot go just with a standardized layout. So track stability is one important parameter, since track buckling is often not so easy to detect. In the continuous welded rail section, you have track buckling if the track is under tension, or you have maybe the risk of rail braking if the rail is getting under stress. Rail braking is easy to detect, or more easy to detect by modern signaling, by modern detecting systems, but rail buckling appears sometimes suddenly and is not so easy to detect. So that is a high safety risk which you have to take into consideration. Where you have critical areas which you might not have in the first place on your mind is also long bridges, because long bridges are applying additional forces in the track, and therewith, by their expansion and breathing of the bridge, you have additional stresses in the standard track as well. Then cuttings, as we saw the introduction movie, you saw that the dedicated freight corridors are sometimes really going through cuttings where heat can build up and the wind cannot cool the rail down, and there you have additional risk for having high temperature appearance and therewith stresses in the rail. Switches and crossing, I mentioned already, the geometry, especially complex geometry, cell in this additional stress buildup. Narrow curves, steeps, all these parameters where trains are operating, accelerating, and bringing additional forces in the track are a risk. Transition zones, then that is all the things which you have in the environment. And the other point is then what you have as maintenance perspective or as quality. So for example, when you talk about ballast, it's very important for the track stability that you have a high quality of ballast. You have to avoid white spots, or also if you have mud sections, that is reducing your sleeper resistance, and there is also your track stability. So that is also an important point. So seeing about a kind of graph, what is selling all in the lateral track stability, that is on one hand the lateral sleeper resistance given by the sleeper, and also under sleeper pads are selling in this point to stabilize the sleeper in the ballast, to giving it more grip and more lateral stability, ballast quality of course. Then cross-section of the rails. Smaller rails will be more beneficial to reduce the stress, but on the other hand, you need some more heavy rails to accommodate your heavy axle loads. Then frame stiffness of the track grids. There also, especially the fastening system is one important key factor, which is given by the torsional resistance also more stability. The rail and the sleepers, of course, as well. Then the alignment, the general track alignment is also a point, degree of curvatures, cut-in sections in the track, and then lateral misalignments, of course. The maintenance regimes having also some impact because you want to avoid lateral misalignments, which are always the indication and the implementation of track buckling. We will concentrate today in our speech on the two parameters which we as fastening system supplier can influence and also evaluate it as a whole. That is, of course, the part for the increasing of the lateral sleeper resistance. With the sleeper resistance, you can improve by the weight, by the geometry, having very engineered geometry which are gripping in the ballast and therewith increasing the track stability, or the introducing of under-sleeper pads. Then you can, of course, introduce some additional equipment, especially in narrow curves like sleeper anchors. You can reduce the sleeper spacing, but as we heard, that is also an economical impact which you have to consider. And the quality of the ballast is really also a key important point. And not only the quality, it's also about the design. The shoulder, in-front shoulder design, if you increase that, that will also directly increase the lateral sleeper resistance. So then moving on to the track frame stiffness, and there we did high research on that. We did not consider the ballast because that we have already discussed in the increasing of lateral sleeper resistance point. We concentrated only on the fastening system, what is really beneficial for the track stability from the fastening point of view. Then, of course, the stiffness and geometry of the sleeper is also impacting the frame stiffness. For example, wooden sleepers having a lower impact as a heavy concrete sleeper. And yeah, using additional guardrails, you can also stabilize and interlink sleepers, and therewith also increasing the track frame stiffness. Things which can be done also very fast in existing lines is, for example, to lower the rail temperature in hot summers, to reduce also the compression force in the rail. That can be done by white coloring of the rail. That is introduced in some of the European countries for years, but it's very maintenance intensive and it is only lasting for a few months. So, of course, if you are in a very high stress situation, you can also cut the rails to reduce the stress and even reduce the length. But thinking about global warming, we have also to consider in certain locations to change the stress-free temperature, to maybe increase that temperature during welding. Increasing maintenance intervals is also getting more costly, so it's also something which you do not like to do, but that will help as well to reduce less vertical and lateral misalignments. And yeah, heat-related speed restriction, that is a problematic point in all railway lines, because that is influencing your timetables, and also it's very costly. So we thought about what we can do from the fastening system side. We did huge research together with Technical University Munich on the topic of frame stiffness. In the past, the moment of inertia, which is the key value for the frame stiffness, has been given as a standard value. So it has been considered under the calculation method of Meyer, which is the one which we are looking more inside, as one of the key parameter, but as a standard value. And then we thought about if that is really nowadays the truth, because this method has been established in 1873. And we did the following. We excluded the ballast in our point of view. We just focused on the track grid, means the rails, sleepers, and then we buried the sleeper friction-free. And then we simulated the force which has to be introduced to cause a misalignment. And with these empirical values which we get out of it, we realize that there is not a fixed factor to be used for this calculation of lateral track stability. The moment of inertia is really varying, depending on the fastening system which we are using, depending on the sleeper. And with that, you can do a much better and more precise calculation for the track stability. So we built on the Meyer energy method for calculating that, and learned that we can influence this calculation by different factors by the rail fastening systems. To prove that further in the lab, we went from the track grid to the single fastening point and did just a simple EN standardized test method for determination of torsional resistance. Using different fastening system out of the track grid measurements, it was very obvious that the guiding length of the fastening system influenced the torsional resistance, and also cells then directly in the moment of inertia. This, in combination with the contact points where the force is implemented in the rail foot by the tension clamps or clips, having a positive impact on the torsional resistance. In this sample, we compared shoulder fastening systems with the W30, and by having this bigger guiding surface and the difference in the implementation of the toe load in the rail foot, we could increase this torsional resistance by around 90%, and there was a direct positive impact in the track stability. In the first round, we calculated different fastening system configuration, different sleeper configuration by the method of Meyer. In this example, it's just a standard mainline fastening system, mainline track setup with a curve radius of around 400 meter and a speed of 100 kilometer per hour, assuming a rail temperature of 60 degrees. And then based on the Meyer energy method calculation, we compared wooden sleepers with baseplate fastening system, with concrete sleepers and different system configurations. There were two cases calculated. One case, just plain line. Therefore, the delta T0 has been calculated. And the second case is the 65 Kelvin line, which you see there in red. That is the case for the plain line, and the red line with the 95 Kelvin shows also if you have some interruption by bridges or hanging sleepers. Then you need already a much higher safety for the track stability and the value of delta T 0 by 95. So considering, let's say, old-fashioned track with wooden sleepers and baseplate systems, you will get, in this example, already in the risk of track buckling, even in the plain line. If you consider some impact by bridges or other configurations, you will have also some issues, some extreme issues. The heaviness of a concrete sleeper is supporting, of course, a lot, but also the fastening system. You can see if you use then a concrete sleeper with a W30 fastening system, you are safe in all this configuration. If you have then, let's say, a more engineered tension clamp like the M9 with a different shape and design, you can increase further. And there are specific measures also in the, by the angle guide plates with the longer guiding surface, which also buy in more. So beside of these very costly things which we saw before, like sleeper anchors or having more maintenance, you can also plan in advance to choose different fastening system in different critical situations. So these things like the method of Meyer or method of Poschillo or even doing structuralized FEM tools, you can do case by case. But as already said, we have to consider the track and the track alignment as a whole. So we thought there must be some more practical way to do it. And so we initiated, together with Technical University Munich, a tool which calculates the track stability much more comfortable. Additionally to the method of Meyer, we could include the engineering things which we have already learned about in the past. So we include things like mud spots, hanging sleepers in this tool. And with this tool, you can calculate then, or you can first of all put in your alignment completely, and then you can calculate point by point where you have the risk of buckling. So we call it the buckling safety margin, which you can calculate. And if it's going down to 0, you have definitely a risk of buckling. That is one opportunity. The other opportunity is you can calculate in advance which BSM you have with different curve radius and different system configuration, so that you have really a risk-based planning for your track alignment. You can use standard fastening systems in the standard long-term track, but for specific location, you should consider also specific measures like specific fastening systems or even additional measures. So altogether, that will help to understand the track better and to offer you more safety, track stability. So freight traffic impose extreme loads on the track, like high axle loads, high traffic density, and increasing cumulative loads over time. But modern fastening system solutions play a key role in safety guiding these heavy loads by increasing track frame stiffness and torsional resistance. They protect not only the rail, but the entire superstructure, including sleeper and ballast, against excessive deformation and damages. In practice, that means fewer geometry defects, longer service lifetimes for track components, and reduced maintenance interventions, and there is also a lower cost for maintenance. These improvements translate directly into higher availability and low life cycle costs and higher overall safety. Modern fastening system technologies combined with data-based calculation tools, like for example this Meyer++ method, offer therefore a powerful levers to increase your safety. I would like to thank you very much for your attention and pass over. Thanks.
Thank you, Ms. Nicole, for giving us a deep insight into the stability aspects of the track, along with the scientific basis of the calculations. And thank you for sticking the time also. So, second speaker of the session is Mr. Glenn Lawrence. He is from Voslowski Systems, Australia. As you all know, turnouts are among most heavily loaded components of the track, requires the most maintenance intensive assets on a heavy haul corridor. And Australia's heavy haul corridor is one of the most demanding proving grounds in the world for the heavy haul. So these remain one of the most critical and highly stressed assets on any railway. So in this, the paper which is being presented to you shortly, one is the use of new materials for less friction sliding chairs, which help us in a environment-friendly way to not to use the lubricating oil for the lubrication. Then secondly, how nice it is if you see the medical science advancing, some gadgets installed inside the body telling us what is happening to the body. So if something in the crossing telling us what is happening to the crossing, so that is also part of the paper. And the third thing in the turnout is how the switch takes the load, how the switch reduces the impact. So these important points are covered. So over to you, Mr. Glenn Orange. Thank you.
Okay, thank you for the introduction. I'd just also like to take the opportunity to thank Internationl Heavy Haul, Kari and her team, and Mr. Kumar for the DFCC for inviting me to speak at this presentation. Also, I'd like to thank the organisation for their hospitality and the opportunity to speak in such an incredible venue. Okay, let's see. Okay, yeah, this will be my topic for today. Heavy haul turnouts. My experience is mainly in Australia for heavy haul turnouts, but as you'll see through the presentation, it is particularly based around the super heavy haul as well. And these are the experiences that we can use in this 40-tonne axle load environment to be able to then use that same experience down to a different network and a different rail size and different environment. Okay, so heavy haul turnouts. Look, we designed them to meet the design and manufacture, which is what we do at Voslo, to meet the needs of heavy haul rail systems. VCSA, Voslo Switch Systems Australia, we're a designer and manufacturer, so we do both. And we supply heavy haul turnouts to the majority of the networks in Australia. So these ones, and they're generally 32 to 42 tonne axle loads, so they're quite heavy. Our biggest clients that we have in Australia are the likes of BHP, the big iron ore companies, BHP, Rio Tinto, FMG, as well as some of the coal mining companies, as ARTC. Sorry, the freight companies of ARTC and Horizon who get our coal to the port as well. So the top three, I've mentioned them there: BHP, Rio Tinto, and FMG. They run 38 to 42 tonne axle loads. So they're quite heavy environment. Okay, just a quick rundown of the presentation I'll be giving. What is heavy haul? Who uses heavy haul? Client needs, expectations, heavy haul geometries and configurations, turnout design, turnout manufacture, heavy haul turnouts, components, turnout installation, maintenance, future of heavy haul turnouts. Look, I could probably do a presentation on each of these topics, but unfortunately we don't have time in this forum. Okay, just very simply, look, this presentation is not over technical. I wanted to sort of try to keep the audience as much as I possibly can. So just to give an indication for those people that aren't particularly orientated about turnouts, how we actually come to say what is the tonnage and axle load. So any heavy haul network, or what we consider heavy haul, is anything over 28 tonnes. So this is what obviously the DFCC are looking at for their networks to come. So we have what we call medium heavy haul, which is 28 to 34 tonne axle load, which is probably what the Indian Railways are looking at in DFCC. And then we have what we determine as the super heavy haul, and that's around 35 to 42 tonne axle loads. The measure is quite a simple calculation. Basically, the gross tonnage of the wagon, the content of the wagon, divided by the axles, and you basically get what the tonnage is. So it can also be considered that, thank you, high volume networks can also be considered heavy haul, not because necessarily the high axle loads, but basically the volume of traffic that they're actually presenting and running on their networks. So just simply by the frequency of movements, you may have a reasonably low axle load, but with multiple and tremendous amount of movements, and you end up with a particularly large gross tonnage at the end of the year. So in Australia, probably most of our turnouts are what we consider heavy haul. So probably 70% of the turnouts we design and we manufacture would be above 30-tonne axle loads. So we do obviously traditional and conventional turnouts as well as some light rail, but this is probably the majority of our work is in heavy haul, hence the experience we have. Okay, just a bit of an understanding, a bit of geographical content here. So if you look at the map of Australia, I think most people probably recognise that. On the east coast, if you look at the east coast there, we have the likes of Queensland Rail and Horizon, and they're coal manufacturers. They run on a narrow gauge, which in Australia is 1067 millimetres, and they're around 30-tonne axle loads. The bottom right-hand side, we have New South Wales Hunter Valley, which is the ARTC coal network, and they run a standard gauge. On the bottom left of the state of Western Australia, we also have the Midwestern Arc Infrastructure networks, and they run some iron ore on 1435 gauge. But probably the particular interest to this forum would probably be the Northwest, which is like the BHP, Iron Ore, Rio Tinto, FMG, Roy Hill, and they're the guys that are running the 38 to 42 tonne axle loads in that region. This is a region we call the Pilbara, and that's pretty much where they're all dedicated heavy haul freight lines. So there's no mixed traffic on any of those lines. So we can actually design turnouts to suit specific wheel types, specific wagons, and specific axle loads. I was asked whether I should put a cricket analogy in this presentation. So probably this is the best opportunity. So if anybody, if particularly for our Indian teams, unfortunately our North American colleagues probably won't understand this cricket, but or some of the Europeans, I think, Nicole. But if we look at the top right-hand corner in Queensland, that is where the Brisbane Cricket Oval, also known as the Gabba, which I'm sure some of my Indian colleagues know. Down the bottom right, where I live, just below Sydney, is obviously the city of Melbourne, and that's the MCG, Melbourne Cricket Ground. On the left-hand side in Western Australia, we have Perth, and that is where the cricket ground known as the Wacker is. So I'm sure some of my Indian colleagues can understand a little bit of the geography now when we talk about this Australia. Okay. Back to the serious stuff, I suppose. What I'm supposed to be here for is talk about turnouts and heavy haul turnouts. What we focus on is we're very client-centric. So what we focus on is what our client needs in a heavy haul turnout. So basically, we need the ability to handle extremely heavy axle loads. We need long life cycle, component reliability, minimal maintenance, component interchangeability, maintenance access with minimal time frame to suit increasingly frequent train schedules. And of course, we need to provide technical support for our clients after we install and after these things, after manufacture, after installation. And these are requirements of all rail networks. However, when you consider heavy haul, the cost of production to the port versus the downtime ratio is more significant with heavy haul. So it's probably a little bit more important that we meet our clients' expectations with these. Geometry. Look, very little. Everyone probably knows what this is. It's just a turnout. Nothing exceptional. and they vary little from what we would call standard or conventional turnouts, not necessarily, or non-heavy haul turnouts, if you like. We have standard geometry, secant geometry, tangential geometry is fairly standard. The radius, the turnout angle, again, is pretty standard. The angles range generally from about 1 in 10 to 1 in 25 turnout angles, and varying radii up between probably around 300 to 1200 radius, depends on the speed of the network. Look, this is a very simple slide. Heavy haul geometry is very similar to non-heavy haul geometry, but what we need to consider more often is the impacts and forces, and particularly the lateral forces. The lateral forces, so hence the parts that actually carry the load are generally, we need a lot more consideration for. So this is very, very important, the components and materials we use. So of course, unless we start looking at significantly higher speeds for our heavy haul turnouts, but at this stage, I think it's volume rather than actual speed. Okay, next slide. Okay, turnout design features. We need to understand the client's requirements: axle load, speeds, interfacing gauge, wheel profiles, signalling considerations. So we need to select the appropriate components, and material must be significantly robust to be able to handle these load requirements. So we need to look at rail size, rail hardness, rail grade, full depth, switches, switch blades or tongues, some people refer them to, whether they're full depth, manganese tip, thick web, asymmetric, crossing types, swing nose crossings, monoblocks, RBMs, fabricated crossings, bearer types, concrete, timber, steel, composite, plating considerations, fastening system, resilient versus screwed, cast components, material selection, whether it could be cast steel, mild steel, manganese steel, other components we use in manufacturing of turnouts. Now, this list provides options for components, which will provide increased life cycle and maintenance reduction for turnouts. With every component and material selection, there is, of course, cost considerations. So what we need to understand is what the client needs for their specific network. So what we need to look at is we work closely with the client, understand their environment, and then we'll customise that turnout to suit their environment. We don't necessarily want to sell, or make or manufacture a Rolls-Royce, for example, when we can supply a Toyota, which will probably be adequate. And I think Kari touched on that earlier as well. Okay, manufacturing. Again, it's very similar to conventional or not much different to non-heavy haul turnouts. These days we're very, obviously our factories, our machinery has improved. We need to achieve a high level of tolerance and repeatable in manufacturing. And this is critical to ensure we provide a high quality product. We use 3D software, numerical control machines for manufacturing, provides high tolerance and repeatability. Again, very important. For fitting, we use jigs, ensure quality, consistency and replication of products, so we provide the same every time. So what our client gets, what they expect to get and what we expect to give them is exactly the same every time. And we've invested heavily in machinery, modern facilities to improve our output, safety, lead times, quality. Our design engineers, which we have I have quite a big team in Australia, they're trained to consider manufacturing efficiencies, safety, environment for manufacturing, installation and maintenance. So we look at all these issues when we design turnouts for every individual client. Okay, some of the components, fastenings, which Nicole has touched on before. I probably can't, I certainly can't go into the same level of detail as she did. She's certainly the expert in that area. But there are considerations for our turnouts, and they're a very, very important part of creating a turnout which is fit for purpose for the environment that we work in. So, yeah, I think I'll get through that one because I think there's other people talking about fastening systems that are much more qualified than I am. So heavy haul turnouts, the components we use, switchblades or tongues, as some of the Europeans, I'm not sure what they refer to in India of the switchblades. Again, it's a matter of selection. So whether we use asymmetric switch section, which is generally typical 60 E1A1 rail section, full depth manganese tip type switchblades, which is a typical ARIMA style switchblade, or what we commonly use now, and particularly the super heavy haul area, is thick web switch rail section, which is a 136 pound TW or thick rail section. Now these switchblades are key components for our turnout. So rail selection material are critical, along with the profile to suit each wheel type, and they must be able to hold robust to hold that vertical and as well as lateral loading. Crossings or frogs, generally in the super heavy haul, we would recommend the swing nose crossing. So the one on the left and the one on the far right are one's for the 40-tonne axle load, and the one on the right is for 32-tonne axle load. And these provide a typical wheel-rail interface, which is very, very smooth as compared to, say, the fixed nose crossings. So, of course, we also supply and produce monoblocks fixed crossings with welded legs with trimetallic welds, rail band manganese fixed nose crossings. And this is probably the most critical decision, I think, as far as turnout design heavy haul network, is the crossing type. Again, swing nose crossing is certainly my recommendation for a heavy haul, but obviously there's considerations when you look at a swing nose crossing. We have other considerations and cost considerations because they are slightly more expensive, plus you also have extra infrastructure required. So you'll need extra signalling considerations, particularly you'll need to provide another motor and obviously any other signalling detection considerations as well. But if you ask me about swing nose crossing, I'm a big fan. Although we are moving, we do have some very good fixed nose crossings, and we're doing a lot of work in that field, wheel rail interface, to improve those crossings as well, which I'll get to in a sec. Okay, installation. Installation, absolutely critical. Prior to installation, we always do a first of type in the factory to enable our clients to come and have a look at the turnout, make sure everything's correct, and they then make sure the workmanship, the quality is as expected. We also do factory acceptance testing as well in that area. The other thing we'll do is full installation manuals, which enables full construction from bearer layout to switch and tongue installation and signalling equipment setting. We also provide full inspection sheets, and this is carried out and recorded for commissioning purposes once it's in track to be commissioned. We also need to consider the installation. This is the part we supply is from the bearers to the top of the rail. 2 minutes? Bearers to the top of the rail, so we need to look at the substructure, or our clients certainly need to look at substructure, so we give the turnout a good opportunity to perform in its best way. And you'd be surprised how often I've gone out and track, which I do on a regular basis, go out and track and find that they actually don't have an installation manual and they haven't done some of the inspection stuff. So it's really important for our clients to do that. Maintenance, good maintenance, particularly early maintenance, absolutely vital to make sure your turnout increases its life. Early grinding, metal flow removal, it stabilises the turnout, stabilises the crossing, the switches, and you'll get a long life cycle if you do this early maintenance. Lubrication, moving parts, So absolutely critical, as I said. There are influences outside the turnout that there's some we can't control, but the maintainers need to look at that. Things like creation of mud holes, anything leading into the turnout, because the train will create its own dynamics leading into the turnout, which actually affects the turnout. Things like hunting, moving side to side. When it gets to the turnout, it continues that and can lead to problems within the turnout. Our current design on heavy haul turnouts, it's all pretty much always tangential geometry, generally swing nose crossings, thick red rail, factory machined profile to optimise the real rail interface, fully resilient fastening system, in-bearer rodding, so it enables tamping, automated tamping right through the turnout, use of frictionless slide chairs, which you mentioned earlier, to reduce the friction of the switchblade movement, and this fully eliminates the need for lubrication. Provision of rail braces, stronger steels, metals to make sure we get the longest life and best possible life cycle out of our turnouts. So I suppose one of the challenges of these features with the turnouts we have is any new technologies is to be able to introduce the new technologies into an existing footprint. So this may include the geometry of the turnout, it may include bearers, signals, etc. So when we do introduce new technologies, we have to be able to integrate that into our existing infrastructure. I spoke briefly about pre-profiling. I think I'm running out of time, so I'll just skip through this pretty quickly. Factory pre-profiling, we supply this to all our turnouts now, either canted or pre-profiled. We design the turnouts to enable no necessity to have to grind out and track. So when the turnouts go in, they're actually made to suit the client's wheel profile before it actually goes in track, and that can be done accurately within and there's a number of advantages to this, and pretty much all of our clients in Australia are taking up this opportunity. Another area that we are really strong on, and we've certainly encouraged this over the last few years. We also work quite closely with our local, with the university, with Monash IRT, in wheel rail interface and wheel rail interface studies. So to me, we do this on all of our designs now. So all new turnouts, this ensures a smooth and safe wheel transfer. So as well. Ensures strong performance and longevity of the turnout and turnout components. So when we conduct wheel transfer studies, we consider all the rail profiles as machined in the factory. So what we do, the studies can be done on basically, we get provided new wheels, need-in wheels, condemned wheels, and we can then determine what levels of safety are required for that and determine the absolute best wheel-rail interface transfer. Okay, I think this is about my final slide, so I'm going okay with time. Monitoring systems, studies, trials, innovations. We're currently advancing rapidly with this technology. We'll allow remote monitoring system to report condition without needing for site access. This data is collected from these systems and allows predictive maintenance to be incorporated into maintenance planning. So we get a lot of data. We get a lot of data from these systems. As you can see, this is a trial we've actually done. On the graphics on the right-hand side is our sensor, our smart turnout sensor that we've actually got a dozen of these in trial on our heavy haul network in the northwest. That sends a signal to what we call the gateway. The gateway then sends a signal to the cloud via the phone network, if you like, or whatever network's required by the operator. That signal is then sent to a database and a base point. So the maintenance operators and the maintenance people can actually see what's happening with the turnout. From that, we can determine a very simple traffic light system, if you like, to tell us what we need to do to those turnouts. So, for example, if we have a excessive vibration or we get a trend in deterioration of that turnout, that can be seen at a workstation, and we can manage, and we can also see how the good ones are running too, how the good turnouts, which may not necessarily be getting the traffic, they may not necessarily be having issues with deterioration. So we can actually really get smart about some of our maintenance practices, and this is particularly important in some of the areas, probably more so in Australia, because we have hundreds of kilometres between towns. So we can actually look at how the turnout's performing from the comfort of your office. So, and we're already seeing, even on the trials we're doing, we're also doing trials in non-heavy haul applications as well. But we're seeing these systems in place on heavy haul track. This technology, we're starting to understand more about this technology, and we can see how it can be absolutely hugely beneficial. I think there's probably going to be a few speakers as we continue through this seminar on this technology, and I can't see it going backwards. It's absolutely going to go forward, and I think it's a big movement and a very important movement in our industry, and obviously not just Australia but all over the world. So that concludes my presentation. Again, thank you again for the opportunity to speak, and I'll take any questions if needed.
Sorry. Thank you, Mr. Loren. I hope this digital monitoring techniques come to the Indian Railways. I am very keen about it. So we go to the last session of this, last paper of this session. So our final presentation of this session talks about the challenge every mature rail operator eventually faces, that how to raise the reliability and maintainability on the legacy infrastructure. And so I am happy to see in the paper that the improvements in the Pendrol technology, where they have reduced the number of components from 5 to 3 in a track system, in the fastening system, and it has been already been installed on 23 kilometers on NCR. A year back, I think some experience is also already there. So it will be interesting to see the paper which will be given by Mr. Jan Bag. And the paper is titled Improving Reliability and Maintenance of Heavy Haul Track Fastenings in Legacy Infrastructure, Applications of Pendrol RE Systems for Heavy Haul Railways. I hand over. The floor is yours, Mr. Bag.
Thank you. I'll echo the sentiments of the other speakers. It's a pleasure to be here, and proud to have been invited to come and speak on behalf of our company in front of this esteemed audience. Special thanks before I start to my colleague Priyank. So he did quite a lot of the work in preparing the paper and the presentation, so I was going to try and get him to speak as well, but he's a bit shy for that, so he's left that all to me. Just a little bit about Pendrol. Pendrol's been in track infrastructure since the early 1900s, continually innovating in the rail joining or welding space, which you can see there from the original aluminothermic welding process in 1902 through to the one-shot crucible, and more recently our I+Weld solution for holistic management of rail alignment and rail joining with a high level of automation. And not to discount our fastening systems work as well. So early work in resilient fastenings right through to the modern day. Not really the topic of this presentation, but I need to note the fully captive fast clip system developed to provide highest compatibility with mechanised and automated track construction and maintenance, as well as our resilient systems that are used for between sleepers and the formation in under sleeper pads and under ballast mats, complementing high reliability ballast to track installations by extending the life cycle and reducing maintenance operations. Pandrol is a global partner that's just around the corner, so it's a little bit hard to see on that map there, but we've got manufacturing and support operations strategically located across the world, which help to shorten your lead time for both product supply but also support. In India specifically, we've got facilities and teams who provide rail fastenings, resilient systems, AT welding and iron casting products and support. These facilities here in India are supported by our global network of product and manufacturing specialists with expertise across all network types from tramways through to heavy haul and all sorts of operating conditions. So we want to talk a little bit about the challenges of heavy haul and then we'll go on to talk a little bit about fastening system design and optimisation. So what we're seeing with heavy haul is increasingly high annual passing tonnages, so in excess of 300 million gross tonnes with up to 40 plus tonne axle loads like Glenn's already spoken about. This is coupled with very long trains, so 200 plus wagons up to 3 kilometres long, which generate all sorts of undesirable conditions in your track. So string lining, where the train is trying to straighten itself under the power that's applied to get it to move. High traction forces, so immense levels of motive power required to get these heavy loads moving, and that all goes straight into the rails and then into the sleepers and the fasteners. That translates into quite often high lateral loads and high wear of the components. So, and then probably the other thing which Glenn alluded to a little bit as well is that these heavy haul railways are quite often in very hostile environments in the middle of nowhere with a long distance between where people are. So then we go on to look at maintenance operations as it relates to heavy haul, and in particular the things that impact on that for heavy haul are that there is typically greater intervention frequency, so the higher axle loads and the more frequent trains mean that your components, including the rail, can wear out more quickly and require maintenance more often than regular railways. Labour costs, particularly we see in Australia, I'm not quite sure how it is elsewhere, but labour cost linked to the remoteness of where these railways are is quite often higher than in other places. In addition to that is the cost of getting things to and from the site, so because you've got to take it a long way from wherever it's made or purchased to get it to the location where you need to do the maintenance. There is a high opportunity cost for track closures to do maintenance. So for example, if we have a look at a typical iron ore train in Australia, considering the numbers that we had on the previous slide, and assuming that iron ore is roughly at about $100 a tonne at the moment, then each train that we see in the Pilbara has probably got about $3 million worth of product in it. So every one of those that you stop is going to impact on the financial outcomes of the business. So that's why there's quite often a challenge to try and get track closures for rail maintenance, and you know, they want to minimise those as much as they can. And the last is climate considerations. So typically, again, getting things from where they're made or where they're dug out of the ground to the places where they need to be traverses a lot of country where there's not a lot of people, and it's usually either very cold or very hot or can be very mountainous. So in terms of fastening system maintenance, we're going to consider a typical E-type fastening system and some of the activities that we would see undertaken on those fastening systems and in these networks. So re-railing is probably one of the more common ones, where worn rails are removed and replaced for new ones. Component replacement, so insulating components, the pads and the side post insulators, subject to wear through the continuous movement of the rail due to both thermal and vehicular forces, so they'll need replacement as well. And then rail stressing or re-stressing, more common with continuously welded rail these days, not directly associated necessarily with component replacement, but because of the previously discussed opportunity costs for maintenance activities, it's quite often it'll take the opportunity to do component replacement when rail stressing is undertaken. So a typical track maintenance process will start with the removal of clips. Typically, we see, and the numbers that are here are demonstrative of some networks, not all, but it's good for an example as to where we can locate opportunities for improvement. So removing clips would see typically 4 workers utilising either pan pullers or hammers, working on each side of both rails in the maintenance section. Next is to remove the rail using an excavator with a rail grab or a specialist rail manipulation machine. Replacing the pads, we would see 4 workers on this task, typically 2 taking the old pads out and cleaning the rail seat, and then another 2 workers placing new pads into position. Rail is then rethreaded using probably the same equipment that was used to take it out, and then placing the insulators and clips. So this is probably where the most labour intensive part of this operation is, taking 2 workers to manipulate the rail, another 2 to place the insulators into position, and then another 2 to install the clips. So as we'd said, this is probably a highlight of the location where we can look to make the most gains from making a change, trying to eliminate some of the labour that's required for this and then some of the time involved in that process. So how do we go about doing that? First thing, as the moderator had alluded to, is that we look at reducing the number of components in the assembly. So that gives us fewer items to handle, and also reduces the chance of lost components. So the way that these parts are normally distributed on the track in these operations is that you'll have a team go ahead and drop parts along the track at each sleeper ready to be installed when they're needed. Smaller components such as insulators can quite often get kicked into the ballast and lost as part of that process. So removing part of the process, so being able to take a whole section of that out will be able to reduce the manpower that's needed, and then improvements associated with the changes that we're talking about will improve durability of the parts, and also provide opportunities for future automation. So there is a typical exploded view of an E-type fastening system. So you'll see you've got a rail pad, single piece, 2 insulator components and 2 clips. So a total of 5 loose parts per rail seat. So what we looked at was ways that we could reconfigure that to retain all of the function of the existing fastening components, but reduce the number of components that were there. So a novel design of pad was developed, which incorporates part of the function of a side post insulator. So you'll see that white section there that's on the sides of the pad. That is the vertical post component of a standard side post insulator. And in conjunction with that, we looked at changing the way the pad was manufactured, adding a curved shape to that, which allows for easier stacking, so they cassette a little bit easier when they're manufactured and packed for transport. But the bigger benefits come when you're trying to put them on the sleeper. So they self-centre, you drop them on the sleeper and they locate between the shoulders by itself. Also provides a much larger target area for the rail threading operation. So in conjunction with the change to the pad design, we translated the integrated toe insulator design, which already existed on our fast clip system, onto E-clip. So there's a typical RE type clip that has a toe insulator And that's the other portion of the side post insulator that insulates the clip from the rail and provides the electrical isolation, also increases the life of the rail. So there are, as I note on the last dot point there, in particular applications we can look to optimise the clip material by using a smaller bar diameter and performing a manufacturing operation to increase the clamping force and the fatigue life, but that's suitable for some applications, not all. And so this is what we end up with. The system now has one rail pad which contains the co-moulded portions of the side post insulator and 2 clips with the toe insulator attached, so reduced from 5 to 3 in that rail seat assembly. And here's, hopefully if it works, a quick animation of how the change out of these components goes. So removal of the pre-existing clips, insulators, rail and the old rail pad, and then installation of the curved RE type pad, bring the rail into position, and then the weight of the rail actually flattens out the pad and locates it in the centre of the rail seat. And then we present the RE clips and install them. So a little bit about the improvements to durability. Standard E-type side post insulators, which in some markets are referred to as liners or isolators, or in Australia the track guys call them biscuits. They can undertake some fairly complex loadings, a combination of lateral, vertical and longitudinal loadings applied through the passage of traffic and through thermal variations in the rail. So by splitting the insulator into 2 components and attaching part to the pad and part to the clip, what we do is we isolate the functions that those insulators have to undertake, and this provides longer life for those components and less propensity for breakage. So as part of the development for this product, of course, we undertook some lab testing, complete suites of testing to both ARIMA and EN standard tests in our lab internally and in external labs. Feedback indicated that our actions to split the insulator did improve the performance of those parts in the testing, so we were happy to see that that's something that should potentially translate to good performance in track. So an important part of doing what we did was obviously to reduce the amount of labour and increase the efficiency of the maintenance process. So in the UK we undertook a bit of a time and motion study with a customer in a sort of an off-track location where they could control a lot of the other variables. It's probably a little bit difficult for you guys to see that on the screen, but in a traditional setting, distribution takes three workers and about sort of 2.5 minutes, and then installation of the clip, installation of the loose components and application of the clip takes 5 workers and nearly 5 minutes. So the change that this customer saw when we did this study with them to the RE system was a reduction in 1 worker and about 30 seconds in the distribution of components, and then reduction in another worker and probably nearly 2 minutes in the installation of the components and the clip insertion. So overall, the reduction is between sort of 45 to 60% in staffing and time in terms of standard E-clip system as opposed to the RE system. Following that, there's been a lot of track trials undertaken. So the photos that you'll see there, top left is a track location in the UK, the bottom is a location in Belgium. And we've also installed some components in Class 1s in the US on CSX and Canadian National. So monitoring in those locations is ongoing. Also, we've got a trial here locally in India. So there was a section of track on NCR that was retrofitted. So these sleepers were a standard Indian Railways type Mark III type fastening. And we worked with the NCR team to install the RE components on that 23-kilometre section of track. So that was done last year, and that is still in position and being monitored as we speak. So the local team have been getting out on track and observing behaviours for track gauge and also measuring tow load at intervals that they can. So fairly consistent performance in terms of the ability to retain track gauge, and then a fairly tight distribution on the tow load that they've measured in track there. So. And just to get towards the end of what I wanted to talk about, originally developed for Network Rail, this system has now seen a pretty significant uptake from a commercial perspective. So the graph there shows the steady increase in installation of the RE clips on the UK Network Rail network. As of the end of reporting at 2024, they were up to a total of 8 million clips installed. So they've obviously seen the benefits in the system in their maintenance and are keen to continue putting this product in track. So just to sum up, before I go off to questions, developments that we've done for this RE system have managed to reduce the components, increase the performance of the insulators in those assemblies, improved the rail threading operation, particularly removal of the rail alignment task that's required for standard E-type systems, and increased the installation productivity for maintenance operations. So I will thank you for your time and pass back to the moderator now for a wrap up.
Thank you, Mr. Justin. With this, we finished the speakers' presentations. So I got some questions. So I'll read out the questions. So I'll request the authors to please answer the questions. So first questions for Mr. Justin are yet to come. So questions for Ms. Nicole. The first question is from Praveen Kumar, MD DFCL. It's asked how the lateral resistance is being measured in the field. That is the first part of the question. How much percentage of lateral resistance is generally increased by this device?
Okay. The measurement on the track is generally done in that way that you loosen the fastening systems and then you put a hydraulic device on one end of the sleeper and then you just push it through until it moves, and then you measure the deflection and the force which you require, and thereby you can measure the lateral resistance in the track. It sounds quite simple, but it's a very extensive effort to remove the shoulder ballast and to push it, but especially for consideration of the lateral resistance of sleepers and mud spots, we did a lot of these tests. And for the increasing of the lateral stability by under sleeper pads, there is no simple or just one figure which you can say to that, because it depends on the bedding modulus, on the weight of the sleeper, on the ballast design. But in general, under European construction conditions, we would say that's around 20%, as said, depending on all these circumstances.
The second question, the name of the person is not there, but the question is safety margin, buckling versus fracture, vis-a-vis fastener's response to temperature change. So question is not very clear, but basically, again, talking about safety margin.
But and the answer is also very difficult in this way, because the safety margin depends also on the condition which you are focusing on. So we would be highly interested to try it with our tool and with our experience to give a more profound answer, but At the moment, it's not possible.
The next question is from Mr. Pankaj Saxena. The question is, in India, speeds on curve and transition curves are governed by the Kent deficiency and unbalanced lateral acceleration limits, where lateral track resistance is an important factor. Have any railways or research studies shown that improved fastening systems and high lateral track resistance can be used to permit or justify higher permissible speeds on curves?
We have some, or we are doing actually some trials with some railway operators, especially to prove also the validity of our tool. So somehow that is the same answer as to the question before. If we have the original conditions, we can see how the safety margin will come up with different fastening systems.
Okay. Next question is from Anup Agarwal, consultant from Tata Projects. Question is, are we using AI anywhere to predict likely locations of rail buckling or failure of any rail fastening?
So Tata is using AI? Or?
No. They are asking.
Ah, they're asking, okay.
Asking whether anywhere in the world they are using to predict the buckling.
Anywhere in the world. I do not know that, but what we know from our research is that you have to know many circumstances of the track, specific circumstances. So our experience with AI is that the input factors are not so widely that you can use it for a precise dedication. But if you use your alignment and give it to AI, they can at least tell you, okay, here's a bridge, here you should look more detailed in. But to rely only on these factors, I would be cautious at the moment.
Okay. The last question for you is, it's basically a question relating to rail. I don't know whether you'll be able to. Are rails designed for a particular climate zone? Example, cold climate, hot climate, or can a rail handle temperature from 5 degree to 70 degree?
What we know is that there are developments for different rail sections with thicker webs, but here you have to find a balance. As said in the presentation, for avoiding track buckling, you need smaller cross sections, but they cannot be so heavily loaded. So I think the balance is then really difficult to find.
Thank you, Nicole, for answering the questions. Questions for Glenn, Mr. Glenn. So first question from MD DFC, Mr. Praveen Kumar. Whether heavy haul tonnage is different for turnouts and mainline tracks in the context of heavy haul freight operations? That is the first part of the question.
First part of the question, okay.
Yeah.
Shall I answer that first, or?
And second part is, how do you measure the maintenance parameters for turnout geometry?
Okay, I'll answer the first question first. Look, no, what we try to do, the turnout should complement the main line. What we should be able to do is the main line, if at all possible, the turnout, we should look at the particular rail size, particular rail section, particular profile, track stability. All should align with the turnout itself to ensure continuous smooth operation of the track network. Sorry, what was the second part of that question?
Second part of the question is, how do you measure the maintenance parameters for turnout geometry in the field?
At this stage, we're not maintaining them, but what we do is we provide a set of installation tolerances. Our clients generally will provide the maintenance tolerances. So, and they are two very separate things, because when we provide a new turnout, the tolerances are very, very high. We understand that things move in the field, but from our perspective in Australia, currently, it is up to the maintainer to understand their network and understand what's safe working in their network.
Next question is from Anurag Yadav.
Your mic's not on.
Second question is from Anurag Yadav. What is the speed of loop line side for lead radii of 1200 meters?
Standard gauge would be 80 kilometres an hour, I think, off the top of my head. Broad gauge, because we used different Kent efficiency in the calculation, broad gauge would be generally probably slightly higher than that. So on a 1200 metre radius, on standard gauge, which we have in Australia, the maximum diverge speed is 80 kilometres an hour.
Second part of the question is, how is the wear at the nose handled?
Sorry,
how the wear on the nose is handled? Nose of the crossing.
Yep, so, yeah, how's it maintained? The nose, the crossing nose, the switches, generally we would do it by hand. Unfortunately, we don't have the machines. It's very difficult. The big track machines, even the turnout machines, and this is something that we miss quite a lot with our turnouts maintenance, because our maintenance, the grinding machines, with respect to my colleagues at Laram and some of the Spino and these guys, they're generally a little bit scared of doing the grinding around the nose of a crossing and the switchblade, and so they should be scared, because it's a very critical area and we don't want anybody to damage it too much. So basically we have experienced guys do it with a grinder.
Okay. Third part is how to handle the elongation in the switch rail from back of crossing to the tongue rail.
That's a very, very good question. And we get this question asked a lot. We get a lot of thermal differential movement between the switchblade and the stock rail, because the switchblade is basically a free end. It can move because there's nothing holding it down. If we have a good solid turnout with a good fastening system, we consider the stock rail section a stiff section or a rigid static section. But in temperatures, particularly what we get in Australia, we get variations of temperatures on the one network from -5 to +60 rail temperature. So we get a lot of that variation, and that variation between the switch and the stock can disrupt signalling, and we can get signal faults, and we lose detection. So what we use is what's called an anti-creep device, because we keep the switch and stock rail independent, but we use an anti-creep device. The anti-creep device is there basically as much as a monitor as it is actually a device to stop creep. So what it does is, and this is very clear in our manuals, that we say, okay, have a look at the anti-creep device, see how it's set in a particular environment, whether it's hot, whether it's cold, and that's what you actually need, more as a monitor to check track stress as much as an actual mechanical device to stop creep.
Third question is from Mr. Shiv Kumar, retired General Manager, NF Construction. In your presentation, you mentioned that heavy haul on any rail haulage above 20-ton axle load. According to IHHA, the rail network is officially classified as heavy haul operation if it meets two of the following benchmarks: axle load, train operation with static axle load of 25 ton or more. Could you confirm whether it's 28 or 25? Because on DFC, it's currently operating 25.
Exactly, and I'll take that on notice. Thank you for the comment. My experience and what we consider axle load it's subjective. It's subjective. When we consider heavy haul axle loads, I think you might have saw in my presentation, we don't necessarily consider volume to the volume of trains. When we consider axle load, we generally always think of what the actual load is. In Australia, our minerals, our coals are generally around 32 tonne axle load when we bring coal to the port. Iron ore is generally 38 to 42 tonne axle load. So thank you for the comment. I'll take it on board, but my experience is it's subjective. It's subjective.
The last question for you is, it is about, I think, more of our point machine. So one is, please give insight or any thought about back drive arrangement.
Generally, in Australia, the most common points machine in Australia is Siemens M23A, which is predominantly across Australia. We also have MCM91, which is a Vossloh machine. The back drive components, we've moved a little bit. We have a number of back drive component designs. We have a single back drive. We have what we call a pantograph back drive, which is two back drives operating simultaneously, which provides a push-pull system rather than a stress on particular stress on a single rod. And there's also a torsion type back drive, which is a rotating torsion, what we call a torsion back drive system.
This question, I forgot the name, I forgot to mention the name, Arjun Singh Tomar, GGM SNT. The next part of question is, does Oslo give supply of turnout with point machine pre-fitted?
It's generally part of our supply. In Europe, I think yes. I think they put, because they supply tilt wagons with the turnouts. I'm not sure. I don't think they actually put the machine on because it's a bit of a risk. We certainly, when we do our first of type and factory acceptance tests, we certainly put the points machine on it. But it's a fairly fragile piece of equipment, so we probably wouldn't, in normal circumstances, ship the full assembly. So obviously we need to take care of that piece of infrastructure so it doesn't get damaged. So generally it will go separately, or maybe on the same truck, but not attached.
And the last part of his question is insights about holes in the switches for point machine roddings.
Sorry?
Holes you make in the switches for point machine, that rod is fixed. So is there any impact on that?
We aim to reduce the amount of holes in switch and stock rail. Well, when we drill a hole on a piece of rail, it creates a weak point in the system. So we also, but it's necessary. It's necessary to have. Well, at this stage, it's necessary. There are also clamping systems, but the best way to connect the switch system, the switch machine, point machine, switch rodding is still through a drilled hole. Sometimes in the foot of the rail, sometimes through the web. But we're very, very careful on how we drill our holes. Make sure we chamfer these holes. Make sure we do things like cold bolt expansion when required. So we're very, very careful and very mindful, particularly in the heavy haul. A bolt hole is a weak point of the system. So we try to eliminate them as much as we can, and two, when we do drill the holes, we make sure we look after these holes. We make sure we put big chamfers on them. We make sure in many cases, we do what we call cold bolt expansion, and that actually assists with, reduces the amount of bolt hole cracks.
Thank you. Any more questions? I have no more questions. Question for Justin. Any questions? Anybody? Okay, so I thank the speakers and I hand over to Juhi for taking the program ahead.
Thank you very much. With this, we conclude this highly enriching technical session on reliability engineering for high-intensity heavy haul operations. Ladies and gentlemen, please join hands as we thank each of our presenters of the session. We have gained insights into the critical role that reliability plays in ensuring safe, efficient, and sustainable freight transportation. So, with this, may I take the opportunity of requesting MD DFCCIL, Shri Praveen Kumarji, to kindly please present tokens of appreciation and respect for each of our presenters for this session. We begin by presenting a token to Ms. Carrie Gonzalez. Serving as a symbol of national unity and pride, we present the Statue of Unity, along with a very special DFC memento. A round of applause for Ms. Carrie Gonzalez as she shared her perspectives with all of us. The Statue of Unity. We thank Ms. Nicole for presenting her thoughts and joining us in this session. We thank Ms. Nicole for presenting her thoughts and sharing with us her expertise. Thank you very much for your presentation. A round of applause for Ms. Nicole. We thank Mr. Glenn Lawrence for his sharings with us. Thank you very much for joining us in this session. We thank Mr. Justin after this. Thank you very much for joining us in this session. Tokens of appreciation and a way of saying thank you to the presenters. A DFC memento and a token symbolizing national unity and pride. We thank the moderator, Mr. Naresh Dalwani, for conducting this session. Thank you, Mr. Naresh, for moderating this session and keeping it well in time. Thank you very much, Praveen ji, for presenting these mementos. Ladies and gentlemen, with this we invite you for lunch. Lunch will be served in the same area where we had joined for our refreshments earlier this morning. And lunch for all the DFC officials, I repeat, lunch for all DFC officials is being served at level L1, which is one floor lower than this downstairs. Kindly please be back for the next session starting from 2 p.m. onwards. I would once again repeat, please join us right back at 2 p.m. for the subsequent technical session. And of course, lucky draws tomorrow evening will be waiting for all of you. So ladies and gentlemen, we'll be announcing some exciting gifts tomorrow evening, and let's see how many people get lucky tomorrow evening. Thank you. So be attentive and participative in all the sessions. Thank you. See you at 2 p.m. for the next technical session. वेदन अपने अपने स्थान पर बैठ जाएं। इस सेशन की अब हम शुरुआत करने जा रहे हैं। Ladies and gentlemen, welcome back after the sumptuous lunch break that all of us enjoyed. It is my privilege to introduce the moderator for the next session on wayside, rolling stock and track condition monitoring and interaction management. Shri Subodh Jain, a distinguished transportation expert with over 4 decades of experience, Shri Jain has served Indian Railways and its public sector undertakings in a wide range of engineering, planning and management roles. His illustrious career culminated in his appointment as Member Infrastructure, Railway Board, after serving as General Manager, Central Railways. A graduate in engineering, Shri Jain has been associated with several landmark infrastructure initiatives during his career. He played a significant role in the design and development of the Delhi Metro and was instrumental in introducing innovative track technologies that have contributed to enhancing the efficiency and reliability of railway infrastructure. Following his retirement from the Indian Railways, he has continued to contribute his expertise through national and international consultancy assignments, particularly in the fields of track and bridge design. He currently serves as an expert advisor to Hyderabad Airport Metro Limited. An accomplished academician as well, he has taught project management at Terry University, New Delhi, and continues to share his vast experience as a guest lecturer at IIT Gandhinagar. May I please now request Shri Subodh Jain to kindly take over the proceedings of the session and guide us through the session. May I please request you, sir, to begin.
Thank you for the nice words, and good afternoon and welcome back to all the delegates. In this post-lunch session, the topic is technically pretty heavy, so I seek alertness of the participants and the delegates. This session's topic is wayside, rolling stock and track condition monitoring and interaction management. Now, wayside, when we joined railways 50 years back, our wayside monitoring system was the gangman, there was a gatekeeper at the level crossing who used to communicate with the flag that it's okay. So there was an exchange between the train and the staff who is on the track, where they were interchanging the signals that you are okay, I am okay. Those things are no more there. The railways have become manpower efficient. We don't have level crossings. So we have, if something happens in the train, there is nobody to talk back. Particularly in the context of dedicated freight corridor, where the stations are far apart and there is no commercial angle, the wayside staff is totally non-existent. This is not the subject I am conversant with, because I have held my innings when we had a lot of manpower. But the younger people, they have no alternative. The wayside equipment and wayside monitoring is not a luxury. It is the necessity, and I hope that the technologists who are developing these techniques, they keep in mind that there should be a live communication also between the wayside equipment and instrumentation with the train operators and the loco pilots and guards. Nowadays, even guard is not there. We don't have this thing. So having said that, we have a very distinguished set of panelists here who you will enjoy listening to them, and I hope that I will be learning things which I need to know even at this age. Let me remind my presenters that the time allotted is 20 minutes, and there will be a first reminder after 17 minutes, and twin bell will be after 20 minutes. The question answer session normally will be at the end of the session, but in case of any pressing need, if somebody wants some immediate clarification, we will entertain that. So I will request the delegates to send across the questions to me. Our first presenter is Mr. Axel from Siemens. Siemens, we all know, they are authority on the railway signaling, and he will be throwing some light about what is going to be the future of the signaling, future of the data processing in this age of AI, which we hardly understand, but that is going to impact the way we operate, the way we conceive the things. So over to Mr. Axel. Thank you.
Okay, thank you very much. First of all, I have to say this is in 35 years of working with presentations, giving presentations in many instances, but this is the first time in this forum. I feel like a politician here. I don't know if I like it or not. Let's see in 20 minutes how I feel. I will try to stick to my 20 minutes, which is unusual for me. There are certain people in the room, they know. I have a very modern watch. It's the Internet of Things that will tell me. That tells me my pulse as well. So let's see if it stays in a safe region. I like what you just said, that 50 years ago it was all about manpower. Maybe in 50 years from now there is no manpower. Let's see, we are in the middle. And I would like to indicate what we think in Siemens, what the, for the next 10 years, the innovations will be. And I have to say, in this slot, it was actually supposed to be Hitachi. Thank you very much to my Hitachi colleague. He took over the slot tomorrow. And so I don't really fit into the overall topic, but I will try to make it fit to a degree. Siemens thinks in terms of innovation in parallel to implementing projects. And the title of the range of systems, which is the umbrella for our, let's say, innovations, it's called Mobility X. It's not like the X-Men or so, it's Mobility X. And first of all, I hope that the slides will work in this format, because they are designed for widescreen, and it's squeezed, and so that everyone can see my picture. Let's see how it works. If you're going to the next slide and this doesn't work, maybe you can just squeeze me out and give the screen to the slide. But let's see. Please go to the, oh, sorry. Normally I'm used that someone else is doing the trick for me here. Works. Yeah. The title of this was actually giving me the logic for the agenda. So talking about digital twins, then going to the maintenance of things, innovations in the field of maintenance, predictive maintenance, and so on. And then continuing a little bit to signaling, because I'm a signaling engineer, so I have to give you a few minutes of signaling. If you want it or not, it will come. And there is a video coming, but I'm not exactly sure if it will work. Before we go to the video, just, yeah, that's what I was afraid of. It looks very squeezed, but okay, it's still doable. In our understanding of the mobility world, there are two distinct parts. One is non-safety, one is safety. So on the right-hand side, you see the safety part. It's basically what we do in signaling under the umbrella of innovation. And on the left side is the non-safety part. And that is actually the, in my view, very powerful part. That's where it ties in with what you were saying earlier. More capacity, more reliability, overall, using the network to its best performance. And there is a tool chain in Siemens under this an X title, which we call Accelerator at Mobility. And the idea is to have a platform. So my senior managers in Siemens always use, let's say, the App Store as an example. And they call it APIs, application programming interfaces, linking every app together. A few years back, I was giving a presentation here in Delhi in a different format, and we were just inaugurating this App Store. And so with the idea that the industry can join hands and everyone can actually upload their, let's say, their software tools there, so that in the end it creates a world of, let's say, different ideas coming together on the same platform. And okay, yes, we are from Siemens, this is our platform, and but nevertheless, the idea is to make it open via these API interfaces. And that has actually worked so far. Siemens has a collaboration with NVIDIA and with other strong players to bring this further. And under this accelerator at Mobility, there is this tool chain, let's say, for making the overall railway system more powerful. I will come to this a bit later. And I'm not talking about signaling right now, it comes in a few slides. So, okay, the first topic that was on the agenda is about digital twins. And as I only have 20 minutes, and I'm sure it will not take long, there will be the bell ringing here, I try to keep it short. I'm actually very fond of this idea of a digital twin. Okay, we had this slide in Siemens, and it's actually the same guy, but I wanted actually that this, one of the guys looks a bit more digital, but I failed there. Obviously the idea is to link the real world and the digital world. And we are doing that now big time. And Siemens Mobility is actually the smallest part of the company. Industrial part is much bigger, and their digital twins are all over the place. Whole big factories are digitized. They are serving as the model for mobility as well, to basically put everything that has to be real or is already real into software, so that software can help to modify, to understand the limits of infrastructure, to see bottlenecks, to, before money is actually spent for pouring concrete, it can be evaluated if everything is actually designed properly. So now a video is supposed to come, but I am not sure. If it is not coming, I have 2 more minutes to talk. But it's very small, and I can't make it bigger. I'm sorry. Okay, the idea of this video was to link the different phases of the railway system in principle. You have the construction phase, you have the, let's say, the operational phase, and by putting everything into the digital twin, it allows during construction to ensure that the system is designed for the future capacity, for the future desired operation, and when the system is in operation, it can still be used, the same database, to make sure that the operational scenarios are available free of conflicts and so on. So it's a living environment that can serve from construction through operational life, through maintenance, and that's a big, in my view, advantage of digital twins. Okay, this slide is too much detail. Just a quick repetition. The different phases of life of a railway. I have to say I'm coming more from a passenger background with these slides, yeah? But they work equally well in freight. There is the operational side of the railway life, there's the construction side of railway life, there's the maintenance side of railway life. And by having this digital twin available, it will allow to simulate every stage of the railway life cycle. So, jumping to diagnostics, obviously in my presentation is a bit different to what the previous presentations were about. They were focusing on specific products. Today, as I didn't want to give you an overview about our typical signaling systems, I'm staying a bit on the surface of things to outline what is possible instead of going deep into how it works. And but for every one of these topics, we have obviously hundreds of slides, and we can discuss in great detail, but not today. So the intention is to give you an overview. And under this title of Railigent, Railigent is the Siemens name for intelligent rail, and under this title there is a suite of specific tools, and they are designed around the whole railway world: rolling stock, electrification, infrastructure, signaling. All of these things are covered in a tool chain that allows to consistently monitor what's happening. With, let's say, data information from sensors, with connectivity between all assets, and intelligent software that analyzes continuously the status of the systems. And there was the question of AI before. AI is, okay, for me, not the ultimate answer, but obviously it speeds things up. So this is a big move in Siemens now to include, let's say, additional software routines to make the diagnostics more powerful, faster, come up with self-learning, basically over time, a scenario that happens every day in the same way, and on day 10 it is different. The system will figure this out and make informed decisions. And our Railigent toolchain includes a range of, let's say, subsystems from, let's say, diagnostics tools via, let's say, apps that allow the staff to go on site for being guided where things are to be corrected, and get already the correct spare parts, and if they go on site, they get a manual with them for fast correction of problems. So there is a 360-degree circle of tools that work together to keep the railway operational. And that's not just for, let's say, one part of the system, that includes everything. Siemens is a turnkey supplier. We have electrification, we have signaling, we have rolling stock, and basically this tool chain is available for everything. So now coming to, I don't know how I'm doing time-wise. Good. Coming to actually my real passion, signaling, and there again the innovation is massive that is coming there. But signaling has, let's say, the disadvantage that somehow everything is following standardization. So somehow no company can just race ahead and create totally new systems without an alignment with the open global railway community and with, so that somehow everything is consistent, because there has to be, let's say, an evolution that allows interoperability and long-term planning. And here, this is just an example. In today's signaling systems, it's all about, on the left-hand side, about in a copper cable and decentralized architecture, especially in India. It is to this day still quite normal that you have interlocks in every train station, copper cable to wire the outdoor elements. But at least on a global level, centralization is very, very prevalent, and the centralization has several, let's say, targets, not just for the sake of centralization. It is avoiding copper cable theft is a big issue. Then, let's say, diagnostics in central locations is much easier than have this distributed across the country. And this picture in the middle is what is reality today. You have across railway networks your distributed field elements, and they are connected via IP connectivity to more central locations, and there you still have the traditional interlocking environment. But the next step, and this is what's becoming real now, is the going away from traditional signaling systems into data centers. And we call it cloud-based signaling, but it is cloud-based, but in a private cloud. And these rail data centers, they are very different to anything that has existed before. You are putting all the features of the traditional signaling system, interlockings, radio block centers from ATP or CBTC control systems, train management systems, CTCs, everything goes into the same cloud. And this allows to integrate these systems, which was never possible to that degree before. So the integration of the head layers of all these sub-signaling systems into a data center will be a game changer. And the connectivity to the outdoor elements is a big follows a big standardization push in the global railway market under the title of U-Links. Okay, global and U doesn't really fit. U comes from Europe, but this is a big debate. The European technology which starts with an E, I always feel this is a little bit of a stumbling block. It should start with a G for global, or sometimes we are coming up with competitions what the E could stand for, and then we are saying, okay, E stands for everybody. So, because there are customers who are saying, this is ETCS, I don't want it. And this is U-Links, I don't want it. And in India, I remember one presentation, there was one particular person sitting in the audience shouting, I don't want ETCS, I want ITCS. Okay, so I said, it's renamed now, it's ITCS. So in the end, but this, never mind, the true intention is not to make it European, the true intent is to define standards that are very useful, and the global community, so, yeah, okay, this is number 18, so I have 1 more minute. And that's my last slide anyhow. Yeah. So, actually I timed it quite well, honestly. And so I would like to make this plea that in the future, this promise that the innovations coming in the railway world across the technical fields, and we are hearing this here today from, let's say, from fasteners, where diagnostics, this is coming from other parts, advanced diagnostics of turnouts, where, let's say, advanced diagnostics of all the technical systems. These things will come together. And by putting them together, the chances to have a railway system that is efficient, energy efficient, throughput efficient, allows to utilize the investment with the best capacity, has lowest life cycle cost, and will be, my favorite word is demand responsive, will allow you to tailor your operation in a demand responsive way by binding everything together with, let's say, digital means. This is coming, and we would like to be a part of it. Thank you.
Thank you, Mr. Axel, for the nice thought-provoking presentation. Let us hope that digital twin is not far smarter than the original one. So, but the thing is that things are going to change. It won't remain the same, whatever we may wish. Our next presenter is Mr. Jackie from the ENSCO Rail, and his topic is Transforming Rail Inspection into Actionable Intelligence. Practical lessons from North American heavy haul operations using integrated autonomous inspection and analytics. Post-World War, the railways did develop from the Europe, but post-Second World War, North American railroads have brought in the concept of bringing down the unit cost of transportation. And in that journey, this concept of heavy haul and most modern techniques to bring down the manpower and make the things efficient they have taken it to a different level. Let us hope that we learn something very important from Mr. Jackie's presentation. Over to Mr. Jackie.
Thank you very much.
Yeah.
No pressure with that comment. I hope to learn something. I do appreciate it. My slides has also been created to be a little bit wider, so if at any time we feel that I need to ensure that we widen it up, just let me, or let the team there at the back know. I want to start off to say thank you to DFCCIL for the invitation and allowing me to speak and share with you some of our experiences in North America. You know, over the last couple of years, we have seen that heavy haul railways are moving from periodic inspection towards a continuous infrastructure awareness and engineering intelligence. And I hope that we can share with you some practical lessons, specifically from what we've learned in North America with regards to heavy haul operations in transforming rail inspections more to actionable intelligence to do daily decision making. Throughout this presentation, we'll look at many aspects. You know, I'll talk about autonomous inspection technologies, how things are changing in the way of how we collect, integrate, and use infrastructure condition in general. But before we start, I think the real question is for us to understand what is driving this change. I think if we understand what is driving the change, that will help us to really determine how to move forward. So with that, I'll start with the real pressures of high-capacity freight railroads. You know, from a high-level perspective, railways are being asked to move more traffic, operate longer trains and heavier trains, higher axle loads. We are expected to maintain our network availability better than ever before. And all of this we need to do while there is expectations that maintenance windows are limited and the time available to inspect and maintain infrastructure just continues to shrink. So this is really a challenge for us as an industry, and I do believe what we will see is opportunities to access and assess the infrastructure are becoming really increasingly limited, and it really raised the question, how do we ensure we have infrastructure condition visibility and awareness in an environment where we really have the not really availability to inspect, and how that becomes a challenge. So to put this simply, periodic inspections is no longer good enough within this type of environment. So why is periodic inspection not really good enough anymore? Well, if you think about it, periodic visibility provides us a lot of good information, but it only happens at specific points in time. So as the train volumes increases, the train length is becoming longer, our axle loads is increasing. As you can see that representation of that line, they're starting to develop a visibility gap and limited awareness as we move over time. So if we only inspect in those 3 specific inspection snapshots over time at these higher rates and higher axle loads and higher volumes, the infrastructure is changing, and we will be in a position where we might miss what is really happening with the condition within that period. Therefore, the result is really the infrastructure changes and occur before the next scheduled inspection. And I would say, if you think about that, the objective for us is to start creating continuous condition visibility and infrastructure awareness to move forward. There you go. So if we look at where we're moving from these days and where I think things are moving, traditional models were manual inspections. There was very dedicated vehicle inspections with periodic snapshots. But what we see in North America is we need to change how we are handling inspections moving forward. It is known that the infrastructure conditions are changing, and continuous monitoring provides continuous visibility. So what we've seen in North America is a big drive to move inspection sensors onto in-service revenue trains to have continuous monitoring, and then actually help us to really have continuous, almost near real-time visibility of the condition. What's really important, and what we've learned from this experience, is when visibility and awareness are as we create more visibility and infrastructure health awareness, it enables the railroads to really understand what's going on and to make faster decisions. So when visibility and awareness are combined, we really get into infrastructure intelligence to make faster, better decisions in a shorter period of time. So what information is really required? Well, there's a lot of different options, and I'm not going to try and market all these different inspections. I'm just going to touch on a couple of them. But we can look at vehicle track interaction monitoring, where we really measure how the train responds to the infrastructure. We can look at track geometry measurements, where we really measure the measurement or the physical measurement of the track itself. We can look at rail surface condition, and we can look at track component condition. Some of the earlier discussions were focused on fasteners, ties. All of these type of elements is used to really, and are important individual systems that really combine, provide you with some visibility. But I think that these individual systems alone, if you put them together, you really provide continuous infrastructure visibility and asset health awareness. So I'm sure then if you think about this, the question is, okay, how do we do this? How do we create an environment where we can have continuous monitoring of these type of assets? And that brings us to what have been a huge drive over the past, I would say, decade, maybe a little bit more, in North America, where we have changed the way of doing measurements, moving away from dedicated manned vehicle inspections to more autonomous inspections. Here's just a couple of examples in North America where there is a track geometry, there's on locomotives directly, and then there's also environments where they've developed boxcars where we put these technologies on a boxcar. But the most important part of this whole thing is that these situations or these situations of having these systems on the trains that's already operating actually enable us to do condition monitoring, not as we are doing a new, or as a train, as a new, taking up a train schedule. It is part of the existing trains that is actually operating, helping the industry to ensure that we do more with less. That's really what we're trying to achieve. If we look at the industry, how things have changed in the traditional model to the autonomous model, this is not, I think this is not a theoretical experience anymore. We are doing it as we are sitting here today. So I just want to share some numbers that might give you an idea of what's happening worldwide. Predominantly, some of these numbers is North America. But if you look at it at the moment, since 2020, we have measured more than 12 million miles of track autonomous track geometry. We have measured more than 50 million miles of vehicle track interaction conditions. There's more than 42, currently there's more than 42 autonomous track geometry measurement systems worldwide. As we sit here today, I'm aware of about another 20 that is deployed or will be deployed within the next 12 months. And there is about 550 vehicle track interaction monitoring systems worldwide. This is not just North America. This is really starting to be a thing for heavy haul throughout the industry or throughout the world. And we see this in Australia, we see this in Brazil, and we see this in North America. I really think that what we see here is that the industry is changing from manned inspections to continuous autonomous measurements to provide condition visibility. A question that I think comes up is, okay, great, so we have these technologies, are we just going to measure more? And I don't think that is the answer. The answer is for surely not the idea to measure more because we can measure more. The question is rather, how are we going to take these large volumes of data and convert it into information and ensuring that we can generate engineering intelligence? So, in my opinion, the objective is not to have more data. The objective is really to make faster decisions. And with that mindset, I think the question is probably, does this approach and going through this approach of having continuous monitoring, data going through a process of ensuring we can make faster decisions, does that really have an improvement on operational outcomes? And that brings me to share some of the results that we have seen over the past couple of years, I would say the past 5 years within North America. In general, what we find is that inspection frequency increased about 15 times on average for these freight operators, resulting in significant network visibility. we have seen a reduction, and this is really part of the message earlier of making decisions faster, is we've seen a reduction of about 90% in terms of detection and reporting of those defects or those challenges. One Class 1 has measured more than 5 million miles of track in a period of 5 years, really providing them an enormous amount of visibility and enormous amount of data. And another Class 1 in North America saw a reduction of about 70% of their track geometry related derailments, purely due to the fact of more frequent measurements, having more visibility and condition awareness of what's going on. The next slide, what I would like to do here is to just present how the deployment of or adoption of technology over the years had an enormous impact on the risk reduction within North America. These data sets is coming from the FRA. What I'm presenting here is there's a couple of vertical lines, that's just different times over a different period of time, the adoption of certain technologies. On the left-hand side, what you will see is manned vehicle track geometry mileage per year, and the blue graphs, the blue bars is basically autonomous, in other words, no manned operation. And you can see that since that autonomous technology deployment took effect and really were adopted by the industry, it had an enormous increase of the amount of track visibility or frequency and amount of coverage that was obtained to do these inspections. And that, while you look at the right side, is the track geometry defects that resulted in derailments in the United States of America over the same period of time. So what you really can see is there is a direct relation between the increase in coverage and the reduction of derailments over time due to these abilities to have more visibility of our infrastructure condition. I think part of what we want to share here is the lessons we've learned through this journey. And there's 5 high levels or pillars that really have been part of our lessons learned. And there's probably more, but these were the main pillars that we've seen. So what we've seen is that integration matters more than the individual systems. We've seen that inspection frequency provides enormous amount of visibility, and with that there's a change in how you have in typically maintenance strategies and how you implement those maintenance strategies. Just as important is that the sensors is important, the systems is important, but the analytics is just as important as the sensors. Workflow is becoming a major part of a success story in this environment. Without that workflow integration, you will have challenges to do those fast-making decisions. And last but not least is in environments like this, when we put sensors on trains that is actually part of revenue service, the reliability and maintainability is just becoming a more important matter than historically. So you should ask yourself, or I'm asking myself, how does these lessons really are relevant to yourselves today and to the rest of the world? And I think the simple answer to that is this is relevant to anyone that is within the heavy haul, high capacity freight rail corridors. We've got the same challenges. We don't have to copy each other. We don't have to reproduce exactly the same things in different areas of the world. But we definitely can learn from each other. And if you think about it, I believe that it's pretty clear that more traffic is happening daily, and we have less time to do our maintenance, and there's a greater need for infrastructure visibility. As the technology creates visibility and inspection frequency and operational processes create the value, I think that you will see that there is a benefit of moving into a continuous infrastructure visibility condition monitoring environment. So what's happening, or what do I expect is going to be the future? Well, I don't think it will be a surprise for you to see that, you know, I would say we would see continuous infrastructure awareness as the future. We will see integrated condition intelligence, and from there we would be able to do predictive infrastructure management. I do believe, and it's in my opinion, that the future of rail infrastructure management is not really periodic inspections anymore. It is continuous operational intelligence. And with that, I really thank you for your time and hopefully gave you extra couple of minutes. Thank you very much.
Thank you, Mr. Jackie, for the nice thing. 70% reduction in the derailments is a dream for any infrastructure operator. And as you said, that merely instrumentation is not enough unless it is properly integrated in the system, and analytics is very important. We hope that this is going to be the order of the day for the infrastructure operators and maintainers. Our next speaker is Ms. Emily, co-founder of One Big Circle, the UK rail technology company behind AIVR, an award-winning AI-powered video and multi-sensor inspection platform now deployed across the vast majority of the UK mainline network. The subject is one of the direct relevance to everyone in the room in service infrastructure monitoring for heavy haul here in India, using trains already revenue service as the inspection fleet. Please welcome Ms. Emily.
Thank you. Thank you so much, and thank you to the conference for your invitation to join you today and for your hospitality. I hope with our speech, which I think without any previous preparation should be quite complementary to Jackie's speech, it should hopefully support the words that Ms. Carrie Gonzalez addressed at the start about really taking lessons learned from other technologies deployed in other environments and how you can use them to your best advantage. And I hope this supports the addresses made in the morning as well. So there's a quick rundown of the contents. And as I say, I think it's going to be quite complementary to Jackie's work on the power of in-service monitoring. Just a brief introduction just to build on there. We're proud to be representing the UK here at this conference. I'm one of the co-founders of our company, One Big Circle, and we've been delivering intelligent video and AI solutions in the UK rail industry for a number of years now. Quite recent in rail history, only about 6 years in UK rail, and more recently internationally as well. We're a team of hardware and software engineers, and a couple of conversations I've had recently over the last 2 days of being in Delhi is how the importance there is of hardware and software teams understanding each other's challenges and opportunities as well, with the ability to try and create integrated, holistic solutions. And I'm proud to say we're an award-winning SME team from a small to medium enterprise from the UK. So I thought I'd begin with a case study from the UK. For those of you that may or may not be familiar, they have what's called the yellow banana in the UK, or the flying banana, just because it's long and yellow and travels around very quickly. And that's their NMT, their new measurement train. Over the last decade, the NMT is slightly older actually, it's now becoming obsolete, but over the last couple of decades, this has been one of their, what's been in their sort of toolkit of being able to monitor the environment, a dedicated 9-car train that travels around the network and captures video data. Very advanced at its time, but very resource heavy, and obviously requiring its own scheduled train pattern to be able to deliver the UK. Over the last 10 years, they've quite rapidly evolved what they do with their infrastructure monitoring. And this is one of their early stage innovations, where they moved a lot of that monitoring equipment onto these smaller 153s. So these are single carriage trains that actually were due for the scrap heap, but were rescued in time to have some new technologies put aboard them. You can see them at the front there, the yellow boxes that are hanging off the front. And these were tested around the UK environment to capture video data and sensor data and make it, very importantly, automatically available online. These proved successful, and more recently they have polished them up, painted them blue, not yellow, and the number of these now travel around the UK network capturing video data. The reason they do that is for infrastructure monitoring, and again, hopefully this chimes well with the addresses this morning. It enables the earlier intervention, as we've been discussing, delivers cost effectiveness. Hugely importantly, it increases safety both for the railway workers and for the passengers. It accelerates targeted maintenance, improves operational performance, and extends asset life. So all the things that every network in the globe wants to be achieving, and reduces that service disruption. We've recently made a partnership with LRAM, our friends here that are also presenting, and the effective rail grinding, I'm trying to bring two subjects together, is just such an example of that maintenance which helps meet those challenges and objectives. Many of you are familiar with the fact that pre-grind surveys are captured from rail inspection vehicles, again collecting high-quality railhead conditions to create grind plans. And they create those rail surface scoring process as well, so that they can ensure those grind plans target the correct treatment to the relevant defect condition. Now, the next slide is going to make sense why these two subjects have come in close succession. Both of these concepts have similar data capture constraints. Methodology of the RIVs face similar as to UK infrastructure monitoring. Let's wait for the next. There are limitations on the distance they can cover. There's reliance on the scheduling access. There are remote and challenging environments through which they travel. And then there's the physical data transfer and limited access to that data by particular users as well. So data is much more siloed and only used for specific reasons, much more difficult to access. And we know that that data is valuable to the organisation in a much wider context. So our topic today is how to talk about how IM data and RIV data is ready to evolve and how that can be applied to the wider heavy haul industry as well. The advent of cloud computing, edge processing and artificial intelligence is what's reshaping what is possible. And there's a little schematic there of what our AVA system does, which essentially has sensors on board trains, integrates with sensors that are already on board, or we install what's required ourselves, ships that video data to the cloud, makes it hugely accessible. In the UK alone, we have over 12, in fact the number's gone up since then from 11,000, we have over 12,000 users from multiple disciplines accessing that data on a daily basis to derive from that the information they need about the areas that they're responsible, be that a certain discipline or a certain location. And then the machine learning models there then feed back into the whole system and really help refine what's captured from the trains. So there's technology required to meet this challenge. I'm going to talk a little bit about AVA Focus, which is one of the systems, a core part of our monitoring system, which captures processes and delivers the high-quality visual data that's needed. This, for example, and many of you may be familiar with concepts like this as well, we're looking here at a 7-camera rig that sits underneath the train, and as we've said now, this can be under an in-service vehicle, and captures video data of the forefoot, the 2 railheads, and then 4 cameras that capture either side of the railhead there, both gauge and field side. We can install that on any vehicle, or as I've mentioned and going to come on later, we can integrate with data that's already been captured in this way. And that's just an example of what it looks like live as well. And you'll notice the lighting rig along there as well, those 4 lights as well, which shine the single line of light across the millimetre of image that's being captured. That's all integrated with the speed signals from the train as well. So it captures an image every millimetre that the train moves. And these can operate at line speed as well. So this is the type of data that is then delivered, and it has that visual fidelity required. In this instance, when we're talking about the LRAM's rail surface scoring methodology, and that will include things like checking, spooling, and correlation, and being calibrated at a 0 to 5 scale for severity. And And what we do at One Big Circle as well is try to ensure the high level of, for the want of a better word, accuracy, but what we look here for is the precision and recall. So understanding both from the recall how many, we try and reduce the amount of false positives that the engineers can see, but when it's a very critical thing such as broken rail, then what we will do is enable the engineers to view that so that they are the human in the loop, the expert that can then verify those conditions as well. So very important to make that visual very quickly. And we're going to talk through some of the ways to do that. So the opportunity here is to deploy equipment on board in service trains, as well as the infrastructure monitoring vehicles that are still relevant at the moment. We provide connect devices. So these devices are plugged in on board the train, and you can see a couple of installations there. And they are purpose-built for harsh railway environments, so they comply with a lot of the standards required to enable them to cope in those harsh environments. And again, touching on one of the speakers earlier as well, the fact that it's not just about shiny and new technology, it has to be about things that work in the challenging environment of the railway, trains on the move in very difficult environments, and on very huge range of vehicles that travel the environment. So once we're capturing data, the continuous line scanning images creates an awful lot of data. Across the UK here, for example, if you recognise a section of the British Isles there, this is an example of what it looks like to network rail. They're capturing the video data across all of their network, and then we can actually start to tune that into the conditions that they want to understand, so they can start to target the areas of most concern. But as I say, there's a lot of data that leads into that. So I'm now going to go through those three topics of how we actually manage that huge amount of data. The first is to start with edge processing. So this is the first layer of our data management. What this does is, at the edge on the train, perform some automated quality assurance on the captured imagery. Now, in the UK, we have a lot of in-service trains that have our devices in the cab environment. Lots of things can go wrong with that. Lots of good things can come from the imagery, but we can also have terrible weather. As you know, it rains a lot in the UK, and we deal with that quite often. It might end up coupled against another vehicle as well, so actually you not have any particularly good imagery. Or it may be so obscured by dirt or something else that really that imagery is of no value to the end user. So we can first of all cut that data being shipped to the cloud, and we can reduce that payload by up to 10% in the first instance. So no one gets bothered by data that's not good for them from a visual perspective. What we can also do is push to the edge is near real-time detections of safety critical defects so that they can be accelerated and sent sooner than the standard data. These are just a couple examples, so we can have cracked joints, or we can have thermal images that are being detected by the thermal sensors. So there's a good combination of basically advancing data and accelerating data that is very relevant to the operational control, and we can also cut out data that's not going to be of any use from a visual perspective as well. So that happens at the edge, and as I say, that's the first bit of data management where we reduce the volume. And that enables, what that means is that all freight and maintenance vehicles can help provide these inspection services because it's being monitored at the edge. This is a pictorial overview of the transmission architecture that's required. So at the bottom there, you can see these vehicles that do have the edge compute on board, and they can be, as I say, both the inspection vehicles that are targeted to capture data, but very importantly, and as Jackie was mentioning earlier there, that that in-service revenue fleet that's travelling around as well. So they ship the data to the cloud, and we do that by breaking the data, fragmenting it into bite-sized chunks, and attaching each image with its metadata, shipping that to the cloud, and then stitching that back together in the cloud so it becomes a seamless piece of imagery, a video for a user to be able to view and access. We then apply in the middle there a huge amount of processing to that, and that will be the machine learning and the AI pipeline to start to detect both assets and issues as well. And then the third part at the top, the view and share, equally important, is that we make that visible in a way that's really beneficial to the end user, the end engineer, the planner, the operator, the maintainer, etc. That also works with a number of APIs as well, so we can import data from other systems. We can make it visible in other platforms. I know we have feedback from engineers sometimes who don't want to see yet another system on their screens and laptops as well. So it's very easy to integrate with other systems as well, and we can take alerts and map them onto the system or white label that into an enterprise model. So I was at a presentation earlier, I think I mentioned the word flexibility about 17 times. It's a very flexible system to fit into whatever your environment is currently working on and helps advance that, that capability as well. And what we have here from the top down is what that transmission architecture does. So at the top there is the huge scale of data that can be captured by the in-service fleet, possibly up to 100 petabytes if you were going to be transmitting all that. We go through the edge processing to reduce that down, so we're both getting rid of the data that isn't of any benefit to us for poor light or whatever other reasons, and we've also accelerated the most use of the alerts data as well. And then we have dynamic demand, which is another way of reducing the volume of data that's taken from the cloud, taken to the cloud, and I'm going to talk you through that now. So dynamic demand is an AI orchestrated upload. What it does is it talks back to the revenue and in-service vehicles that are travelling the tracks. It also combines that with the infrastructure monitoring vehicles, the RIV vehicles, and it will talk to that fleet as a whole and will instruct where data should be prioritised, where data can be left behind because there's already enough of it, where run-on-run data on a daily basis isn't required because we've already had one run for infrastructure purposes, and unless something happens from an alert perspective or for an operational incident, then we don't need any more data that day. So there's lots of different, as an agentic approach to this, where basically the organisation as a whole can talk to the wider fleet, and this can be a combination of fleets, and really have intelligence across the scale of what's delivered. For example, what we're doing with our partners at LARAM is prioritising RSS-relevant imagery, so we can test those different environments where it may be lacking from certain RIV vehicles, and if we've got an in-service vehicle covering that area, then it can transmit that data as supplementary information. A case study from the UK, South Eastern Railways, based, funnily enough, in the southeast part of the railway, now has 32 in-service revenue trains installed with this equipment. They went from having a temporary housed device which they could deploy on in the cab of the train and on the front there. They've now turned it into an installed device. You can see the forward-facing and the thermal imagery in that yellow box at the front with the two windows, and then they have the AVA Focus installed underbody as well. So they have that range of data capture systems. They capture out in service all the time, and they use our agentic approach where they can dial down the data where they don't need it. That's then reduced the volume of data by 73%, but importantly, it's giving them everything that they need from an infrastructure monitoring purpose, so they can have that scheduled as appropriate, but then where there are any operational incidences, they can accelerate that data and make it instantly available. So it's a really good example, as demonstrated on the dashboard on the right there, of how they can monitor that fleet as a whole, but not have to worry about every individual train that's travelling around and having to schedule that appropriately. So it's suddenly giving them a holistic view across their network without having to deploy different resources to be on board the trains, different technicians. I don't know if maybe I scooted over that a bit too early in an earlier slide, is all of this is automated. So apart from the driver on board, there's no other physical intervention required to make this data accessible online. This volume of data then lends itself to having multiple AIs and an open approach. So supporting data it's collect once but used multiple times. So once that data is in the cloud, there's a number of different applications. These are just two examples. So the forward-facing video may have been collected for signal sighting, for example, but the fact that we can apply a machine learning model to that to detect wet beds is a further use out of that. And we've estimated that there's over 200 different machine learning models that could be applied to this type of data to detect things as well. For the thermal imagery again, so we started off by looking for hotspots on the third rail, on the conductor rail, but since that we've evolved to look at different components and started to angle that up to look at the overhead line equipment as well. So again, we're agnostic about the hardware that's being installed and why it's being installed. It's about making the most of that data once we can get it to the cloud, and the important thing is making that an efficient way to make it possible. I'm hoping this video plays. But this shows you a little bit of it, what the dashboard looks like in action. So you have your coloured alerts there, and you can click onto any of those features. And as I say, it's designed to meet different groups of engineers' requirements, different operational requirements. And here, for example, they can go and examine all the number of joints that they have across their particular area, and they can look at the different capture through time as well. So they can look at the same issue, but from different days. And so they can monitor change over time as well, or they can work backwards from when a change in other sensor systems such as geometry occurred. And then, as you can see there from the fidelity of the image, this is how an engineer can move around the dashboard with ease. And a further example as well is being able to move through, again, based on alerts here, so we can move through the filter. They can select what type of fault they're looking for. And again, this is entirely in the control of the end user. So they're looking for their corrugation, and then they can move through different locations of that. They'll always get the location converted from GPS and other locating systems as well. This, for example, has a high accuracy locator system on board as well. So then they have their location reference, and they can scroll through that, check on that, be the human in the loop, the expert eye that applies their information to that, and then they can extract that detail, create that as a report or as a work plan. That can then feed into whatever workflow system comes off the back of that, and then the maintenance is then carried out accordingly in whatever the next schedule requirement is. And we continue to innovate in this area as well. So a lot of the work we've done with thermal, we were asked to transfer that into the wayside environment looking back at the train. So we've taken the same concept of the thermal camera and the line scanning camera and use that to look back at the train. So as the train passes that environment as well, we've created a similar dashboard, or actually slightly squashed in there, but essentially you can see the image of the train that you can track through, and also any overheating alerts as well that have come off the axle or other other components of the train. From the line scanning perspective, you can look at radiators, other catches and equipment around the train as well. But this is a good example of innovation evolving in response to the industry and taking what is good technology already, but applying it into a different environment for a different purpose, but with the same goal of being able to more smartly monitor your environment and your rolling stock. So in conclusion, so in the context of heavy haul railway, the performance of the railway relies on effective maintenance of the railhead, and we've touched on there on the early work that we're doing with Loram and Partners on getting that data to enable that rail grinding, rail surface scoring to evolve. And a large part of that is by harnessing the coverage of the in-service fleet as well, on top of the RIVs. And that potential vast volume of data can be gathered and managed optimally because of those pieces of equipment that we've talked through and that architecture that enables you to handle volume at scale. And so, yes, we want, as we touched on earlier as well, things have to be scalable and robust, not just shiny and new to work in the environment. Data should be open, and we should be able to work with that accordingly. And we want a continuously updated picture of your environment. Rail is going to be monitored more effectively now than ever. Thank you for your time.
Thank you, Ms. Emily, for the power-packed presentation. The rail grinding is the most cost-intensive operation in the track maintenance. And if this technology deployment can reduce the rail grinding requirement even by 10%, it will be a huge saving to the infrastructure operator. I hope this, as it is already deployed in the UK railroads, it will find place in Indian Railways also. Our next presenter is Mr. Michael from Gazner. His presentation will be extending the service life of ballast track while improving track quality and safety. Basically, Gazner do provide the solutions to the track vibrations and vibration mitigation measures. That is the resilience in the track. Resilience in the track is a very complicated phenomena. It's not that the more resilience is better. Track needs to be within certain range of the stiffness and the resilience. Over to Mr. Michael.
Okay. Thank you very much for the introduction. I'm here today filling in for my colleague Martin Kirchmeier, who has prepared the paper and the presentation. And I now have the pleasure to present it to you. We have now heard about predictive maintenance, so I'm very excited to tell something about prescriptive maintenance. So the art, the way of designing a track that you need less maintenance from the get-go. I would like to start to introduce the DFCCIL&D, how we work. We combine simulations, theory like FEM modeling for track turnouts, and we also do discrete element modeling to understand the ballast better. Then we do laboratory testing. We have 4 hydropulse machines up to 500 kilonewtons that we exclusively use for R&D purposes. There we can do component testing, but also whole system testing. And to conclude, we also do a lot of track measurements, displacements, ballast contact pressure, vibrations, and so on. And all of these we take and pay into our system, whole system understanding. As a producer of elastomers, we need to understand all of the components because we're always in an interface. And our components can only be properly laid out if we understand what's above and what is below. Next, I would like to explain what an undersleeper pad actually is, so that we have all seen it and know a bit better what we're talking about. Getzner produces cellular polyurethane undersleeper pads. They all consist of an elastic layer and a connection layer that is placed into the wet concrete at the sleeper manufacturing plant, and therefore then properly connected to the sleeper. All of them are good for ballast protection, but we then also distinguish between highly elastic pads for vibration mitigation and elastoplastic pads with particularly good ballast protection and which are also good, especially good for track stability and safety purposes. Our other range in the heavy haul area is rail pads, so that you can easily add resilience or retrofit resilience to your track. Then, well, the undersleeper pad, which is our workhorse, where you can get the best results for the investment that you're doing. And then we also have under ballast mats, for example, for bridge protection or to design transition zones. Today we focus on undersleeper pads. And we go directly into ballast protection. In a modern superstructure, with all the engineered components, ballast has become the weakest link. We see that, for example, here with white spots at transition zones. We have crust ballast that can no longer support drainage, and that is no longer elastic enough as it is required. Then we have geometric faults or hanging sleepers that can occur. And as soon as we only have contact in the middle, we also get cracked sleepers. So how do undersleeper pads protect the ballast? Well, we introduce resilience, so we make the track softer, and this leads to a elongation of the bending line, distributing the load onto more sleepers and subsequently reducing the load on the individual sleeper, and then again on the individual ballast grains, less stress on them. It's an indirect effect. The direct effect comes by making the contact area larger, therefore also reducing the pressure. Protect it directly. Here we have some sample pictures on the left-hand side without the undersleeper pad. We have crushed ballast, and on the right-hand side it's much better. This is after 100 MGTs in a 280-meter radius curve. So how does it work, this contact area? An unpadded sleeper typically has 4% of contact area. Now, with a pure elastic material, if we now reduce, let's say we can increase our contact area from 5% to 20%. That means we reduce our ballast contact pressure by 80%. If we now do this with a purely elastic material, we need to get very soft, and this will increase the rail deflection. But of course, we want to limit our rail deflection for various reasons, also for safety reasons. So then we arrive at a very important question. Is there a material, an undersleeper pad material, that is stiff and thus provides still a big contact area? And we find that in our elastoplastic undersleeper pad. Plastic deformation is known. You imprint the stone into the underballast mat and it leaves an imprint, but the imprint will stay. Elasticity, you will always get a rebound. It will always come back. The elastoplastic pad combines both properties. So the stone can embed itself into the material, but when it is removed, or when the stone moves along the underside over time, the pad comes back and the connection retains in a good quality. The pad grabs onto the stones. We then did a material test to figure out how different materials behave, different principal material properties. For this, we did a full sleeper test according to the Yen standard with 100 kilonewton in our large-scale test rig. And we used the same ballast padding for each scenario. What we measured? We measured the ballast contact pressure. We used for this our sensor sleeper technology. This is a matrix pressure measurement technology. These are 10 by 5 millimeter large pixels that can resolve individual ballast stones and how much pressure the stones insert onto the sleeper. We tested 3 scenarios: the no USB case, ethylene vinyl acetate copolymer pad, and our elastoplastic polyurethane pad. We did 2 tests with our elastoplastic pad, number 1 and number 3, and in between the EVA test. We did this in order to make sure that nothing significant has changed from one test to the other, as we left the ballast pad the same. These are then the results. You see the loading on the right-hand side with the cyclic loading, and you see without the undersleeper pad you have hard peaks. The EVA pad reduces them already, and the polyurethane pad has a significant reduction. And now I can mention, looking at this picture, I can mention that the EVA pad and the polyurethane pad have the same nominal stiffness. They were categorized as the same pad when you only look at the load deflection curve. Also, we sometimes have some extreme stones, which just, well, statistics. How can we now evaluate this to get some single values, to get a good comparison? In each sensor, we identified 8 areas, numbered them, and for each experiment, it were the same ballast stones. We took the maximum pressure out of each area, and then we calculated the median values, because with the median values, we can exclude 2 extreme stones. And this is the result. The EVA pad already reduced the peak ballast pressure, but the polyurethane undersleeper pad reduced it 4 times more than the EVA pad. Antonio Merheb, now CEO of IHHA, has found similar results in his measurement. With the USB, he has a 3 times higher contact area in this track measurement that he has done. And most importantly, he had a reduction in tamping cycles of 2 to 3 times in his heavy haul operation at MRS. From him, there's also this investment strategy to kind of give us an idea how we think about it. When you want to build a track, you always have a planning, and design and a construction phase, which are initial costs, and after that, you have your maintenance costs. And after some time, the maintenance costs, they increase fast and rapidly, and at that point, you will need to renew your track. There's the approach to build now, fix later. So you build cheaper, save money there, but eventually your maintenance will overtake, and your track life is actually lower. Or you invest a bit more, and throughout the life, you will save on maintenance costs, and your overall costs will come down. At this point, I can also mention that we're now working on models and testing and having first results where with the undersleeper pad, you can also save in other areas, like for example, ballast costs, that you can build cheaper with an undersleeper pad. We're working on that right now. This is another way to, well, quantify the effect, the business effect of an undersleeper pad. This is a study by the University of Graz, where they plotted on the horizontal axis the gross tons per day, and on the vertical axis the internal rate of return, including operational hindrances. We've heard today operational hindrances are very significant in heavy haul and need to be considered. And so we have here values of 10, 15, 20%. Now let's put it into the heavy haul context. The graphic goes up to 80,000 tons per day. Rumo has 110, MRS over 500,000, and Vale 660,000 tons per day. So although extrapolation has its limits, it gives you an indication where we're going. This is another way to quantify it. When we look at track stability, here we look at ballast protection lifecycle costs. Here we look at the track degradation rate, which is the exponent in the exponential track degradation. And we compare it at welded joints that are padded in green and unpadded joints, welded joints in red. And on the horizontal axis, we have the impact of the wheel onto this joint. And so it goes from low impact on the left to high impact on the right-hand side. And there we also see the degradation rate is significantly lower with undersleeper pads, also for very hard impacts. So much for this part of my presentation. And now I want to go into track stability, safety, and also lateral track resistance, a topic we've heard about today already. So, since we're now continuously welding our rails for decades now, well, we have the problem that we no longer have these rail joints, because on these rail joints, all the stresses, well, a lot of the stresses could be released. And when we have too high stresses, some small rail defects, and when the stress forces outweigh the lateral track resistance, we can get these rail bucklings. How would one describe this? You have a lot of effects that come into play. We can sum up all of the thermal effects on the left-hand side. It's a sum of all the thermal effects, and it's consistent of the actual change in rail temperature. Then we have a safety factor as a second input. This is from the German Federal Railways. The third term is track structure interaction. And the fourth term is longitudinal force accumulation, for example, in front of a turnout. So all of these factors define the required or the necessary delta T that the track needs to provide in order to be safe. And on the other hand, this is one side of the equation, and the other side of the equation, we have these formulas for tangent and curved track, and they contain the moment of inertia of the complete grid. We also heard about that today already. It contains the radius, it contains the model of elasticity, and it contains this WQ. The WQ is the lateral track resistance. And on the right-hand side, we plot the increase in lateral track resistance, and on the vertical axis, we then have the increase in delta T, in available delta T, that is. So let's say we have a 40% increase in lateral track resistance, so we can end up with a 25% increase in available delta T. Theory looks very promising. Now let's jump directly to a measurement of the Austrian Federal Railways. There they measured the lateral track resistance for wooden sleepers, concrete sleepers, and concrete sleepers with undersleeper pads. On the left-hand side, directly after tamping and dynamic track stabilization, and on the right-hand side, after a consolidation of 3 months and also 7 months for the 2 bars on the right-hand side. This shows significant improvement. Now let's try to analyze that. When we look at the sleeper, we have different parts that contribute to the lateral track resistance. We have the shoulder ballast at the end, we have the friction on the side of the sleeper, and the largest part is at the sleeper bottom, where we can place our undersleeper pad. Now we again ask the question, does every USP type perform equally good? For this, we designed a lab experiment where we have a ballast trough, where we put 2 half sleepers. We designed a ballast shoulder so that we do not lock our ballast into the box so that it can move freely to one side. And then we also consolidated it again according to the loads for a full sleeper test. For the unconsolidated case, we did 900 cycles at half the load, and for 2 hours at 3 hertz, 21,600 cycles with a full load. We did only 20,000 cycles because we did 70 tests to get good statistics. This is our setup. You see the ballast trough, 2 half sleepers on the left, and on the right-hand side you see the edge of the ballast bed. And now this is how this push test looks like. You see here a hydraulic cylinder where we also measure the force, and we control it with a needle valve, and it pushes the sleeper to the left. And on the other side we have a displacement sensor, and this displacement sensor now records us our displacement accordingly. And then we did this for a number of configurations. We did a reference without an undersleeper pad. We had several elastoplastic pads, our standard portfolio in orange, and a new development here in green. We had checked high elastic pads, and we checked elastic pads like EVA or granulated rubber. And this is the results that we got. Left not consolidated, right consolidated. And we see right away that orange and green is above all of the others. Through the whole phase where we displaced it over these 10 millimeters here. Typically this is now evaluated at, which is an industry standard, at 2 millimeters, and we create a bar chart from it, and this is the result that we get. We have the no USB case, and now we clearly see the elastoplastic ones. They're peeking out. Let's put some more lines into it. So what we see, the highly elastic and elastic pads have no negative effect on the track or the lateral track resistance. But the elastoplastic pads, they add significantly into the lateral track resistance. So it's this material property that is important. Now, since we did tests with only 20,000 cycles, we also did a couple of tests with full sleepers and 1 million cycles of consolidation. And we did the same push test there again, leading to this result. What we see with more consolidation, we get better results. Hereby in the lab, doubling when you see at the full bars, which is the consolidated measurement, we double the lateral track resistance with the right material. And the half sleeper tests are overlaid with these circles. Significant impact. Now let's have another look at another track measurement where we have a no USP, EVA, and PU. This is now a test done at a narrow gauge operator in tight curves. We did a very thorough testing over a year. And we also see that with the polyurethane pad, you have a significant increase, again, a good increase in lateral track resistance, significant one. And we also overlapped our half sleeper test in orange and our full sleeper test in green, thereby considering that, of course, the ballast shoulder and the side friction also contribute. But this is the result of an actual track measurement. Now we come to my last slide. So I want to go to the conclusion. Do different USB materials perform similar? So great answer, no. You can choose the right undersleeper pad material for your application. And for ballast protection, it's elastoplastic. For vibration mitigation, it would be highly elastic. We have a good impact when it comes to life cycle cost and when it comes to track stability. This combination of a stiff material that has its plastic properties to properly grab onto the ballast gives you just a bit of more stability at high temperatures, more resilience. And I also want to point out here, what I'm actually proud of is that through theory, lab experiment and track measurement, we gained consistent results. So, thank you very much. Looking forward to questions, either now or later at our booth. Thank you.
Thank you, Mr. Michael, for the nice presentation. The underslipper pad is effective in maintaining the track parameter and improving the ballast life. There is no dispute on that. The debate goes on what material to choose, EVA, polyethylene or resin bonded rubber, what thickness, full surface, half surface. The need is that there should be some codification of these recommendations so that the practitioners, they don't have to struggle with what is good, what is bad, and they can simply adopt a particular situation. Somehow that is not happening. Somebody will have to take initiative. Let us see that if we can take initiative in India on this. So with that, we have had the 4 thought-provoking presentations, and there are a whole lot of questions. If we really address all those questions, it will be more than an hour. In fact, I never thought that post-lunch session, that kind of excitement will be there in the delegates to ask so many questions. Anyway, I have given the questions to the presenters. The first presenter, Mr. Excel, has so many questions, and others also have questions. Some of these questions are unrelated to their topic. Some of these questions will involve a totally different presentation in itself. Although our presenters have the expertise to address those questions, I'll request the presenters, in the interest of time, kindly use your value judgment and try to finish it in 5 to 7 minutes.
Mr. Munich can get my time too.
Yeah, everybody.
You are scared of... Okay, you said 7 minutes for all of us, no? Together. Not,
You can. You
no,
decide.
No, it's okay. I will try to keep it very short. I got 7 questions actually. 5 I can answer because they are part of my field. 1 I cannot answer even if it is part of my field. And 1 I cannot answer because then my Siemens bosses would kick me out.
But at least you read the question and the author, so that to do
No, I
justice
can't. These questions are so detailed. I have clustered them.
Okay,
yeah?
fine.
So the questions I'm answering, they're all. I mean, I will make a joke later about the one from Siemens. Yeah? But the questions are all related to cloud-based signaling. They are clustered in 3 topics. 1 is about IT security. Is cloud-based signaling secure? From yes. There are tools out there. Siemens has own tools, but there are tools generic in the market. We have our tools called Core Shield. There are safety layers embedded everywhere. This is safe. There's no doubt about it. And it exists already. This ties me into the second question, if it is real. It is real. We are having several projects, and in Austria, in Germany, now for the first time in Norway, and the IT security is obviously a big part of this. And yes, it is real, and it ties me to the third question. Sorry, there's more questions? Okay. Okay, thank you. Oh. I put it in the stack of maybe to be answered. Okay, and so the third question is, actually it's safety versus reliability. And that's actually an interesting point, because something can be 100% safe, but then it stops, in a way. Yeah. So
So because when the question came, I thought, what am I actually saying here? Because it's saying, is cloud-based signaling reliable in view of cybersecurity? It's actually two questions. And so the reliability is achieved through redundancy. So data networks are duplicated, triplicated, but I don't want to make it sound very hardware heavy. That would be the wrong statement. But in an IT world, there are always options, routing options, going along different paths, and so on. So in summary, cloud-based signaling is safe. Cloud-based signaling is configured to be reliable. Cloud-based signaling exists as an operation. And yeah, and there was one more question. Yeah, and can it be installed in India? Yes, just to give you a quick snippet, we are in discussions. It started with the Railway Board, a person that just retired, but somehow we are installing a trial in India right now in a brownfield environment based on an installed line. We are converting this into a cloud-based signaling trial. And this will be done over the next 6 months. So we are convinced it can be done in India in an existing railway environment. So these were the questions related to signaling, cloud-based signaling. One question came with regard to, this is, I have to read it out because maybe the colleagues from Foslo have an answer. What is better, spring setting devices or dual drives? This refers to point machines, in my view. And I take this question with me, and we have experts. I was actually desperately reaching out to my Australian colleagues, but no one answered. 6 hours ahead, they're in bed or in the bar. I don't know, but they didn't answer. So I take this question with me, unless a Foslo colleague has an answer. And the last one, I have to read this out because I found this quite a good question. What was the background and strategy behind Siemens' acquisition of Mermec? How can I answer this? If I answer this, I will be in big trouble with Siemens because we have a silence period, so I hide behind this one, but honestly I have no answer. Most of us in Siemens are saying that will be great, but let's find out later. So I can't really answer. Yeah. So these were my questions.
Thank you. Thank you. Now, Mr. Jackie, please.
Thank you. I'll try and answer, there's 3 here with me. The first one was, we understand that autonomous inspections are still not allowed by the FRA. You need to have manual inspection. Please comment on how do you justify autonomous inspections in this case. So I think a quick one is, there's different autonomous. I do believe that man inspections for certain elements are still required. However, from a Class 1 perspective and from the FRA perspective, I believe that in December of 2025, there was a waiver provided by the FRA to the Class 1s to do more studies on this specific topic. You know, as ENSCO, we don't really advocate for or not for manned inspections in a sense. We do advocate for tools to support inspectors to be more efficient and effective. But there is more information going on, or there is more information available publicly about this opportunity. There is Class 1s at the moment that's doing a lot of their own work using autonomous and automated track inspection to prove that the value is there for them then to basically do less manned inspections. Not getting rid of it, but do less of it. And I believe that, you know, they've got about 5 years for this waiver that has been provided. I think all in good, you know, in good faith to see what technology can bring. So that was the one question. The other one was, where is this one? Here it is. A bit more difficult question. The average bogey rake examination and repair cycle may be approximately 6 hours, but autonomous inspection systems primarily reduce. Oh, sorry, the question was about Where's that? Here it is, sorry, my apologies. The average inspection and repair time on a bogie array in Indian Rail is around 6 hours. How much of this yard examination time can be practically saved by going for autonomous inspection? So the first thing is we need to distinguish between the inspection versus the fix, the repair itself. What I can say is our experience, and there's some more information out there publicly, is if you look at the inspection piece on its own, I know doing train inspections, typically from an FRA inspector, takes about 2 to 3 hours for a whole train to do the inspection. Some of those inspections, or a lot of those inspections, is actually at night, so we don't know what they see or they don't see. But if you look at autonomous inspections and wayside inspection technology, you basically can bring that down, anything from half the time to probably only 20% of that time to do that. Again, this is a technology to actually then assist inspectors rather than the inspectors going out and doing it in a live environment. I hope that helps with that answer. That was for Akesh. And then the last question, if I can find that. It says, when the train consists of a fixed and addition of a dedication measurement wagon is not feasible. That's pretty, I've heard about this before. It's not unique to Indian Railroads. So what is the practical approaches available for rapid installation on instrumentation on commercial vehicles? While ensuring minimum time and no impact on the schedule of train operation? Very good question. I think here it's again, it depends on the type of technology. If you look at vehicle track interaction technology, you can really do that installation with less than an hour. You need to be prepared, you need to plan it. A good time to do it is when you do your locomotive maintenance, general maintenance, and just do the installation during that time. When you look at track geometry, it is a bit of a longer period of time. I think there you should look at the cost benefit of having autonomous inspection installed on a locomotive, for example, where it will probably take about 5 days to a week. But again, you can do it during general maintenance of those locomotives. But as soon as it's in, your advantage of getting that condition monitoring continuously is just outpacing that installation time. Thank you.
Thank you very much. Ms. Emily, please.
Thank you. I'll just rattle through these. The first one is, how is edge processing going to give real-time fault detection? What is the delay? I think there's a couple of responses here. For real-time detection for faults which are on board the train, there's the impact there is the sensor required and the compute power that would be required on board to enable fault detection to happen from visual systems to be part of the train control system. That's something for the trains of the future. I think it's not something that can be retrofitted with technology as it is now, but it's certainly an area of R&D in which that capability is pushing along with. I think what needs to be taken account there is how you manage the false positives from a system like that, if it was going to be responding to faults from on board the train. At what level do you position your parameters to cope with false positives? Do you want more of those or less, essentially? Which ties into some subsequent questions as well. What are the precision and recall values of your system? We aim for both of those to be achieving over 98%. In the example of where we've got faults on the track, for example, faults in the joints, cracked joints, etc., cracks in the rail, etc., we will err on the side of increasing our recall. So we would want all alerts, all machine learning that has detected that to alert the end operator. What we then have is their ability to verify those faults. So if there were 10 faults along, or 10 alerts along a 100-metre stretch, say 8 of those were true faults and 2 of them were false positives, we'd rather have all 10 alerts delivered to the end engineer so they can verify those and then respond to the ones that they have confirmed. We've had things like a tiny little trickle of paint has been detected as a crack. It's not until you're on site that you can understand that, but in a lot of examples, this data set enables us to train the model even further as well. But precision, for example, if we're looking for graffiti or scrap rail, where we've got a high volume of the problem, then we would rather have a higher level of preciseness so that actually you're not being sent lots of false alerts about things that you don't need to attend to because there's a high volume of them. It's quite an art and a science, so I'm happy to have a deeper chat with anyone that does want to go into detail around precision and recall. Has operating rail inspection vehicles completely eliminated the manual inspection? No. But there are processes that are moving in that direction where at the moment we have like a parallel, certainly with Network Rail, they're having parallel operations where they're testing the manual inspection against the digital, and ultimately it will start moving across as they grow their confidence. What that really relies on is the consistent delivery of the data. There's no point in changing systems to digital monitoring if you can't support that with continual accurate data that's being provided as well. And at what speed can you capture track geometry data? Our systems work at line speed, so we've tested up to 125 miles an hour in the UK. And the last one was as ROI studies to establish business cases for absorption of technology, basically looking at the cost benefit from the operations perspective. So it's been proven in the UK that an hour spent on the digital system online reduces an 8-hour site visit. They've estimated over 1 million hours of boots off ballast on an annual basis now, being able to do digital inspections rather than on foot. And for the detection of a fault, for example, that can be anywhere, say a thermal fault has been detected in the southeastern or a cracked joint, for example, that going to a full failure can cost anywhere between £50,000 to £500,000 in delays and remedial work. So being able to detect that sooner, attend to it in that first access gap within that 24 hours has a huge cost saving and operational benefit to the operators. Those are mine.
Thank you. Now, Mr. Michael, please.
Okay, first question, whether using USB also increases the longitudinal resistance. Well, the USB itself does not care in which direction it is pushed. Then again, when you look at lateral track resistance, we push a narrow object, the long side of the sleeper, whereas longitudinally it is a relatively wide object. So there already we have a lot more resistance. So in this case, I would say it comes down to the forces in the rail seat and the resistance of the rail seat against a longitudinal movement. The next one is whether undersleeper pads has advantages over underballast mats. If yes, and how much? So basically when it comes to ballast protection, we recommend undersleeper pads. You have the best result for the money that you're investing, and you do not have much movement in the ballast compared to some underballast mat. It produces a bit more movement. Underballast mats are used mainly for structure protection or in order to modify the track modulus to design smooth transition zones. There you will have huge advantages if you combine these in the right way to get a much smoother track or a much smoother transition. This gets to the third question. Maximum differential deflection between the transition zone and the adjacent standard track as per code. So I would say yes, the transition zones, when we design a transition zone, we use our finite element modeling and we smoothen out this. So you get a smooth transition from one into the other. Each zone then itself, of course, has its own deflection. We can take care of the code, what's required, what the limits are. I do not know the exact limits that would be relevant here, but it can be tailored to it, and we have designed transition zones here in India. So therefore, my answer would be yes. Thank you. Thank you.
Thank you very much, all the presenters and the delegates. for cooperating and participating in this session. Thank you.
Please join hands for all the presenters, and we thank you for sharing your perspectives, thoughts, expertise with all of us. As railways move towards greater speeds, heavier axle loads and higher traffic densities, the future belongs to systems that can sense, predict and prevent. Once again, a big thank you to all the presenters, and before we begin presenting mementos to each one of our presenters, I request our Managing Director to kindly please welcome our dignitaries, because we are now being joined by some esteemed guests. We begin by welcoming Shri Shyam Sundar Gupta ji, Principal Executive Director, Infrastructure. We welcome you, sir, and I request Praveen ji to please accord a green welcome to Principal Executive Director, Infrastructure, Shri Shyam Sundar Gupta ji. We also welcome Shri N.C. Karmali ji, who is Principal Executive Director, Gati Shakti. So may I once again request Praveen ji to please welcome Shri N.C. Karmali. A very warm welcome to our dignitaries, and now we move ahead with presentation of mementos as tokens of appreciation and respect for our presenters, beginning with Mr. Axel. Thank you. Praveen ji, may I please request you to present. May I request Shri Anurag Sharma, Director Infra, to please present tokens to each of our presenters. Thank you, Mr. Axel, for your very interesting presentation. Please join hands, ladies and gentlemen, for our speakers, presenters, for sharing their expertise, knowledge with all of us today. And after the DFC memento, here is a very special statue of unity, which serves as a symbol of national unity and pride. We also welcome and thank Mr. N.J. Westhuizen. Thank you for your sharings. Zordar Talia. Let's join hands. Thanking all panelists for being a part of this very interesting session. Thank you, Ms. Emily, for your presentation. A very special DFC memento. And another one, the Statue of Unity, which is a towering monument, as we could also see on the screens. We thank Mr. Michael for his sharings with all of us today. Thank you for being a part of this panel. Once again, a big thank you to all the panelists, and now we would be thanking our moderator, Mr. Subodh Jain, for moderating this session. Thank you very much. Ladies and gentlemen, every meaningful conversation deserves a brief pause for reflection. We will now break for a small refreshment break and reconvene in 10 minutes from now. We request you to take a short break and be back in 10 minutes. Thank you. seats, and also request our participants who are standing outside to please join us back.
जिनके स्कैन हो गए उनके स्कैन छोड़ दो, जिन्होंने स्कैन नहीं करा उनके लिए बोल रहा हूँ। दोज आर नॉट, जिनकी अटेंडेंस नहीं लगी है स्कैनों पे। कल एक लग के जो निकल के कुछ मनी है उसमें, मनी दे रहे हैं, लाभ तो नहीं होगा। 10 तो कुछ भी नहीं होगा इनका, लाख ही होगी।
We are beginning with this session now, ladies and gentlemen. Please take your seats. We are beginning with this session. May I please request you to take your seats. Ladies and gentlemen, welcome back after the refreshing break that all of us enjoyed. And now we're all set to begin with the third technical session on System Intelligence, Digital Twins, and Predictive Maintenance at Scale. This will be moderated by Shri Shiv Kumar, who is an IRSC officer of the 1972 batch. He has had a distinguished career spanning nearly 4 decades in Indian Railways, a civil engineering graduate from Delhi College of Engineering, and an MBA and a master's diploma in public administration. He has held several prestigious positions, including Divisional Railway Manager, Sonpur, Director Edison, Pune, Advisor Vigilance Railway Board, and General Manager Northeast Frontier Railway. He played a key role in landmark infrastructure projects, including the rail connectivity of Agartala to the Indian Railway network and the construction of the iconic Bogibeel Rail-cum-Road Bridge across the Brahmaputra. He has also pioneered e-learning initiatives in railway training and authored numerous technical publications. With his rich experience in railway engineering, infrastructure development, and technology-driven transformation, Shri Shiv Kumar is ideally suited to moderate today's session. May I please request you, sir, to begin with the deliberations of this session. Over to you.
Good afternoon. Thank you, Juhi, for a very flattering introduction. I welcome all delegates to this last technical session of the day one. I know it's the most difficult time in any seminar because when delegates are already saturated with so many new ideas, novel things, and I will only request their kind indulgence to continue to pay their attention to the speakers in this last session. As you know, we have traveled a long way since morning. We begin with validating design intent of various track components under sustained heavy haul loading. Then we looked at how to detect defects and manage forces and protect infrastructure. This session will focus from data integration to corridor level decision support. This is the crux of the seminar, engineering reliability at scale. We have learnt about digital twins that mirror track, overhead equipment, rolling stock, and operation together, predictive maintenance architecture built not for a single asset, but for the whole enterprise. And the data quality and interoperability that will decide whether any of this is sustainable. I do visualize for the DFCC management to benefit from this session particularly because they are engaged now with twin tasks. One to manage the two corridors which they have already constructed and another one which is in the offing. We are privileged to have 4 speakers in this session who represent the leading lights in their respective fields. The first speaker on my right is Professor Ravitharan from Monash University. By the way, he is the only professor in the whole audience. So let's give a big clap to him. So he is director of the Institute of Railway Technology at Monash University. He is internationally acclaimed for his contribution in the field of railway engineering research. He has worked extensively with heavy haul operators across Australia and other countries. His work focuses on translating advanced engineering research into practical railway applications. The title of his presentation is Improving Resilience of Heavy Haul Railways through Advanced Real-Time System Monitoring. So let's give a big hand together in welcoming Professor Ravitharan.
Thank you, Shri Shiv Kumar, for that kind introduction. Ladies and gentlemen, this is a great privilege to be here second time in your second heavy haul seminar. My presentation, as highlighted, is improving resilience of heavy haul railways through advanced real-time system monitoring. The focus should be resilience and advanced. The theme of this conference is engineering reliability at scale, the next phase of heavy haul railways. Once you have built a railway, the next phase is to maintain the reliability of that rail network, and how do you bring that reliability through resilience. So I introduce myself, my institute, which is Institute of Railway Technology, on 2 slides. One, it has got advanced capability and significant knowledge of heavy haul. With our connection with Australian heavy haul for last 54 years and 26 years of that from Monash, with that type of connection point and identified as the premier track and vehicle research center in Australia, Institute of Railway Technology is very well known to everyone in Australia as well as in India. The reason that we are very well known is because it has played an important role in transforming Australia to be the global benchmark of heavy haul railways. The numbers shows why it is regarded as the global benchmark. Now, most of you know, when I presented last year, I targeted about predictive prescriptive maintenance capability using instrumented revenue vehicle technology. I will just briefly run through what I presented last year in the first 10 slides so that those who weren't here would be knowing what I have done, and then go into much more detail of the advanced capability that has got at the moment. Again, it has been presented quite well before me by several presenters. The dedicated instrumented dedicated track geometry vehicle is the past. It's not the present. It actually gives you information not continuously, ad hocly, and that creates issues such as the ones that I have got here: slow, silo, a reactive capability. It doesn't really give you a continuous understanding of the rail infrastructure. It also doesn't really provide that important aspect of vehicle response that is required for a holistic investigation of railway infrastructure. So instrumented revenue vehicle technology was introduced in heavy haul in Australia in 2002 to really continuously monitor using real-time reporting capability on revenue vehicle instrumentation. This technology has got the capability to automatically measure, process and report data, at the same time also provide continuous deterioration of a railway infrastructure to identify when to do the maintenance, and therefore it can identify rapid deterioration of tracks that is required to be maintained very quickly. Heavy haul is a railway infrastructure, in my experience, is like a normal railway infrastructure with a fast forward approach. So any deterioration that you need to be picked up very quickly before it becomes a problem for the railway operation. So the system approach, what it means is, if there is a vehicle response to a track is significant, as shown in this particular graph with a circle, that need to be responded immediately. That response is not track geometry measurement, it's actually vehicle dynamic response. Vertical acceleration is being picked up that it has gone beyond a preset level of comfortable range. So that needs to be addressed very quickly through ways of looking at the information that is provided in this graph. On the top particular graphs, it shows the bounds of a railway rolling stock because of a top 4 meter, top 4 level track geometry. So that is what I think it is important to highlight here. So what I'm highlighting is getting that information very quickly that will allow you to start looking at how to really implement some operational restrictions to safeguard, to provide a significant reduce the risk of the rail infrastructure. It's the approach that we use in Australia and several railways use, using temporary speed restriction. Temporary speed restriction need to be applied in an appropriate way, not to really bottleneck the whole network. So you need to know by what sort of numbers that you can reduce the speed to reduce the dynamic that goes through that particular rolling stock which is running on that rail network. So now you can see where I'm heading with this requirement. For a data that is collected on an instrumented vehicle, that needs to be converted into useful information. For that, it has to have a reliability, the accuracy, the repeatability is quite important, which I highlighted in my last year's presentation. But what I want to present today is that that information to provide improved resilience, it has to be available in a timely manner, immediately. It should be available whenever you need the information. And the third one is it has to have the integrity of that particular requirement. How do you get that type of data provided to railway operations very quickly? is through continuous monitoring. Continuous monitoring provides early detection of a problem as soon as it happens or even before it happens, and therefore you can start planning your improved safety maintenance immediately. That also reduces manual inspection. Manual inspection, if dedicated track geometry measurement every 3 months is not good enough, manual inspection is not really the best way to go forward if you're having a railway infrastructure. What I want to highlight is bring track buckling, which has been mentioned previously in this forum. Track buckling happens very quickly. Within hours, within a day, the track buckling happens, and in the past, we use a VERS capability to measure track buckling tendencies. But using instrumented vehicle, you can measure the subtle change in your rail infrastructure. Changes can be monitored and measured immediately. That's what we have actually highlighted and show here. Track buckling to be understood and identify early stage when the track is starting to breathe through a vehicle running through that section, and you can actually say this section is going to buckle in the next few runs of a train going through that section. This is capability is one which requires timeliness approach of data, and a systematic full-scale data is critical. We are using this in Australian heavy haul to identify track buckle without putting a VERS or unclipping the railway infrastructure. This is identified. That's one point I would like to start with. The second one is identifying where the rail is going to break. If a rail break happens and if we say, oh, rail broke and we want to identify it, it's too late, the rail has broken. You need to understand where the rail is going to break using the leveraging the instrumented revenue vehicle technologies, surface acceleration, which has been measured, and through that mechanism, you can identify the fatigue damage on a rail. Even when the damage has been removed through grinding, still the damage is there on the rail. You need to understand how that damage is going to cause a defect in the future. That is the way that we can actually put some numbers on a fatigue damage odometer to say these sections need to be maintained much more frequently in a manner that reduces the track rail failure. So that is the second part I would like to show that what has happened. Now I want to really focus on the availability of information. In Australia, if you have been to Australia, it's a large country. There are a lot of areas where arid areas where the heavy haul railway is running. These 3-kilometer long train with 40 to 43 ton axle loads are running through areas where there is no Wi-Fi connectivity at all. So in the past, what we have done is we have used to get this boxcar to be a very advanced condition monitoring capability. We have got solar panels. Solar panels are great, but it's not great all the time because there's no solar all the time. Therefore, you have to introduce batteries, or there's dusty and cloudy environment. So what we have done is we have come up with a energy harvesting technology methodology to retrofit into a train. So we are not going and putting it when the train is being manufactured. We are introducing a dynamometer next onto the rolling stock, which is already running, onto the bearing cap, which can produce up to about 300 watts at 80 kilometers per hour, which gives the availability of this instrumented car 100%. Now the instrumented car continuously monitor the data on the railway infrastructure. How does that work in a railway environment which is long is great because you have continuous capability to measure. But the other part is what I mentioned before, there is no Wi-Fi or 3G or 4G capability in massive areas. So you detect some defect very well, very quickly, accurately and reliably, but you can't really transmit that data. Why? Because we had actually come to a port where we can send the data to our center to process the data and provide it. This is where the technology has taken to a next step for us, through us. Through onboard edge computing, we can now communicate, data analytics can be done on board on a instrumented ore car running in a Western Australian environment or in a Hunter Valley environment, provide that information immediately to the operator within minutes. Within 2 minutes is our median at the moment. Within 2 minutes, we can actually give, there is a problem in this particular section of track, with the advice what to do as well for the next train which is going to pass through in the next 20 minutes. So this is the advantage of the technology that is moving forward. Therefore, there is no way a train which is going through a section is going to be affected. And this is how we are improving the resilience. Now, I will go into a bit more detail. If you have detected a defect, that defect has to be characterized as soon as possible. Then the impact has to be assessed and decisions has to be made. Instrumented car is an engineering capability. In the past, we didn't have any visual inspection, because these cars are O cars. They actually go through dumpers with a dusty environment, and cameras cannot really take that information as soon as the engineering information is collected. But now, with various new technologies, we are starting to use cutting-edge computing vision system to not only understand what is the engineering impact of that particular section from a train on a track, what is happening on track. At the same time, provide advanced knowledge to why it is happening as well. I think you have seen some of the fantastic presentations before me that vision systems are available to really understand what is happening on a section. But if you don't have the engineering knowledge of that vision system, you don't know what to do with it. So therefore, I'm actually coming from the other side. We had the engineering knowledge, now we are going with a vision system to improve the knowledge of what we have measured. This particular next one, if it works, I think you will see that we have got a large-scale, full-scale digital twin which can be used in a laboratory to really replicate what is happening on a railway infrastructure and simulate main light speed, acceleration and braking to understand what would happen if we have the information immediately on a railway infrastructure. This is not a track, it's not a digital twin of a real one, it's a digital twin of a make space capability to understand what would happen in a railway environment using this particular laboratory. You had to come to see it. I think I can't really explain it in a few words, but you had to come and see it. These are images taken from a train, from running at normal speed, and we saw some of the beautiful images. They're very clear. You can see where the joints are, you can see where the damage to the joint is, or various damages that we can actually bring together, various images we can bring together accurately to provide an optimal accuracy of AI inspection modes. So this is actually taking that images further and trying to make use of that to provide a resilience for railway infrastructure. We did find out before, turnouts are great infrastructure when you are manufacturing it. Once on track, generally regarded as very hard to maintain. The inspection has to be done manually because we can't really get any information on that complex turnout infrastructure. No, that was past. Now, I think what we can do is instrumented revenue vehicle technology is capable of understanding where the turnout point is, where the turnout crossing is, and how they are deteriorating. And this accurate information would give us enough reliable, repeatable information to see how the turnout is deteriorating and what sort of maintenance has to be done. And to confirm that, we have got images. So we can see the information that we have collected on a point or on a crossing where majority of the damage happens. We can actually say how well they have been maintained or not maintained. So that is the other part that I want to highlight. I think finally, and probably coming to closer to my presentation, and I'm not sure how I'm traveling, but probably I'm going reasonably well. Ballast. Ballast life estimation is an art. A lot of people think that if you know at the start what the ballast track deterioration rate is, at a certain point you measure it, these are the two red dots, you can actually draw a straight line and say at the pre-set engineering requirement, it's going to need to be replaced. No. I think that is very conservative prediction of ballast life. This is wasting a ballast life, ballast which can be lasting even further. if you have information that is how it's deteriorating using the models that I'm highlighting or the measurements that I'm highlighting, then you can actually start looking at how to really get that the real life, true life of the ballast. What does that mean is you can, through monitoring, you can actually understand how the ballast is deteriorating over a period of time and what is the actual extension of that ballast can be, not just on the, based on the couple of measurements that we normally do as railway engineers in the past. Now we have got capability to really extend the ballast life. You need that information because ballast is very expensive and it also creates a lot of difficulty to replace ballast which is on the track. So like for example, dedicated freight corridor would actually need, after 30 years or whatever the design life, need to replace the ballast and they need to know what has to be done. Along with that, I actually highlight the ballast rail condition assessment. Once you have identified the ballast has got life left, you need to continuously monitor. And the cameras are such a, the line cameras are very, very advanced nowadays. You can actually get a good image of what is happening on your ballast. And using that ballast information, that is a key part of containing risk when extending asset life. So you can decide how to extend it based on engineering parameters that I have shown how the track is deteriorating, but you need to continuously monitor what is the condition of the ballast as well, using the things that I'm shown here. For example, skewing of sleepers or ballast powdering and fines of ballast. They are the ways that you can actually start looking at it. So I've explained to you how instrumental car works in the past, but getting that instrumental car information, which is on the left graph, we identify where the problems are, then we get the images along with that, and using that images, then what we do is looking at individual defect, how it's deteriorating over a period of time. So you know that deterioration, how it's happening, like for example squat on a rail, how it's actually getting worse, and what is the impact of that squat on the train which is running, which is impacting on the rail, which is what I'm showing now, is actually how that it all stable, suddenly that squat is becoming a problem for the trains which are running through that track. And that information, bringing that together, well, first you actually know the information, the squat, what is happening to the vertical acceleration, and then the engineering mindset comes in, how do I manage that one to reduce the G force that is going into the rail. And that is the way it is actually increased the ability to improve the resilience of railway infrastructure. So in a nutshell, I would say using advanced real-time systems monitoring, such as instrumented revenue vehicle or anything else that is capable of doing that type of capability measurement, it enhances the asset management processes and improve resilience. That is a simple message. If you have that information, you can use the data-driven approach to look after your railway infrastructure and forecast when the maintenance has to be done. If you haven't really planned it early enough, that would give a more informed maintenance activities to protect your railway asset. You ask any of the railway heavy haul railways which has got instrumented revenue vehicle technology, they use instrumented revenue vehicle technology to protect their asset, nothing else, because asset is very critical and very expensive. With that, I actually want to complete my presentation by highlighting the capability of instrumented revenue vehicle technology. As I said, in a summary, it can measure, it can provide insight, it can provide forecast. For that particular capability, the significant recognition in Australia as well as overseas been provided for this advanced instrumented revenue vehicle technology. Thank you.
You have heard a very excellent presentation in which he has brought out how in the field we can make use of such type of equipment. I think if we look back, like for me, who has put in 50 years in the railways, we have come a long way. I remember the era which we grew up, there was a portable unit attached on a fast running express train, Rajdhani or whatever train at that time. So when you used to get a quick record in the section, what's happening about the track, track parameters only. But now, as he explains, there are so many things which you can monitor in the run. And as I said in the beginning, DFCCIL can take a cue, and rather they can decide what sort of like this type of cars are suitable to their systems. Now, I just have another speaker. Next speaker is Mr. Wesley Thomas from Loram Maintenance of Way, USA. As you all know, Loram is one of the best known names in the railway maintenance of way worldwide, particularly in rail grinding and rail integrity. Mr. Wesley Thomas will describe how a digital twin was used to reduce the risk of vertical split head defects and how to optimize the target rail profile. As you know, when we think of heavy haul, or for that matter railway infrastructure, rail is the costliest component in a track. So it is in our interest that we drive maximum mileage out of it, and we protect this asset fully, and we make sure that the failure doesn't occur in the operation phase. So I know this title of the presentation which he is going to make is Digital Twin Case Study, Vertical Split Head Risk Reduction and Target Profile Optimization. So let's again welcome Mr. Wesley Thomas for his presentation.
Thank you, sir. Good afternoon, everyone. First, I'd like to start this presentation with some important acknowledgements. First, I'd like to say thank you to Mr. Kumar and the DFCCIL team for this invitation and having the opportunity to share some of these learnings with you all. I'd like to recognize Mr. Rajender Sehgal and Mr. Yash Sehgal from Vanhana and the entire Vanhana team who have been long-term partners and contributed components to this presentation. I'd like to acknowledge my team at Loram, Mr. Brandon Rittering, and all the smart people who helped take this technology, build it, and implement it. But most importantly, I'd like to highlight my co-author of this paper, Mr. Daniel Hampton from the CSX. The CSX is a 30,000 kilometer heavy haul freight railroad in the United States, and Daniel Hampton is responsible for contracted services, of which rail grinding is one of them. And he was really the inspiration and was driving a lot of the implementation and change that we'll see here. So I'll do my best to present on his behalf. The content that we'll share today is a case study over the last number of years where CSX has been implementing some of the technologies that were in this pillar today. Systems intelligence tools, digital twins, prescriptive maintenance tools. And what I really wanted to share with this audience is some of the key things that we've learned, some of the key challenges, and some of the results that Dan and the CSX have seen from this work. But also I've taken the liberty to add a few examples of similar work we've already done here in India, as we'll be getting started with more of this work around the network, just to put it into context here locally and some of the things that we're excited about bringing some of these opportunities to bear here in India. So thank you very much. Where I wanted to start, based on Carrie's thoughtful guidance, is the problem to solve. And this is really where this story starts, of a very serious problem to solve. This is February of 2015 at Mount Carmel, West Virginia, where CSX experienced a very significant derailment of a number of tanker cars, leading to evacuation of the local homes. And the root cause of this derailment was a vertical split head defect that had been hidden underneath poor condition surface of the rail. And so it wasn't able to be detected in time before the rail broke and the derailment occurred. So this is a long time ago, but this was right at the time when Dan Hampton had taken over the rail grinding program at CSX. He was about a month into his job at the time. And this is just about the time that LORAM started working with the CSX and taken over from the grinding program from some other folks. So it really formed the focus of what are we trying to prevent and what problem are we ultimately trying to make sure that something like this never happens again. And these bar chart, or the line charts you see here are some of the results that Dan Hampton's been able to implement over the last 10 years. The black line is the transverse defect rates at CSX, and the red lines are the surface shelling and corrugation, the type of damage that was covering up that vertical split head. And there's numbers there. You can see that we kind of working together with the team, we're able to take some more data, make a number of changes to the grinding strategy, and ultimately have driven down those defects by 70% and 94% over that 10-year long-term partnership. So it's been quite successful. Some ideas that we tried out in the field worked, some didn't work, and we just had to continuously improve and get better. But you can see in the last few years, the key consideration here is we needed to find some technologies and some new approaches to help get rid of that last long tail of the remaining defects and really continue to drive down this rate. And that's really where we've focused on some of the technologies that we'll show today. And this is a vertical split head. And it became very timely again about 2 years ago, where CSX started seeing these vertical split head shears occurring across the network and breaking rail again in a pretty significant way. And you can see here that typically vertical split heads split right down the middle. It's usually due to some material deformation inside the rail steel itself. But these defects were splitting on that gauge corner, so right on the edge there of what we're seeing. And the key consideration here is that that does not flag the signaling system, so the track doesn't know that there's a problem until somebody comes to it, hopefully an inspector, but worst case, a train. So it's a relatively low frequency problem, but it's a very high risk problem that we wanted to investigate further and see if we could solve. And so that's where we've started applying some of these new technologies. The first one is a systems intelligence tool that we've worked with the CSX on implementing. But this tool effectively takes the ultrasonic inspections done by Sperry on the CSX network, and anytime a defect or a broken rail is identified, it's sent automatically back to this database where it's overlaid with information of the tonnage, information of the grinding history, information of the track in a thoughtful way. And really what this gives us an opportunity to do is be able to see a problem and very quickly understand what the context of that problem is and try to see if there's some common themes or root causes of those defects around the network. So we'll see there. So having the access to the rail inspection vehicle, the grinding history, all together with that is key. And as Emily mentioned, a lot of these problems, if you can't get your hands on the data in one place and actually do something with it, it's not very useful. But one of the things I'll say I'm quite jealous of over here in India is some of the test sites that Vandhana and the team have installed across the country, where this is kind of seems to be the equivalent here in India of test sites where the grind history is tracked, the surface condition is tracked, the rail profile over time is tracked. And this is a really great way to have a very large team of test sites where you can understand how the rail is performing in different zones around the country and be able to understand where can we make improvements. So in the absence of these types of systems intelligence tools, this is quite a resource for you all to have. And this is the work of the systems intelligence now moving into the digital twin and some of the key considerations we've learned. The digital twin technology, as we call it, is a physics-based digital twin. And essentially what it's meaning is we're trying to simulate there on the left what the wheels coming into contact with the rails, how it's creating a contact band on the rail, and try to understand how it's degrading over time in its current condition. So then we can test out if I make changes or isolate certain variables in that track, what are the things that I need to fix? And if I make the fix, can I quantify, is it going to be successful or not before we put it into the track? So these simulations that you see here are from us going through all of those examples of vertical split heads that occurred. We had identified that there were some common rail and common track problems in all of those locations. There was some wide gauge, but more importantly, the rails had started to cant out, going kind of out towards the outside, and almost all of these locations had a very severe lip of the rail that had been growing over time, and the current target grinding profile, the shape when the grinder comes and it's trying to recreate the rail to, was set up essentially not to take this location off. So over time, with more and more traffic, more and more grinding, these lips would get larger and larger. And as we put these into the simulation, we could compare on the top there, that's that normal curve, normal contact, and the red area is the damaging contact. When we put these factors into the model, you can see there on the right, this is the low rail, that the contact band shifts very aggressively onto that lip. The damaging contact starts to concentrate in that lip, and that lip is already a weak point in the material. So you can imagine the damage is being accumulated there, it's not being taken off very effectively by the target profile, and eventually you're seeing it shear right off as the cracks grow. So this was a really helpful way for us to investigate some of the hypotheses around the root cause and then understand what changes we had to make to prevent this from happening in the future. And again, I just pulled up some examples of some test site measurements here in India, but I'll just say in all heavy haul networks, these rail lips on the field side and the gauge side are going to form under these conditions. And these are just some examples here from India where we're seeing the lips forming both on the field and the gauge side in certain locations. And we're just starting to learn how important it is to prevent those from occurring in the first place and treat them when they are there. The other thing I really wanted to highlight that we learned from this work before we go on designing the solution is, as many folks have talked about today, Mr. Kumar, Kerry, the way to fix these problems is to work in a system. And one of the most important sets of data and one of the most important partners in this decision for the wheel-rail interface is the mechanical and traffic teams. So these are some presentations from many years ago that Dan and I did, but it was showing the impact of how much the loading of each of your cars, the speed of your cars going around a curve, and the wheel shapes and the distribution of those wheel shapes impact the contact band, the damaging contact, the wear of the rail, and ultimately the life of the rail and these types of problems. So this is something where I just wanted to highlight, we've been working with the CSX very aggressively on using their wild site data to understand the traffic, using their wheel profile detectors to get the wheel data. And you can see some systems have very good quality. You can see the one in the bottom right there kind of looks like spaghetti. It does not have very good quality. And what we've learned from this process, working with different systems, is that it's really important to make sure you're getting these data, you're validating that it's being maintained well, and that the vendors who will be able to share this data openly, make it easily available to the railroads, are going to be successful, because the CSX unfortunately had one vendor get acquired by another company. That company suddenly didn't want to share that data to their customer or to their partners after that, and CSX responded by ripping all their systems out, putting in new systems from another vendor, and now we've got the KLD systems there, and we're setting up some software right now to be able to access this data very well. But through going through the importance of this data and then how difficult it can be to get, I think just as a company at LORAM, we just keep learning, you need to be open with your data and be able to share with partners to be successful here, because we've seen it go the other way. And here's another example from here in India, just to help demonstrate the importance of the wheel data and the traffic data. In the left, there's two things I want to point out to you. The black line is the target rail shape, kind of the nominal rail shape of a certain partner we had worked on doing these studies and designing some rail profiles. So the black line is kind of the standard wheel. The Vandhana team had gone out and measured all 1,000, about 1,100 wheels, and you can see the colored lines show there's a much higher variation of how worn these wheels are, how many hollow wheels there are. So the important part as we design a solution for the grinding program, the simulation on the top, that is a simulation of this same location on the track, and it has the perfect black wheel profiles, and it has the perfect rail profiles. And it's hard to see here on the screens, but you can see a very nice concentrated contact band right in the middle, and there's no red area, which is the damaging surface contacts. So the good news is their standard target profile and their standard wheel profile match perfectly. But when you take that wheel out and you put in their actual thousands of wheels that have been measured on the bottom, you can see that the real story is very different. The contact band becomes much wider. There's a lot of damaging contact there in the red, and the location of where that contact band is moving to the gauge corners essentially would promote hunting and instability of these cars. So this is just to highlight the importance of then designing the grinding strategy and the shape of the rail to accommodate and understand that the wheels are not going to be perfect, and you have to find a better shape to match up with those wheel populations. And that's effectively the journey we've been on with the CSX for the last 5 years now. And this was the new rail profile that we had designed to target these vertical split heads. And the good news here is we went through a lot of process. There's a lot of tools behind it to come up with the strategy. But we actually ended up seeing that this target profile, when it was optimized, we had to go through many iterations, test them out. But we found one that both addressed that gauge corner, reduced the damaging contacts in that damage area and got the contact band back where it needed to be, but it also actually extended the wear life of the curves that we evaluated to show that we could also see some life extension. And the two key considerations here is, as we went through different iterations and we worked with different partners, we found that certain rail profiles down in the middle, you could very quickly just take a big cut of the gauge corner, take off a lot more metal, right, and do it kind of in an imprecise way. But as more metal needs to be removed by the grinding program, it means the grinders have to go slower, and it's a very expensive asset to own and operate and maintain. So what we found is when the first iteration that had been designed was put into our grinding scheduling tool, essentially it said, all the grinding you had planned to do by June will now be done by September. Your productivity just got cut by 30%, and that is millions of dollars, very significant change. And so CSX, you can imagine, said, nope, that is not an acceptable outcome to solve this problem. And so through the iterations, we were able to find a better performing rail life on the top right, but we were able to also make sure we're taking the minimum amount of metal off in the precise right locations of that railhead so that you could achieve the benefits that you were looking for, but maintain the productivity of the grinder and make sure you're not over-investing in this change. So this was a big learning from Dan, where we were kind of developing these tools over the last couple of years, and he said it's really important to not only consider the benefits or the outcome, but also what impact it's going to have on productivity and costs, and evaluate both of those components together to really come up with a decision. So the exciting news here is we designed these profiles working with the CSX, and Dan has now started implementing them all across the network for the curves, mild curves, tangents, and we're just sending out teams right now to get the initial field feedback, but it's been quite good. So I'm hopeful in the future we can share some of the field impact and see how the simulation and expected benefits translate to the field. Hopefully they're good, but I think we'll also see field feedback of where we can make more improvements over time. And again, this is just an example, again, from India. We've gone through this same process to design target profiles for different places in India, and we're going to be starting some large programs along with Vandhana here shortly. But again, this is just an example on the top right. That was the baseline profile, how it was performing. And on the bottom right, we see that after testing out about 5 or 6 iterations, we were able to come to a shape of the rail that reduced that red damaging contact and extended the rail life and matched up well with what they had been observing in the field. So I think there's a lot of opportunity here, and we're building a lot of tools to continue to automate this and make it more easily available to our railroad partners. The last 2 things I wanted to share with you, we've talked through the system intelligence tools. We've talked through the digital twin and some of the case studies and what we've learned there. But again, another big learning here is, we could come up with the best strategy with Dan and say, this is the target profile, this is how you want to do it. But for many years, even we were working with some consultants, and the work would end up staying on the shelf, right? It would be put on the shelf. We'd go, great, we did it, but if it doesn't get implemented and it doesn't get measured in the field, it's not effective. So we have a number of tools that Dan's been using for a long time to ensure that the target profiles are put into the grinders, the correct instructions of how to use those machines to achieve them are occurred. And probably most importantly is the work to go through the entire network, use some mathematics and some understanding to set how often do you need to grind in different locations around the network, reduce grinding in certain areas, do more in different areas based on their demand, and ultimately make sure we're planning our grinding fleet going around his very complicated network to hit those locations on the time that they need to. And Dan has really led that scheduling effort and using some tools, but he has been able to achieve a 94% compliance to his targets. We're updating those targets to make them even more precise, but one of the things we've learned here is just that for some of his grinders where he gets a lot of track time and you get more productivity, he's been able to get 98% or higher. Recently, we had one grinder that was getting about an hour less of track time than it normally expects, and that number went down to 70% for a couple weeks because the grinder just wasn't able to catch up and get around the network as fast as possible. So again, just working with the operations team, getting the track access as needed, but then tracking how we're doing and where we can make improvements has been really important from these prescriptive maintenance tools. So that's everything I wanted to share. Certainly we've learned a lot, and both tough times and good times from working with Dan over the last number of years, but these are technologies we're excited to bring more to India and hopefully share some of these learnings so we don't have to go through them the second time and see if there's more opportunities. So thank you very much, and happy to take questions.
Thank you, Mr. Wesley Thomas, for an excellent presentation. This presentation has brought out a very important aspect that we have to also examine wheel profile, because that has also an impact on the rail wear. Now, DFCCIL is in a precarious position because the rolling stock is not dedicated. So Indian Railways is giving them whatever rolling stock, and they are only the carriers. So we'll have to find a way and means how to keep an eye on that aspect. Another aspect which he brought out, very important, the defect, vertical split head defect, which comes without any notice, and it's one of the dreaded type of defect in a rail. I recall in my career one derailment which occurred near Khanna station in Punjab in 2000, sometime in 2000, 26 years ago, where many casualties had occurred. It was one of the worst kind of derailment we faced. And naturally, this jolted Indian Railways to look into the solutions. Of course, various things were educated. One of the solutions which we implemented was degassing plant in the Bhilai, from where we get the rails. And then we strengthened the USFD mechanism on the Indian Railways and went for this grinding. That was the starting point, I recall. Now, even if we say DFCC is only carrying freight traffic, not passenger traffic, which we really bother in these type of casualties, but we can't afford such type of defect to cause a derailment, as we saw in one of the slide CSX has given. One of the dreaded slide, I've never seen such in my whole career. So thank you once again, Mr. Wesley Thomas, for a wonderful presentation. Thank you. Now, our next speaker is Mr. Marcel Taubert. He is Managing Director, Waslow Rail Services. As we know, any railwayman knows, Waslow Rail Services is one of the world's leader in rail milling and grinding. But today what we are going to listen from him, the introduction of hotspot milling, which is a complementary tool now which is working alongside grinding. As we know, no single rail maintenance technology will be sufficient to do everything. So let all these complementary technologies work together in tandem, each doing where it is best suited to extend the rail life. That is our crux, what we are talking, extending the rail life. And then protect the rail far more effectively than any single technology could do alone. So the title of presentation by Mr. Marcel Taubert is Cost-Effective Rail Life Extension, Integrating Hotspot Milling into Grinding Strategies. Over to Mr. Taubert.
Yes. Thank you very much for this introduction. Thank you, of course, very much to DFC and the organization team of this wonderful event. Thanks for this invitation. And as Mr. Kumar already said, it's this presentation is a little bit about milling. And by the way, you were the first one who mentioned milling today. And I think I hear it countless times grinding, which is, of course, a very dominant technology in rail maintenance. We are a strong believer, as you already said, in the complementary approach of different technologies, and this will be in the content of this presentation. So I do the marketing block quite short because I've already two of my colleagues were before me, and by the way, I can promise this is the last presentation of Foslo today. So as you can see, Foslo is a infrastructure dedicated company, meanwhile, delivering a lot of very essential components to the track infrastructure. And I'm representing the rail service part of Foslo, which is located in Germany, in Hamburg, but meanwhile serving worldwide networks with different rail maintenance and turnout maintenance services. For us, very important is that we always name ourselves technology open, so we tried to really find the right technologies for the right purpose. So that's why we have different type of grinding machines, milling machines, and we tried to use them in the best customer value. Talking about rail maintenance, I think that today three dominating rail maintenance technologies on the market. Of course, we have the conventional grinder, and LORAM is, from my perspective, the dominating and most experienced player in this segment. We have on the right corner the high-speed grinding, which I will not touch too much today because it's for freight lines, most likely not the right approach. It's more dedicated to high-speed lines, to very high-speed lines. But in the middle, the milling is a technology which is becoming more and more popular. Although I would clearly say in a properly maintained rail strategy, in a properly working rail grinding strategy, there should not be a lot of space for rail milling. Rail milling is somehow, I would call it the last exit before you have to replace a rail. It is strong when it comes to very heavy metal removal. But again, saying that, if you have a very strong and successful grinding strategy, the need for milling should be quite low. And this is where we see both technologies could work extremely complementary. And this is what will follow in the next slides. I took here an example which I found. It's already 10 years old publishment for a rail grinding strategy here in India, and I took it because it was from India, but it was as well, from my perspective, a typical rail grinding strategy, how we see it in a lot of especially heavy haul railroads. It's somehow programmatic, so it's depending on load tons, and as we can see here, a lot of the major aspect is grinding on all tangent track and let's say mild curves every 50 million gross tons, but having already something for or a different approach for sharp curves. So this is again something we can see in nearly all countries worldwide, this programmatic approach, load-based, and somehow a little bit differentiated already. But if we look into our practical reality, still we see rail defects. So we obviously have, and we call that hotspots, we still have areas where the grinding program does not work sufficient, or sometimes, let's face it, railroads just don't do it, or they save the money in the wrong end. So you find these type of defects out in the field. I clustered them in two different areas. One is the load and fatigue initiated rail defects. By the way, I'm happy that I didn't listed the vertical split head, because that would, for milling, definitely be too late. But the other defects you can see here are typically those which milling can handle. So it's a defect size of 2, sometimes 4, 6 millimeters. Assuming the rail head is still carrying enough material, you can still save a lot of these rails. On the other hand, again, with a good rail grinding strategy, you should have most of them under control, and they should just be occurring in some hotspots. And in addition to that, you have non-load initiated defects such as wheel burns, low welds. Those are not really related to the grinding strategy, but are still to be treated with a lot of rail material. So, coming back, why do we see that? Why do we see that? So, a lot of the theory around rail grinding is still based on magic wear rate. So basically, you, on one hand, of course, you create always different contact bands. You make sure that the wheel-rail interface is always healthy. And on the other hand, you create some artificial wear, because rail steel and wheel steel is becoming harder and harder, and in order to avoid rolling contact fatigue, you prevent it by some artificial wear. So what we all see in practice is that those cyclic grinding approaches we have, they work in the majority of the track. We see that we keep the rail defects under control, but there are some, and especially in the very sharp curves, or when sharp curves meet some other, let's say, difficult track conditions, that the defect growth rate is just higher than a classic cyclic grinding, and you come then to these hotspots where, again, even the best grinding strategy has its limit, but it should be in just a few cases. So let's translate this into, this is a global view on what, how are rail defects happening over the track. So you can see that, again, in sharp curves, you might have deep rail defects. It's happening quite fast. And your grinding strategy for the plain track, which is based on 50 million gross tons, is definitely not enough. But even if you add another cycle and you say, I'm going into the sharp curves of 25 million gross tons, you might still have areas where you would even need more passes. You might even do it every 10 million gross tons or below that. But then you reach some economic boundaries. This is just too expensive. So basically, can a conventional grinder remove those shown defects with 1 or 2 millimeters? Basically, it can, but such a production grinder is, as its name says, it's designed to do as many track miles as possible per night, per shift. So using this heavy tool and sacrificing these operational hours by going forward and backward to do enough passes would just be non-economically. So, and this is where we now come into the, well, where we see hotspot milling as a perfect addition, a complementary solution, is to say, let's focus with those milling machines on those small sections, hotspots where it's strongest. And they are not hundreds of meters, they're not kilometers. Usually they are then just a few hundred meters, or sometimes less than 100 meters. So from our perspective, a production grinder should do its cyclic grinding program as efficient as it can in all these operational boundaries. And what is left over, all those hotspots which have been shown, can be removed with small flexible machines which are just dedicated to take away these hotspots. This is where we see, again, a huge potential to make sure that the production grinder is doing production grinding and not fixing small issues and just ruining his planned schedule. So, and again, why is then milling a good solution? I already mentioned it. Milling is then the last exit before you have to replace rails. And presentation from Justin was already showing how painful it is to replace rails. This is something where you need a lot of time, and we have here an example from Deutsche Bahn to just replace such a 30-meter hotspot. To replace the rail would take them in average 8 to 8.5 hours, whereas milling 30 meters takes you 1.5 hours. So it's a huge time saving. So that's why we're, even if it's for grinding, too late. For milling, it might not be too late, and this is the last exit before replacing rails. Just to give you a little bit of content, what type of machine are we talking about? This is such a small milling machine. We call it VTM Compact. It just covers 150, 200 meters. of track per hour, so it's not very fast compared to a production grinder, but again, it does a completely different job. It removes up to 2 millimeters in one pass, and since it's such a compact machine, it's quite easy to deploy it in a network and take it out after the job is done. Always the question is, what does it leave behind? Usually a crack-free, defect-free rail, and usually as new profile. So milling is usually not intended to then do some target profiles. What you leave behind is usually the profile as it would be new. Otherwise, you would need difference of profiles, milling heads, possibly yes, but again, if you would replace it, you would have a new rail profile anyway. And this is what is what you leave behind with milling. I talked about the flexibility which is necessary. Again, this type of machine should just do what is not economic to be treated by the conventional grinder. So it will be extremely it needs to be extremely flexible. So we have designed this equipment to be unloaded on every level crossing. In Germany, for instance, we use it on a flat wagon, and from the flat wagon, you unload it just at the side where you need to mill the hotspot. And the pictures you see there are from North America, where we have a high rail trailer, which is giving us the demanded flexibility. Some other references, examples where we are already working with this small machine. And to sum it up, as we said, the advanced rail grinding strategies, and we believe that especially here on the dedicated freight corridors, where you started together with Loram and Vandana, there is a very successful grinding strategy. This should cover the majority of the work, and hotspot should be that additional tool to make sure that this performance of the production grinder is maintained, and just the hotspots are then treated with a hotspot milling machine. So again, this is our summary. I tried to speed up a little bit to give Ben as well some moments of time, but I think you can see what we tried to develop. Milling not as a better solution, not as a different solution, as a complementary solution. And this is where we believe brings a lot of value for the customer and a lot of rail life to the rail. Thank you very much.
Thank you, Mr. Marcel Taubert. Listening to your presentation, I went back 6 decades ago in college days, when we were all taken to the engineering workshop. We were asked to do the milling, we were asked to do the grinding. So I think the same technology we have brought to improve our rails. I'm so happy. As you all know, South Central Railway in Indian Railways is already having now exposure to rail grinding, and so is DFCCIL, about to begin. So, but this hotspot milling is a new concept. We have yet to, because you have rightly given the advantage, I understand, it's very appreciative, but we have to see how far it is going to improve such things, because you know, you have to evaluate cost benefit. I remember the first presentation, the slide given by Madam Kari Gonzalez. She said, we should not go for novelty. Before we go in for such novelty, we have to examine in detail. So it looks a good concept to me, but we'll have to see how far we can imbibe on our DFCCIL. Thank you once again, Mr. Taubert. Now, we have got last speaker of the day. He is Mr. Benjamin Hans from Holland, Western Australia. He is going to As you know, Holland has built a strong international reputation in the field of rail welding and rail maintenance technologies, particularly in supporting railways seeking to improve infrastructure reliability and long-term asset performance. Since heavy haul railways increasingly focus on life cycle optimization, welding technologies constitute important component of reliability-centered maintenance strategies. The title of presentation by Mr. Hans is Flash Butt Welding as a Reliability-Centered Maintenance Strategy for Heavy Haul Networks. So let's put our hands together to welcome Mr. Hans.
Thank you very much. Good afternoon. I do have the enviable position of presenting last. So I know I am standing between you and the end of day one. So I'll try to make this direct, informative, and hopefully at the end engaging. In heavy haul railways, infrastructure does not typically fail everywhere at once. It fails at the weakest repeatable point. This point can be the rail world. So today I'll talk about flash butt welding, not as a technology, but as a reliability-centered maintenance strategy for heavy haul networks, and how we're moving beyond traditional maintenance philosophy. So just a quick bit about myself. I've been involved in the rail industry for 15 years now. Throughout that time, I've specialised in turning rail technology into practical field outcomes. My history has included delivering construction and maintenance on some of the world's heaviest haul networks, and most notably for the discussion today, the implementation of flash butt welding and its integration into maintenance practices. So just a little bit about Holland as well, in terms of our global footprint. Within our organisation, we have over 900 team members. We actually are an OEM, but we are also an operator as well. So we have the world's largest contracting fleet of flash butt welders, which spans over 200 machines. And within that fleet of 200 welders, we actually have 3 of our hybrid welders. So that's our battery-powered welders. In terms of a global presence, we've seen our equipment in over 41 countries, and we've sold 175 welders globally. So it gives us a really good understanding of the different markets around the world and how the technology is adapted. In 2025, we completed 214,000 flash butt welds. So what that does is that gives us a really good data point to understand the nature of flash butt welding, how it's used, and how ultimately to get a consistent top quality weld. And then in terms of other parts of our business, we also do track geometry systems with over 500,000 kilometres of track tested in 2025. So India's leadership in heavy haul. So the dedicated freight corridor is one of the most significant freight railway developments underway anywhere in the world. We already heard this morning what has been developed and also the future plans for the dedicated freight corridor. But more importantly, it presents a unique opportunity from an engineering and maintenance perspective. Other heavy haul networks have evolved over decades. Maintenance philosophies were developed gradually through experience, failures, and changing demands. But DFCCIL has the opportunity to establish maintenance philosophy very early in the life cycle. What this is it allows a leading change in heavy haul railway. So as one of the newest large-scale freight networks in the world, the DFCCIL has the opportunity to evaluate lessons learned from established heavy haul networks and determine which practices remain relevant for the future. Now, the demands on heavy haul railways are increasing. The challenges facing modern heavy haul railways is no longer simply how to build the infrastructure, but the challenge is now how to maximise reliability, availability, and the asset life while minimising intervention throughout the life cycle of that infrastructure. The DFC is transforming transportation. So the heavy haul reliability challenge. So the challenges that face heavy haul networks around the world is the increasing higher axle loads, and I know we've talked about this today, and the DFC is future-proofed with designs that allow up to 32.5 tonne axle loads. And global heavy haul networks are pushing this even further with the planned implementation of up to 45 tonne axle loads. What this means is we're seeing an increased dynamic loading at the wheel-rail interface contact point. Now, like all heavy haul networks, this also means that we're looking to increase the cumulative tonnage with greater cumulative tonnage than we've ever seen before, because it puts an emphasis on the utilisation of rail infrastructure. It continues to be the most effective and efficient way for bulk transportation when used correctly. So with that, we look at other aspects, including rail quality. So we're now looking at harder rail grades that provide improved wheel-rail interface. And what we've seen is an increase in the hardness of the rail going from 260 hardness Brunel up to in excess of 420 hardness Brunel hyper-eutectoid rails. But one of the greatest challenges that we're facing is shorter maintenance windows. This is the operational challenge for maintenance teams, but what this does is it applies a pressure to increase productivity in the windows that are made available. As intensity rises, weak points become more expensive. So why weld quality matters when we talk about this. We have cyclic loading. So where increased freight traffic subjects rail welds to more frequent loading, which in turn has a reduced time frame in which the rail infrastructure manager have to observe the performance of the welds and also react accordingly. The contact stresses due to increased axle loads have placed greater contact stress between the wheel-rail interface at the weld, and this in turn demands a greater performance of the weld zone in the rail. The forces that we're also seeing, and we've talked about track stability today, rail welds must be able to withstand the full magnitude of longitudinal forces. Failure to replicate the mechanical strength and ductility of the parent rail results in the first point of failure under thermal forces. Weld deformation is also paramount to the life cycle of a weld and the structural strength of that weld to perform under the heavy stresses of heavy haul rail networks. And ultimately, infrastructure reliability. The rail infrastructure is only as strong as its weakest link. The engineering practices fail to achieve optimum life cycle value if the weld cannot last as long as the rest of the infrastructure. Weld reliability is not a minor detail. Now, flush butt welding has already won the quality argument. It's industry accepted that it has a superior performance versus other welding processes. Laboratory testing has proven flush butt welds outperform load testing of other weld processes and provide improved metallurgical structure. Flush butt welds also outperform other weld processes in field performance, providing greater reliability and ultimately safety. And repeatability and automation of the process provides greater consistency of the rail weld and in turn, greater predictability of the asset performance. So if we see below, and it's a little bit hard to see, but there is a bit of a graph there that shows the difference between the hardness and the heat affected zone of an aluminothermic weld versus a flush butt weld. So you can see the flush butt weld more similarly replicates the parent rail hardness, but also the heat affected zone in which we see the battering and deformation of the weld is severely decreased. From a basic metallurgy perspective, flush butt is a forging over a casting process, so it eliminates the need for any filler materials, which then also mitigates risks for things like voids and porosity. It's a far more automated process than other traditional welding processes, so it does mitigate some of the risk of the human variable inputs. From a heat affected zone, as we've talked about, it's reduced, so the deformation that we see in the weld is also reduced, and then ultimately the performance. But more importantly, I'll jump to the bottom, it's the failure rate. It does have a statistically proven lower failure rate than other welding processes, and that's what's important. So the debate is no longer whether flush butt can produce a better weld. So the industry shift. So the traditional use of flush butt welding has widely been adopted throughout global heavy haul networks during the construction phase, predominantly due to its capacity to be able to produce high volumes of welds efficiently in a construction environment. Now, construction environments had some advantages, such as access constraints were reduced because there was minimal interface with rolling stock pathways. Long welded rails could easily be welded and handled in fixed locations. A weld could be performed every few minutes, so there was the speed. Automation of the weld processes itself meant it was less dependent on hard-to-find skill sets. Large volume production provided cost savings per weld when compared to other weld processes. The weld quality advantage mitigated the contractor and the network owner's risk as well, and the methodology was easily incorporated into construction practices. Flashback traditionally was seldom used in maintenance environments, as methodologies were based on traditional practices and also lacked the industry expertise to efficiently implement them into a maintenance. However, increasing demands on heavy haul railways drove performance and cost analysis. So historically, there's been a focus on the cost of performing maintenance. Flashback was not rejected because of weld quality. It was constrained by the implementation costs. However, modern heavy haul railways increasingly focus on the cost of intervention. Every broken rail has a cost, whether it be the cost of the rail, consumables, equipment, and even labour. Every possession has a cost, whether it be lost rolling stock pathways and the increased cost to recover those pathways, the knock-on effect, the delays at the freight and the availability at the destination point, and a term we all hate to hear, consequential damages. And ultimately, what is the cost of a derailment? We've already spoke about some of the implications seen from derailments, and I've been lucky enough to have the previous presenters show some of that. So what that means is the cheapest weld to install doesn't necessarily mean it's the cheapest weld to own. The cheapest weld to own is the one that provides that lasts the longest, requires the fewest interventions, provides the greatest lifecycle performance, and returns the most track time back to operations. The cost of network reliability and availability outweighed the cost of performing a better weld. So global heavy haul rail networks are moving in the same direction. In North America, we've seen some Class 1 railroads remove aluminium thermic welds within a set life cycle period. This has seen a reduction in the total allowable time in which an AT weld is allowed to stay in track from the time it's done. We've also seen a greater criteria around the total rail wear allowance for the acceptance of AT welds to remain in track. And what we've also done through the data is Class 1 rail networks have analysed that 48% of broken rails in 2025 were field related, driving the need for a more reliable process. If we take cases from the Australia and the Pilbara network, which we've heard about today, there are times where AT welds may only be used in place of flashback welds for emergency circumstances. Some networks have mandated an AT weld must be replaced within 48 hours of its installation with a flashback weld, and at times permission must be given for the use of AT weld. If we look to Brazil, we see the continued integration of flashback welding into the maintenance programs. This is because the weld quality and performance continues to play a greater role in the network accessibility restrictions. And weld technology and expertise has improved, allowing for networks to harness the advantages of flashback welding. Now, these regions and the companies implementing these are commercial organisations, making decisions based on operational outcomes. They are high consequence railways. If flashback welding did not create value, they would not continue to expand its use. The reality is these railways have concluded that the long-term reliability benefits outweigh the short-term maintenance costs to complete flashback welding. The most demanding railways use flashback because it produces value. So the challenges to implementation of better welds. There have been historical challenges and operational limitations associated with flashback maintenance were accepted as unavoidable. Rail infrastructure was designed to incorporate historical maintenance practices. Flash butt welders were large pieces of equipment that were difficult to incorporate into agile mobile platforms that could easily access the rail corridor. Older control systems lacked the ability to consistently consume the same amount of rail each time. This in turn meant it was difficult to perform closure welds and stress restoration welds. The methodology for in-track welding was different to that of other welding processes. Flash butt welding is a consumption-based process rather than an additive process. And flash butt had traditionally consumed over 30 millimetres of steel. There was also the expertise required to effectively use flash butt efficiently. As the saying goes, you can't know what you don't know. There's also the human aspect of resistance to new practices and technology, and ultimately there's a cost. It's expensive equipment, and the recovery of investment, if only doing a few welds, is hard, and there's also the understanding of what maintenance and spares are required. But every rail network faces these same challenges, but success has been proven. So how do we take on board these challenges and move forward? The welding equipment design has evolved. OEMs such as Holland have created flexibility in their design. And these design improvements have come from practical application. Like I said, Holland aren't just an OEM, we are also an operator. So with a fleet of over 200 flash butt welders, we are constantly looking at our design and how we can better perform it, because we too need a return on our investment. We're also able to do better integration onto mobile platforms, utilising our knowledge to pick the best platform for the scope of works in which the weld is going to perform, but also understanding the constraints involved on different rail networks. And for us, it's what will work best for the dedicated freight corridor, if we're talking about today. We are consistently evolving as well to meet the market needs globally, and hence the reason why we now have a battery-powered welder. So you can see in the pictures there, we've got 4 different platforms in which our welders are used today. In the top left corner, that's actually our battery-powered welder. And we've just recently actually demonstrated that in a show in America. In the top right and the bottom left corner is a configuration we call the portable plant welder. So you can see it's actually utilised in 2 different ways, and that is using existing rolling stock equipment that's readily available to the network, but also as a temporary fixed location. And on the bottom right is our standard deluxe container on a top of an RRV used as a mobile flash butt welder. The other side for us is the weld systems intelligence. So the new control system for us is the IntelliWeld system, and it allows for a greater finite control. When we compare our old technology with our new technology, our processing speeds have increased 5-fold. What this means is that it allows the system to monitor the weld throughout the cycle and has the ability to correct the weld to ensure a consistent weld quality. It's also allowed us to produce what we call the low consumption welds. Low consumption welds improve weld quality thanks to a narrower heat affected zone. It also allows us to adapt to network standards for stress restoration, reducing the amount of distance required to unfasten rail. Ultimately, LCW ensures that rail stress can be restored in maintenance practices rather than during de-stress campaigns, and therefore achieving more outcomes in the same maintenance window. Our equipment design has also changed for the capability. So we run an H650 welder head with a puller-like configuration. What this does is also provides a cost saving to our customers because it eliminates unnecessary force transmission through the welder head, which is the most expensive part of the componentry in any flash butt welder. It also allows for independent control of the rail gap, alignment, tension and release. What we are able to do is post-weld, the tensioning system can actually maintain hold of the rail while we release the welder head. And what this does is it allows us to confirm whether the weld has been acceptable to network standards, start to do quality control checks, and also begin refastening the rail as soon as possible, so accelerating the works. When we talk about time and the increased push to give pathways back, every single minute counts. But ultimately, what does 50 years of experience in welding give us? It gives us the ability to do equipment training and support. All of our equipment is set up and commissioned with experienced weld experts. Now, because of our global presence, we've been privy to a number of different rail grades, and so we're able to qualify on a number of different rail types. But we also work with rail manufacturers. Ultimately, as they look to improve their rail quality, if you can't weld the rail, you can't sell it. We also have the operational expertise through the provision of experienced staff. And what that allows us to do is to show the end user how to truly utilise all the features of the system. It provides operational know-how on how to create greater efficiencies and in-depth knowledge of the actual process itself and how we follow the path to success. We also look to create early engagement, not just with our customers, but also the network owners, and understand, for instance, how would the DFC best be able to implement our technology. We partner with local contractors to ensure full support at all times, but we also make sure that the IntelliWeld system now has the ability for experts to dial into the system from anywhere in the world. So we are able to monitor the graphs and provide greater support to our customers, but also provide troubleshooting and diagnostics. So if there's a problem, we can actually start to work with the teams anywhere in the world and rectify those problems so that the machine is back up and running as soon as possible, but also look at the weld quality perspective and correlate graph data and see, is there any degradation in the machine that ultimately would affect weld performance? After all, that is our number one goal. Thank you very much for taking the time, and I'm happy to take any questions.
Thank you, Mr. Hans, for a wonderful presentation. Debate is no longer whether flash but weld can produce better weld, as you mentioned in your slide. There is no doubt in our mind that flash butt welding is the best and most reliable technology. That's why DFCC went for it. So they have not permitted any thermit weld to that matter. I remember I was working as the engineer in DFCC. So I went to even Japan, where these rails were manufactured by Nippon. So we brought 260-meter rail, and for Eastern Corridor, from the first track which was built by me, it was again from Bhilai steel plant, 260-meter welded rail panels were brought. And then we, of course, we had to weld it further to make it to long welded rails. So the challenge now for the DFCC will be to concentrate and focus whether, if any failure occurs, to investigate why the quality went bad or whether anything else went, because there could be many reasons for a rail fracture. And of course, a question also rises, if it has happened, fracture, we have to take care of it in least possible time to restore the traffic. So what are the strategies available? Do we again go in for flash butt welding, because time is also limited for us, machines will not be available, or whether we permit at that time thermit welds? That's a question mark. Now, I think all my four speakers have done excellent work. They have presented wonderfully, and more importantly, they have stuck to the time limit. Nobody has exceeded the time given to them. And they have demonstrated the engineering reliability at scale requires successful integration of infrastructure, technology, maintenance, and operational knowledge. Even this was the last session, as I said when I started, it was difficult to concentrate, and I requested the audience, and I think they cooperated so well. They have asked so many questions from all my speakers. I have handed over the slips to each one. So I'll now hand over back to them to answer their questions. Though time is limited, we started half an hour late. I don't know, the organizers will tell me how much I can go beyond 6 o'clock, because I started at 16:30, half an hour behind my time limit.
Thank you. Thank you, Shiv Kumar. There are quite a few questions, so I'm just going to go through some of them, and if there are commonality, I might not really go through in detail. The question about what is the average range of axle load in Australia, I think it's very well known. It is in the range of 35 ton to 42 ton axle load, but we are going towards 45. It was mentioned as well before. And the other question was how an inspector goes to a site once it's identified and accurately understand what is the physical, to do a physical inspection of a defect identified by instrumented car. I might have not mentioned today, but I mentioned previously, the instrumented car has got a sub-meter accuracy of the location where the defects are identified. So it actually takes you to the exact location where the defect has been identified. The other question has been, what are the annual average tonnage of heavy haul routes? Again, I think up to 330 million gross ton has been recorded in Australia during a year. So that is one part of it. The other one is, can you provide economic impact in real terms, savings from optimized inspection maintenance? You have to ask the operators. You won't get that information, but I will give you some leading answers. If there's a derailment, it's $20 million a day. That is the impact for a heavy haul operator. So if you can avoid a derailment, and it has actually helped to avoid derailments continuously based on the records that we have, based on the track condition, it's $20 million that you save. And the majority of the maintenance, more than 50% maintenance, are determined through the advice of the instrumented car. If you have an instrumented car, that's how they have actually highlighted. So it actually helps significantly in that aspect. The other question is about data, amount of data that you collect. How do you really transmit that information, and what is the cost? There are a couple of questions along those lines. I think it is actually processing the data on the train itself. It makes it much easier. But at the same time, data transfer is not that expensive anymore. I think we actually collect that information. If we were doing it in the old way in Western Australia or even in Hong Kong, and even in Brazil, we collect the data and send it to Australia and then give advice from that. So data transfer is not that expensive. But when you start looking at images, it becomes very significant amount, and doing onboard data transfer processing is quite important. I might just take one more question that is here. It's the question about what is the grade of the rail that is used in heavy haul. It's 68 kg rail, head hardened rail. I think Brunel hardness is about 400. I leave there because I want others to answer as well their questions.
Thanks, Professor Ravi. I have a very thoughtful question from Axel, my colleague over there, asking, do I think that optical fiber sensing is promising technology for broken rail detection? And this is a very easy one to answer. It's a very quick, I have no idea, but that has never stopped me before from investigating it. So I'll just say what I learned from Dan in these vertical split heads was the kind of system that CSX had for using the signal to detect whether the rail was broken was not working when just the gauge corner sheared off. So that's now where I'm getting excited in my brain to say, are there other technologies that could detect those rail breaks? But since there's so few of them overall in their 30,000 kilometers, it's probably 6 examples that we ran into, right? Is it prevalent enough to make the case? But then I got excited. I found a white paper from the Federal Railway Administration, and shout out to the MXV in Kerry. They had tested out some fiber optic solutions on the test track, and so it looked promising. So out of my no knowledge, I'll just say that the MXV test track said it looks promising, and it's certainly, if it could help with this problem in a thoughtful way, it'd be something for the railroads to look at. So thank you, Axel.
Okay, a question I received is, can you share any heavy haul railways where rail milling has been used in place of rail grinding as an alternative? Well, I would think, currently our experience that nearly all of the heavy hauls are at least doing the first steps into rail milling. You have seen maybe the first slide, there was a picture of our small milling machine at Canadian National. At that place, it was a hotspot, which was basically a bridge, a wooden deck bridge. So, main reason there was to use it because of no sparks. So I think there's a lot of railroads finding their way in, but I'm struggling a little bit with the phrase of an alternative to rail grinding. For me, rail milling is more an alternative to rail replacement. Rail grinding should still do its job, but rail replacement we want to reduce significantly by rail milling, and that's the alternative. Hope that answers your question.
Thank you. Thank you very much. I do have a question. So on heavy haul, where flush butt welding has been used, when breakage occurs, what are the rectification strategies, and whether to go for thermite welds or again complete flush butt welding? So look, it probably goes in line with some of the challenges that we face. The strategies we look at is availability of the flush butt and the accessibility to the track, and obviously the requirement in which we've got to get track back running for the safe passage of the trains. Now, if I look at the Pilbara network, because they've adopted flush butt so heavily into the maintenance strategies, the availability and the accessibility to flush butt welders is far more common. So the ability to implement that back into the rectification of rail brakes is a lot easier. At that point, we do look at the approach of getting in there and then understanding when we do the rail brake, what are the other things that we can help mitigate. So restoring that track section back to its stress restoration at the same time. However, we aren't that naive that we recognise that there is still a place for thermite welding, and at times that is often a sufficient method to restore track in operation for rolling stock. However, what we then look at is the strategy of how do we replace that alumina thermic weld in the next available window so that we're reducing the risk to the network and replacing it with a better quality weld. So I hope that does answer the question, but please feel free to come up and I'm more than happy to talk at length along with anyone else that has questions. But thank you once again for this opportunity.
Thank you. As an ex-railway officer, it was my duty to ensure that even if the train was handed over late to me, I would pass it on, or rather reach the destination well before time. So we have saved 20 minutes. Thank you, everybody in this hall. It has been a wonderful day. With this, we conclude the proceedings of day one of the Internationl Heavy Haul Seminar 2026. On behalf of DFCCIL, I would like to express my sincere thanks to all the speakers, moderators, and more importantly to the delegates present over here for an engaging day of discussion. I look forward to welcome you tomorrow again for another day of engaging proceedings. Before I hand over the mic for the next part of proceedings, I would like to express my sincere thanks to MD DFCCIL and his team for organizing a seminar of this magnitude in a most befitting manner. It's a wonderful seminar. I think it will go in my memory forever. And let's give a big hand to them as a token of our appreciation. Thank you once again. Thank you.
Thank you very much. This session has truly offered a glimpse into the future of railway operations, where intelligent systems continuously learn, digital twins mirror real-world assets in real time, and predictive maintenance enables us to anticipate challenges before they arise. Ladies and gentlemen, we would now be presenting tokens of appreciation to each of our presenters for this session. May I please request Mr. Shobit Bhatnagar, Director, Operations and Business Development, to kindly please present tokens of respect for our panelists for the session and the moderator as well. We begin by thanking Professor Ravi Ravitharan for his presentation, for sharing his thoughts, his expertise, views, and ideas with all of us today. Thank you, Professor Ravi, for joining us here once again. So we begin by presenting you a very special memento of DFC, followed by the Statue of Unity. So we have another memento, the Statue of Unity. This is a very special memento. It serves as a symbol of national unity and pride. Thank you once again, Professor Ravi. We move ahead, and now we thank Mr. Wesley Thomas for his sharings with us. Thank you, Mr. Wesley, for your presentation and for joining us here in the seminar and this particular session. A very special memento, the Statue of Unity. Thank you very much again, Mr. Wesley. We thank Mr. Marcel for his presentation. Thank you, Mr. Marcel, for sharing your expertise with us, for your perspectives, and here's a token of appreciation and respect from DFCCIL. Thank you once again. Thank you, Mr. Marcel. Thank you, Mr. Benjamin, for joining us here again and sharing with us your views and thoughts. Thank you very much for your presentation. And here's a way we thank our panelists. Thank you once again, Mr. Benjamin. And of course, last but not the least, the moderator, Mr. Shiv Kumar. Thank you for conducting the session really well and for keeping it in time. Thank you once again. Thank you very much. So after the presentation of mementos, we now invite Director Infra, DFCCIL, Shri Anurag Sharma, to kindly please present the closing remarks.
Respected Mr. S.S. Gupta, PED Infra Railway Board, respected Managing Director Shri Praveen Kumar, respected Ms. Carrie Gonzalez, President and Chair IIHA, distinguished speakers from India and abroad, respected moderators, representatives of industry, academia and technology partners, senior officers of railways and DFCCIL, and ladies and gentlemen, good evening to all of you. It's my privilege to deliver the closing remarks at the end of this session of Internationl Heavy Haul Seminar 2026. Today's deliberations have clearly shown that heavy haul is not merely about running longer and heavier trains. It is about creating a complete ecosystem of robust engineering, reliable assets, intelligent monitoring, predictive maintenance, safe operations, and institutional learning. DFCCIL is operating one of the largest dedicated freight railway system in the world. Our corridors are already playing a transformational role in improving freight mobility, enhancing average speed, decongesting Indian railways, and supporting the national objective of shifting more and more freight from road to rail. However, as our operations scale up, our responsibility also increases. Our focus must now move from only asset creation to asset performance, asset reliability, and asset life cycle optimization. The next phase of DFC will be defined by how effectively we maintain our infrastructure, how intelligently we use our technology, and how consistently we provide reliable freight path to Indian Railway and logistic users. I would like to sincerely thank all the distinguished speakers and the moderators who shared their knowledge today. The presence of international experts from organizations such as IHHA, MXV Rail, Monash University, ENSCO, Lorem, Waslow, Getzner, Pendrol, Siemens, and other leading institutions has greatly enriched the seminar. I also thank our Indian experts, industry partners, and DFCCIL's officers for their valuable contribution. As we close day one, I would request all the participants to carry forward today's discussions into tomorrow's sessions. Let this seminar become not only a platform for exchange of ideas, but also a starting point for deeper collaboration among railway organizations, technology providers, research institutions, and industry partners. Thank you very much.
As rightly mentioned, a starting point for deeper collaborations. So we take back these learnings and wish to build on the work that has already been done. Thank you very much, ladies and gentlemen. With this, we conclude day one, and we'll see you tomorrow for the session at 9:45. We request you to be seated by 9:40 so that we can begin in time. Thank you very much, ladies and gentlemen, for joining us here. Thank you.